So if anyone has questions, again, how's the studying going? How's the reading going? There's a lot of material. I will tell you that. A, a 10 or 11 or 12-hour class is not for the faint of heart, especially when it's stacked vertically and not horizontally. So if everybody saw, that's why I said I hope you're studying in advance because it's really going to help.
I myself use the ham study online mostly.
Well, hopefully we're gonna make this a little bit real for you. Is there anybody here yet who had a ham license sometime in their past and let it expire? We sometimes get that too.
I had used ship single side bands before up to like 16 megs, but that's it.
How many do you have?
What?
How many do you have?
Signed up?
No,
243.
in the class.
Well, it hasn't even started yet.
200
When does it start?
Yep.
Does it start at 9?
Yeah, we start at 9 today.
Okay.
Are you going to join us?
I'm going to work.
Oh, you're going to work. Bye. Well, Hannah, wait. Do you have 15 seconds?
Sure.
You can introduce yourself.
Hi, I'm Hannah. I'm Scott's daughter. I've had my extra class license since I was, right after I turned 18. Ham radio super fun.
Nice.
I talked to Wallace and Fatuna on CW the other day, so that was fun.
Have a good day at work. And for those of you of school age, I'm going to give a little brag. Can everybody hear me okay?
Yes.
Okay. So she got her technician license when she was 15 or 16 because I said, it's really a good idea because there's a lot of scholarships out there. And then COVID hit, and I said, well, I offered you $100 for your technician license. I'll give you $100 if you get your general. It's like, okay, because she had 2 months off of school, and she was already taking physics, and she got her general license. I said, I'll give you $200 to get your extra, and she did. She spent 3 months studying for it and did it, and then went off to college. Helped to found the University of Oregon Ham Radio Club, applied for a bunch of scholarships that are specifically related to ham radio, and over a period of 4 years got $60,000 in radio scholarships,
Awesome.
which basically paid for her entire tuition. So,
That's great.
for
So
those
that
of you
same
who are school age, and I know Leighton, see, it can actually turn into actual money because what ends up happening is that there's, believe it or not, a lot of people who have been hams for a lot of years, right? And when they get to retirement age, they try to figure out what they're going to do, and they say, how to give back, and they take some of their take some of what they've done, and they teach and they mentor, and then eventually people do pass away. And what usually happens is that they've often put in their will that I want to start a scholarship fund, and there'll be $50,000 put in it for for a period of the next 10 years. Or you get an organization that decides they're going to fund scholarships to the tune of $200,000 a year, and it's going to be split up 20 ways every year. And okay, well, that's good. There are other scholarships out there, but let's say you've got a total of 100 scholarships, and there would be 20 or 25,000 people applying for it. Ham radio scholarships, there's maybe 200 or 250 people applying for that
Right.
same amount of
Right.
scholarships. So you basically have pre-qualified yourself. It makes it, a lot higher probability of getting something.
Yeah, it doesn't seem like the younger people are as much interested in it in today's time as what we were back when we were young.
Well, yeah, yes and no, because I can look at a lot of the people who I am friends with and operate and make contacts with on the air, and they're the exact same people who are interested today. What ends up happening is that there are, if you look back into, let's say, the 1950s, 1960s, you had a lot of people who got their license and never did anything with it. So in 10 years, it actually back then, in a year or two, it expired. There are people who got interested for a couple of years and then they never used it again and it expired. So today, what ends up happening is that those same kids who I was, that was 1984, there were lots of other things to do back then. I mean, there are a lot more things to do now, but I was still the kid who was interested in science and exploration and engineering and stuff like that. Yeah, the internet and cell phones exist, but you know what? It's still not as much fun. It's really not as much fun. It's the same kids who really like to do something challenging, do something different, and those people still exist. So it is the same people. We are. I mean, that's why I'm teaching this class. I know that not every single person who contacted me is going to be interested in this for the same reason that I am. And to be fair, there's, like back in the 1950s, I would say at least a third to a half of the people who signed up aren't even going to show up. And of people who do show up, I don't want people to think this is going to happen, but at least half of them won't even bother to take a test. It's just the way it is.
Yeah.
So try not to be that person, but I know it happens because I've been doing this. I've been I've been teaching classes like this in person and online for the last 8 years, and I've got a lot of data. And I don't want that to happen, but it does happen. So I figure of all the people who sign up, about 1 in 5 actually get their license. But I'm willing to accept that. Because I think that of that 1 in 5 who are actually interested and stay interested, they're the ones who remain active. So I think that I think that it's a good deal. Ham radio is not easy.
It can be overwhelming for somebody who has never really had any electrical or any radio experience at all. I mean, I can see
Yeah.
that it's very overwhelming with a lot of the questions and stuff.
But you also have as much time as you need to study. You have as much time as you need to take a test. It's not timed. The whole process is not timed. It's the process. Essentially, you're trading money for time. I mean, the process of getting a license is not expensive. I mean, if you're under 21, it ends up being what, $35 like everybody else, but no, I take that back. It ends up being no, if you're under 18, it ends up
Yeah.
it ends up basically being free. And there's a lot of help out there. So, besides the fact that if you're in school, this is something that, in addition to getting you scholarships, also will really help in school. I mean, it gives you experiences that most people don't have. It gives you opportunities that most people don't have.
Hey, Scott, just checking my mic here.
Sounds like a microphone.
All right, sounds good. I actually took your last class back, I think it was Labor Day weekend.
Mm-hmm.
But I have my father coming to take your class, so I'm getting him set up so that he can take the class.
Excellent. So do you have your license now?
Yep. Kilo Echo 9 Bravo India Foxtrot.
BIF. Very cool.
At least until my vanity calls come in, and that's going to be in a couple of days. So
Let's keep the fingers crossed. Is it something that everybody else wanted also, or no?
I don't think so. I wasn't going to try and go for anything too crazy to do. So yeah.
Yeah, it's at some point it's like for a call sign that's just like your initials. If your initials aren't anything really special, it's not hard. But sometimes you'll get, like for extra class, you'll get a 1x2 call, like N7JI, which I've held for 25 years. If let's say N7JC comes up because somebody passes away, and their license expires, there are people who pay attention to that because those call signs like that are really, really, really rare now. And the FCC might have 100 applications for one call sign. And then it just comes down to picking a number out of a hat.
So after your license expires, is that call sign immediately available, or
2 years.
okay, after the 2-year period, then that call sign becomes available to anyone else?
Yep. Yep.
So the moral of the story is don't let your license expire.
Don't let your license expire. It's good for you have to renew it every 10.
All right. Well, I'm going to go ahead and shut up and step away. I'll let him take over here. Have a good class.
Thank you. We will try. And I will continue getting myself ready. Try to figure out new things to try.
Yeah, it can be overwhelming when you're alone, but one thing I have noticed is when you do meet somebody else that is a ham, they're more than willing to share any help they can. So, what may seem overwhelming, as soon as you make some local friends and stuff, it usually becomes a lot easier. You get a lot of help.
And that's why I say that clubs are the lifeline for ham radio. Gotta find your local club. And it might be that there are a couple clubs. You find the club that suits you best, and you go with it. And go to meetings. And if they have have breakfast, go to a breakfast. If they have an event, go hang out at the event. Start meeting all the people in your local area and developing contacts, and get on the air. Many clubs have repeaters. Most people who are active will be active on their repeater, and you all get to know each other. So, and then of course, you say, well, what do I buy? And for every one person, you get 10 opinions.
Buy what you want.
Yeah, that
Maybe
is
more.
the question.
Yep. What do I build for an antenna? And then a half dozen people come over to your place, and they look at your property and come up with plans and ideas. And
Well, that 200 for my extra license will go a long way from you.
yeah. No, that was a one-time offer. That was a one-time deal. Sorry, one-time deal. I'd go.
Can we get that in writing, perhaps?
It was a one-time deal.
Yeah. Sorry, I brought it up.
Scott, you're in Eugene, correct?
Yeah.
What are I'm in Eugene as well. What are the radio clubs in the area?
Well, okay. So I'm the vice president of the Willamette Valley DX Club, which goes all the way from Longview down to the California border,
Wow.
and covers all of Oregon. Then you've got the Valley Radio Club, which is about 160 members. That meets in Eugene. Springfield Club, which is the Emerald Amateur Radio Society, or EARS. They've got about 50 members, of which I'm also a member.
Mhm.
And they meet once a month. And then you've got some kind of what I'd call special function clubs, like clubs that are more closely tied with the with ARES, Amateur Radio Emergency Service, more closely tied with working with hospitals, and then you've also got even bigger clubs. So you got
So how was it that Anchorage Amateur Radio Club is who I ended up signing up for this through?
for the exam. I'm also an examiner with Anchorage.
Ah, got it.
And so they were the anchor. Okay, so I'm a volunteer examiner with GLARG, Anchorage, ARRL, Laurel, and W5YI. And I since the first time a friend of mine did a proctored exam with Anchorage, I've really liked the way that they ran things. So when it came time to looking for somebody to help do a license exam for a remote, for a remote class, I asked, and they said, "Sure, we can do that. All hands on deck."
Is there a website that lists all the different local clubs, or this is KU7EKR? Just taking this as a refresher.
All right, are you a member of ARRL?
I don't think I am. Yeah.
Well, I strongly recommend that everyone joins ARRL. I'm also the section manager for the state of Oregon.
Mm-hmm.
And one of the reasons that it is beneficial to join ARRL is because, for instance, you go here, you go Club Finder.
Oh, okay.
Search for affiliated clubs. And we'll pick Oregon. I think at last count there were 48 or something. Let's see how many come up. 50.
Well, thank you for the info.
There are lots and lots and lots of clubs. And again, their clubs are kind of like the beating heart of ham radio for a lot of people. It's how people meet their friends in person and get to know each other. And so, and I recommend that everybody, explore the ARRL website. And membership for those under 21 is free. Membership for those under 26 is half price, which is about $30 a year. For everybody else, it's $60 a year, and that funds a big part of that funds Spectrum Defense, which we'll get to. Never know how many people are actually going to show up.
You said you had 200 and something sign up. You got 31 in the queue, as I see it.
Wait,
73.
73. There's no waiting room, so at least I don't have to deal with that. 74. Yeah. I was hoping for well over 100, and we've still got a couple of minutes to go, so.
You know you'll have some late arrivers too.
Oh yeah, yeah, and you know this it was not part of my plan to have a huge class. I just said, you know what, I'm just gonna I'm just not gonna turn anybody away and see what happens.
I'm going to have to duck out for a couple of minutes because my car picked this morning to have a dead battery.
Well, fun.
Yeah.
Hey, so I saw on the email that there were 35 slots for the test on Sunday.
Mm-hmm.
If those 35 are filled, then are we just like out of luck?
You know that there are often some people who will drop the exam or say I'm not ready and I'm going to sign up. I'm going to sign up for another time. You can go on to the website that you signed up for, and if you do want to change your date, you can change the date, which means that another slot will open up. So, just out of curiosity, how many people here weren't able to sign up because there weren't any slots for Sunday?
I actually got the last slot. I was number 35.
Okay. But
How
again,
do you know if you got the slot or not?
well, it takes your money.
Yeah, I think I got
You,
like
you would
32.
have gotten an email from them.
Yes.
Oh, I got an email yesterday saying that.
I didn't realize it was only limited to 35 slots.
Yeah, I got the email saying there was 35 slots. I'm assuming I got in then.
Yeah, if you got a receipt, and a link that says "Welcome
That
to
says
the,"
you were one of many candidates scheduled to take your amateur radio exam with us, following by Scott Rosenfield.
Yep.
So apparently I'm in.
Okay, and that
Does
means
the
that when
location where you take your test make any difference? Does the location where you take your test make any difference at all?
you know it doesn't. There are people who sign up for exams. I know this particular group has given exams to people overseas, military folks, you know, in fill in the blank country, et cetera, et
Okay.
cetera. So,
Great. Thank you.
all right, you know what? It's 9 o'clock here. It's other times and other places, and we're just going to start. Good morning. My name is Scott. My call sign is N7JI. Hopefully that will make a little sense as we continue into the class. And so we are here to talk about, learn about, and discover this thing called amateur radio, also known as ham radio, which has existed for over 100 years and keeps us all very, very busy and very interested. Lots of opportunities for personal growth, to help out the public in times of need, and so on and so forth. I've had my license since I was 15. Tomorrow will be the 40th anniversary of getting my license in the mail, and welcome to everybody. Thank you all for agreeing to share your Black Friday and then the Saturday. I guess we'll call it Cyber Saturday with me and everybody else. And this is a big class, and it's the biggest one I've ever taught. So I'm a little bit nervous and kind of had to prevent myself from feeling like I was going to throw up this morning. So, but you know, my biggest concern is that I will not know what I'm doing, which probably won't happen because I've been doing this for a lot of years. But you know, you never know. There's certain things you can't control. So, all right. So first thing to say about amateur radio and this particular class is that this is not a class to teach you how to use a radio. This is a class that will hopefully teach you what it is that makes ham radio work. Well, let me grab this real quick. Hey, Steve.
Yes.
What's up?
Yes. Is this Scott?
Yeah.
Yeah, I've got 6 reminders, but not the link to get into the course.
Okay. I'll make sure you get that.
Okay, thanks.
Okay. And I'm seeing that we're at 100 right now, and somebody just said that he didn't get the link to get into the course. So everybody, give me 1 second, and I'm going to make sure that it works. Da, da, da. 6
Yeah, I
notices.
believe the link was only in the first email that I got. The rest of it wasn't in there.
Yeah. Yeah, I believe that's true. And I could probably improve that. Whoop. Let me just send that out. Of course, that's also the same link that had everything else, all the information packet and stuff like that.
Right.
So, all right. So anyway, let's talk about what ham radio is and what it is not. So the first thing we're going to do to say what ham radio is and is not is we're going to take a look at the FCC rules, because what class would, what would a class be without the FCC rules? So let me open up my browser and go to the FCC rules and share that. Okay, so FCC. This is something that you actually have to know for the exam. Part 97. FCC, Amateur Radio Service Rules. Okay, everybody see this right here? This is what makes us exist. This amateur radio, first thing, it's the word amateur, spelled E-U-R, very important. Amateur comes from amat, which means to love. So an amateur is somebody who does something for the love of it, which also means they don't make any money. All right, so first thing, we don't make any money doing what we do. We are a voluntary, non-commercial service, as defined by the FCC and defined by the International Telecommunications Union, which is a part of the United Nations. Amateur radio exists on certain frequencies all over the world, in every country, even North Korea, in theory. Although they don't have any licensed amateurs right now. They have in the past. As you can see, these are just the sections of the rules. The most important part of these rules, these are searchable, by the way, which really helps. Notice this basis and purpose. There are 5 reasons we exist. All right? Non-commercial communication service, continuation extension of the amateur's proven ability to contribute to the advancement of the radio art. We are allowed to do all kinds of experimentation that other services are not. When you get a family radio service radio, handheld, like a little blister pack radio, it is allowed to operate only in certain ways on certain frequencies, and that is it. The same with GMRS, the same with Citizens Band. You get what you get. Amateur radio is an experimenter's dreamland. We're allowed to come up with our own protocols. We're allowed to build our own antennas. We're allowed to build our own equipment. We're allowed to do all kinds of cool stuff. Part of that is expansion of the existing reservoir of trained operators, technicians, and electronics experts. We are actually encouraged to go and fix our own stuff, unlike a lot of other things. Continuation and extension of the unique ability to enhance international goodwill. I like to talk about the fact that when I was about 19 years old, I used to be on the air all the time, and the Berlin Wall had not fallen yet. The Soviet Union still existed. The Eastern Bloc still existed. That did not stop me from making hundreds and hundreds of contacts with the Eastern Europeans, East Germany, Bulgaria, Moldova, people who were in the Soviet republics. When it came time to me getting a job, I had to apply for a security clearance. When I got that security clearance, I was in the interview and they said, have you ever spoken with or have any relationships with anyone who is considered an enemy of the United States? And I said, well, I mean, there are all the people who I have contacted who are from, former Soviet republics and Eastern Europe, and we weren't friendly with them. They said, are you a ham radio operator? I said, yes. They said, oh, you're fine. So we actually fit into that. And we are actually ambassadors to the rest of the world. Okay. So let's see. So that's part 97. It's important to remember that. Part 97, that is on every single exam. One question will be, what part of the FCC rules defines amateur radio? And that is part 97. So another big part of it is the fact that it is a non-commercial service. We are not allowed to play music. We are not allowed to make money. There are a couple of things that we can do. We can help out in times of emergencies. We can pass health and welfare traffic. We can work with a fire department for dispatching. We can do all kinds of things like that. Many different emergency functions, but we can't get paid for it. Okay. Other things. So what we're going to do is we are now going to talk very briefly about the process of getting a license. So the first thing you do is, I kind of view this as two different parallel tracks. The first of which is studying for an exam, right? So you can study for an exam, and I'm going to bring my wife and kids up in this particular case, who all are licensed. My wife has her tech, my daughter has her extra, my son has his general. None of them is an engineer. None of them had taken any engineering classes, electronics classes, or anything like that, yet they all passed their exams. And when I got my license, and then I got my technician general, advanced, and extra back in 1987, I had never taken an engineering class, and I'd never taken an electronics class. I had a natural tendency to do well on exams because I was in college, and I was good at studying because I was in college. I was used to studying, so I studied just like everybody else here is doing. I prepared for, and I took my tests. That doesn't mean that I understood everything. That took a long time to do. So when the time comes, you just need to take your exam. You need to prepare for and take your exam, and not necessarily worry about the fact that you don't know a lot of the material that's behind it. However, what I have had the benefit of doing is, over the past 40 years of being licensed, I've gone through engineering school. I've gone through engineering school again, and I've had my ham license for 40 years. I've been on the air a lot. I've built a lot of kits. I've built a lot of antennas. I've built a lot of things that didn't work. And I've worked for the last 25 years building machinery. So what I have is a lot of practical experience with all of this stuff. You know, essentially the hands-on part of all the stuff that you're going to be studying. And I feel like that's actually kind of like the missing part, which you don't necessarily need to pass an exam. But what it does is it makes the process of getting a license a lot more meaningful, I think, and fills in some of the blanks, you know, some of the information behind the questions. So what I like to think of this as is kind of like a beginner's radio theory class. And part of this class is teaching you how to set up and use a radio, how to set it up so that it operates within a certain system. Part of it is teaching you rules and regulations that require us, that we're required to follow. Part of it is teaching you how to not kill yourself or anyone else. That's actually a significant part of getting a license. That's actually part of the exam. But another part of it is understanding what it is that makes this stuff even work in the first place. And that's actually my favorite part of everything that I teach. All right, so the process of examination, technician license, is 35 questions. The question pool, hopefully you've all dug into it at least a little bit. The question pool is about 450 questions, of which you will get a few questions from each section of the question pool, making up a complete exam. And when the time comes, somebody will put it on your screen or hand you a piece of paper and say, here's your test. And you do your best to get 74% or higher, If you score 74% or higher, they process your license. Simple as that. Send it to the FCC. Eventually, it spits out a request to pay up. It costs $35 for the FCC to process the license, and that's true for pretty much any license that they process in any service. And one nice thing about it is that when you go to upgrade, and I do hope that all of you who will pass, notice I said maybe pass, but will pass, when you get to your general license, for instance, you pay to take the exam, depending on who you take it with. That'll cost anywhere between $0 and $15, but the FCC won't charge you at all for processing an upgrade. So they basically charge you $35 once every 10 years, unless you get a vanity call sign, which we will talk about. That's actually another license processing thing, so that costs $35. Okay. Any questions before we start?
Yeah, Scott, this is Jason from Houston. How you doing?
Good.
So if we go ahead and take the 35 and we feel confident enough and we get a passing grade, we can go ahead and at that point say, hey, I'd like to go ahead and take the next level, correct?
And hopefully you've at least looked at the material. In my experience, if somebody who crushes the technician license exam, there is a significant overlap between that exam and the general class exam. What's different about the general is that all the bands are different, the privileges are different, some of the technology is different, a little more complicated, and most people, unless they have an engineering degree, if they've never looked at the general class material and they really do well on the tech, will get between 50 and 60% on the general.
Sounds good. Thank you, sir.
Other questions? So here's the other thing. I can't make you study. I know I have learned I can only show you what to study and maybe how to study it, but I can't make you do the work. Ultimately, you have to do the work. This is on you. And this being here in the first place, this is a really good step. You look around this very large room that we have with 110 people signed up, 3 of which are me, so 107 other people. Everybody's here for the same reason. And this group of people is already taking that big first step, which is studying for and, moving forward and working at it. So
my biggest problem has been how to study. I've never completely figured that out.
And that really comes to, I've got study techniques. I know that the iPhone app, that ham radio exam app, it breaks the exam up into individual sections. And my daughter used it for all 3 exams. My son used it for both, and my wife used it for one. It's ham radio exam, and this one's dash tech, and I just put it in the chat. I also included it in that big informational packet that I sent out in the first place. And it allows you to basically practice one section at a time, because the whole question pool is 400 something questions. It's a lot of stuff. You got to go through it a lot of times to see everything and really understand what's going on. If you do one section at a time, it's a lot easier to deal with.
Yeah, I think part of the problem is that over the years, I used to memorize everything, and then the smartphone came to existence, and I was able to look everything up on command.
So the other thing is, if you're taking practice exams, if you've gone through all the questions and you can take a practice exam, if you could take 10 practice exams and you get over 85% every single time, you're going to pass. So that's a target. Because, you're going to get a little nervous, and that'll knock a couple questions off. You'll doubt yourself. If you're getting 85, 90%, you're going to pass. So. All right. Yeah, go ahead.
You need to get 75% on each test.
Yes. 70. It's
Whether
74.
it's
74% or higher.
whether it's technician or general or advanced.
Yep.
Okay. Thank you.
Yep. Absolutely. All right. Other questions before we get into it? When we get into it, there's a lot of stuff to get into. If you've read the book, we've got a lot of material to cover. All right, let's go.
I'm getting in the 90s on the test and everything. What I'm hoping to gain from this is just a little more understanding. I mean, most of it I understand, but there's a lot of it that it's more of I feel I'm memorizing the question rather than understanding where it comes from. And
that's excellent. That's excellent because that's why I'm teaching it. This is the stuff. This is the stuff that interests me. So, okay. So the first thing we're going to do. This is the first thing I draw. Can everybody see the whiteboard? Okay. Anyone who can't see the whiteboard should be visible to everyone. Okay. So this is a circle. How many degrees are in a circle? Everybody?
360.
360 degrees. And there's the first quadrant and the second quadrant and the third quadrant and the fourth quadrant. And the 0 degree mark is all the way there on the right-hand side. As we start on this circle, our angle increases and goes this way. This is just by convention. So we have two axes. We call this the x-axis and we call this the y-axis. And as we call this the unit circle, this has a radius of 1 unit. I know you probably didn't think you were going to be doing trig today, but we start off with our unit circle. Again, we have an angle that gets swept starting at 0 degrees. So what angle would this be on the vertical axis up there?
90.
90 degrees. Okay. So this is our 90 degree mark. How about on the other horizontal left side axis over here, the blue line?
180.
180. How about down at the bottom?
270.
That would be 270. Yes. Okay. And let me change my pen color a little. So that's the pink line, 270. Okay. And how about when we get back to the right-hand side?
360.
360. It's also, however, called 0 degrees. Right. So 360 and 0 are the same thing. All right. So now what we're going to do with this is we are going to draw out a line that looks like this, except I'm going to change the color and make it black. Okay, so here's our line, and here's our plus and our minus, and here's our angle. So important parts of this, we're going to redraw that because it's ugly. Okay, so what are some important angle marks that we've already put on that graph? How many degrees do we start at?
0.
0. Okay, so we're just going to mark 0 degrees right here. What's the next most interesting one?
90.
90.
90 degrees. Next one?
180.
180. Next?
270.
The next one?
360.
360.
Okay, so now what we're going to look at is how far above or below the ground, this being the ground on our circle, how far above or below the ground we are at any point on that circle. So if we're at 0 degrees, where are we with respect to the ground?
Ground level.
We're on the ground. Okay, so we're actually going to mark that as on the ground. Okay, so here we start on the ground. How about at 90 degrees?
You're at 1 plus 1.
Yep, it's the unit circle. It has a radius of 1. How about when we get over to the blue mark over on the left-hand side?
Unit 2.
Back to 0.
Back to 0. We're back on the ground.
Oh.
Okay. How about when we are at the pink line?
Minus 90.
Minus 1.
Minus 1. And how about at 360?
Back to 0.
Back to 0. Okay, and now we play connect the dots.
Say nice cosine wave.
Actually, sine wave. If we shifted it, it's a
Oh, I
cosine.
always do that. I'm sorry.
Yeah.
Scott, sign.
Yeah. Okay. So we have a sine wave. The function that tells us how much above or below, or our y-axis displacement, is known as a sine. So this is known as a sine wave.
Or a radio wave?
No, just a sine wave. Nope, just a sine wave. So now, given the fact that this circle goes around and around and around and around, what is to the left of the beginning?
The antenna?
No. Remember, this is just a graph. What's to the left over here? It just keeps going. And what's over to the right?
Okay.
So what?
Yeah,
So
it keeps going.
it keeps going. So what we're really looking at is a wave that goes like this.
So it just goes
Forever in both directions.
So
we
it
are
just
just
goes
looking.
0, 180, 360?
Yep. And what we're doing is we're just looking at a little piece of it. There's no real beginning or end to this process because the circle just spins around and around and around. Okay,
Can I
so
ask
now,
a question?
go ahead. Yeah.
So my understanding is this sine wave, as you call it, it just goes from 0 to 180 back to 360 continuously, up and down, up and down, up and down.
Yep.
Basically.
Yep.
Okay. Thank you.
Yeah, because you don't know where the circle is in the rotation. You don't know how many times it started, or assuming it goes forever, it'll just carve out that path forever. We just happen to mark a convenient reference point that says that's our beginning.
Infinite.
Yep. Okay, so now what we're going to do is we're going to take that circle that we drew and we're going to make it like this and go around on the circle. Okay. So it was 0 degrees, 360 degrees. And here's what our sine wave looks like. Whoop, like that. So now what we're going to do is make believe instead that this, instead of just being a circle, is a merry-go-round. And you are lucky enough to be on this merry-go-round as it's going around and around and around. And we are trying to figure out how far this way and this way you go. Well, when you're at this point, which I'm going to mark in green, you are right here. And when you're at this point in blue, you're right there. Because we're looking at the distance in the up and down direction. Okay, so what we can do from this point is say, how long does it take for us to make one full rotation on that merry-go-round?
Is it minutes or?
Well, it could be. What else could it be?
Milliseconds.
It could be milliseconds. It could be, but what's important is to note that it's a unit of time.
Depends on the frequency.
Well, it depends on the speed. It depends on the speed, how fast we're actually moving. So the amount of time that it takes to go around one time is known as t, which is also known as the period. Okay, so if we have a merry-go-round and we're going, time is equal to 10 seconds. How long does it take to make one full rotation?
10 seconds.
10 seconds.
Okay, if we were to look at this graph, how long does it take to plot out that graph?
5 seconds?
No, it's still 10 seconds.
10 seconds.
Oh,
right,
10
10 seconds.
Because it's a
Okay.
complete set.
Right, it makes one complete circle. So the other question now is, if we look at this, we say if our period is 10 seconds, how many times per second do we go around?
One
Point
the circle.
1.
Yeah, we go around 1/10 of a rotation per second. Okay, so it's per second.
Frequency.
That would be a frequency. How often does something happen? That's known as a frequency. If we now have a period of, let's say our new period is going to get really nauseous on this merry-go-round. 0.1 seconds. How long does it take, or how many times do we go around that merry-go-round every second?
10 times.
10 times. That would be our frequency is equal to 10 times per second. The unit of a thing per second is known as a hertz. So that means that our frequency would now be 10 hertz. So what we've now done is we've taken a very common motion, which is going around a circle. I mean, think about it, tires, galaxies, things go around in circles. It's really, convenient way to move in the universe. That translates to a time period, and something, 1 divided by the time period gives us a frequency. So let's say that we now have something that is going around 1,000 times per second. Our frequency would be how many hertz?
1/1,000.
No, it's 1,000 times per second. Our frequency would be 1,000 hertz. How long would it take to go around?
1,000th of a second.
Yeah, 1,000th of a second. That's our period. So what we have now is we have a relationship between our frequency and our period. If we were to change this and say, you know what, we're just going to imagine that we're not on there, thank goodness. And instead we're going to go around 1,000,000 times per second. What would our frequency be?
1 million
hertz.
1,000,000 hertz. How much time would it take to go around one time?
1/millionth of a second.
1/millionth of a second.
Of a
Oh,
second.
no. Yeah.
A millionth of a second.
1 millionth?
1,000,000th of a second.
1 microsecond.
Yep. So we have this right here. Another way to write this is 10 to the 6th power. We're going to get into this as well. So this would be 1 times 10 to the 6th hertz. This also has a name. Anyone know what 10 to the 6th is?
Mega.
Mega. So now our frequency becomes 1 megahertz. And by convention, if we now look at the time, we can go 1, 2, 3, 4, 5, 6 places. So this is 1 times 10 to the minus 6th seconds. Anyone know what 10 to the minus 6th has another name?
And a micro?
Yep.
Micro.
So that's 1 microsecond. Okay, so now what we've managed to do is define some prefixes, micro and mega. There's also milli and kilo and giga. Everyone's heard of a gigahertz or a giga, let's say a gigabyte. Then there's also nano and pico, which are very small. Nanotechnology, that means a billionth. Pico means a trillionth. So all of these things actually show up in the book, and they may be on your exam as well. And why is it that we bother to do this? Because let us say that we have a frequency of 352,000,000 hertz. What is the really important part of that number? There's actually 2 things about that number that are really important.
The 352 would be one part and the number of zeros the other?
Yeah, the 352 is what's really important here because this tells us it differentiates it between 353 and 351. The other thing is how many zeros are there? So what we can do with this is we can take this number and say we have a decimal point there, and we count 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So that would be 3.52 times 10 to the 9th hertz. And what that allows us to do is use scientific notation to basically denote something in a way that is easily managed. We can also write 10 to the 9th power as the big letter G for giga. So that frequency becomes 3.52 gigahertz. So that is why we use scientific notation. Another way that we do it is, for instance, we have a capacitor that is 0.00000000022 farads. Again, what's the really important number here? There's two things that are important.
22.
22.
And the amount of zeros.
And the amount of zeros. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We could write this as 2.2 times 10 to the minus 11th, but it turns out that minus 12th is a more conventional thing to do. So we could move it over here, and we have 22 times 10 to the minus 12th. 10 to the minus 12th is also known as a pico. This is in farads. So that's 22 picofarads. This is how we call capacitors that are very small. Most capacitors are small like that, which is why we do that. It makes it a lot easier to deal with those numbers. The other cool thing about this is that it allows us to very quickly deal with numbers that are very big and very small without having to worry too much. By convention, 10 to the minus 12th times 10 to the minus 12th is, we take the bases and we add the exponents together, and 12 minus 12 is?
0.
So that's 10 to the 0 power. Anything to the 0 power is 1. So what we've done is, instead of having to write a 1, 2, 3, 4, 5, 6, 1, 2, 3, 1, 2, 3 times 0.00000000001, we've instead written it like this, which saves a lot of space. Makes it a lot easier to punch into your calculator.
I have a question.
Yeah.
So would that be a picofarad?
That's a picofarad. And that's why we call it a picofarad. So it's 22 times 10 to the minus 12th farads is a picofarad. 22 picofarads. That's why we do that. It makes it a lot easier to deal with those big numbers. Okay, so now that we have established, this is actually all in the book too, but now that we've established that we have this circle with our 0 degrees, 90, 180, and 270 degrees, and we roll it around this way. Okay, let's see. Okay, so we now have this circle that's going around and around and around, and we have this graph that is going like this. We are now going to take this circle and we are going to roll it. We're going to rotate it 90 degrees so we're looking at it edge on. Imagine that you're looking at a bicycle tire, but all you can see is the tread. So we're going to take this part and spin it that way, and take this part and spin it that way along this axis. So all we get to see is a bicycle tire that looks like this. We're looking at it edge on. Okay, so now, let's say that we are a person that is standing on this bicycle tire as it's spinning around. All right, and we're basically going down like that, and then back up the backside. And then we go this way again, and this way again. If somebody could see us going up and down, all they would see is that we were moving like this, and then we were moving like this, and then moving like that, and moving like that. Would our speed always look the same or not?
No.
No.
No. And in fact, it would be peaked in the center, right there, going up and down. And when we got to the bottom, it would look like we stopped momentarily, because we're really looking at this graph, but now looking at it from the end. So now what we're going to do is we're going to take this, and we're going to take this wheel, and we are going to instead start to move it. And we're going to move it. Come on. We're going to move it this way with some speed or velocity v. So if our graph, if somebody were to look at us, we would see us going up and down and up and down and up and down like that. But then they start taking that up and down motion and adding another movement, which is side to side. What would they see again?
They would see
Sine
it.
wave.
They would see a sine wave.
Yeah.
But now, what would that sine wave, how long those waves are, what would that be proportional to?
The height.
Well, yes, but let's say the height doesn't change.
And, yeah.
How fast it's moving to the side.
Yes,
That would be,
thank you.
Frequency.
that would be the velocity. So now we have our frequency over here, how fast we're doing this. But if we're not moving at all they see is a dot moving up and down. And what I can do is let me do this. Okay, so what I'm going to do is hold up my phone here. And I'm going to turn on my camera and turn on my flashlight. Okay, can everybody see a flashlight?
Yeah.
Okay,
Yes.
here
Yeah.
we go. I'm going to be going up in a sinusoidal pattern, but what do you actually see being made? What shape?
Straight line.
A straight line up
A
and
L.
down. A straight line up and down. But now what happens if I start to move it to one side?
That's your velocity.
D.
You have a velocity, and what does it do to the side? What does it do to the straight line?
It widens it.
Turns into a sine wave.
It stretches it into a sine wave. But now the sine wave is proportional, the size of the sine wave is now proportional to how fast I was moving it across the screen. So I have a frequency which is proportional to how fast we're going around the circle, which is basically how fast I'm moving up and down. And now this circle is on its side, and we have a velocity. The velocity determines how fast the sine wave goes up and down, and how far it stretches out. If we were going really fast, it would look like this. If we were going really slow, it might look like this. Okay, so this is actually really important because let's say that we're making our circle go around and we're moving this at the speed of sound. The speed of sound is about 330 meters per second. Well, if we are going up and down at 300 and we're moving at 330 meters per second, And we have said, let's go ahead and make this frequency be an audible note of 330 hertz. So we have this circle that's spinning around 330 times every second. And every second, it's moving 330 meters to the right. Well, we know that a hertz is a cycle per second. It's a thing that happens per second. Well, we know that our velocity is 330 meters per second. So let's try to figure out what we can do with those to make them useful. Well, we could divide 330 meters per second and just arbitrarily divide it by 330. Would help if I could write cycles per second. So what do you all see right there? What could cancel out?
330.
Yeah, what else?
The seconds.
Per second.
Per second.
So 330 divided by 330 is?
1.
1 meter
per second.
Per cycle.
Cycle.
And this is a cycle. 1 full wave. So what does that mean? We just figured out that for this particular frequency and speed right here, we have something that says that 1 wave carves out a path of how long?
1 meter.
1 meter.
1 meter.
That is known as a wavelength, and it's measured in meters. Well, okay, and what did we divide? We divided our 330 meters per second. That's our velocity. And this one, cycles per second, is a frequency. So we now have this formula. Here we go.
So for this frequency, V over F equals 1 cycle?
Yeah. Our wavelength is 1 meter per cycle. Our wavelength is 1 meter.
Hey, Scott.
Yep.
What did you just write down at the bottom?
Lambda, which is the wavelength,
Okay.
is equal to the velocity divided by the frequency. And we can rewrite this. We have lambda is equal to velocity divided by frequency.
Alex got it in chat.
Oh, good. V is equal to F times lambda. Velocity is equal to frequency times wavelength. Okay, so now what we're going to do is we're going to say that our velocity, what did we use for our velocity there?
330 meters per second.
330.
Yeah, which was the speed of sound, right? Well, okay. Does something have to move at the speed of sound? Does something have
slower?
It could be anything, right? It could be moving in water. That would be sound waves. Those are pressure waves. They're moving in water. They're moving in any number of different things. So that also means that for a given frequency and a medium, if the velocity changes, that means that the wavelength changes as it travels through there. This is actually really important because we're now going to move into a different form of wave. Still looks like a wave. Okay, what's something you can say about the wave? It has a frequency. And how fast is that thing moving from one side to the other? It has a velocity. And because of that, it has a
cycle wavelength.
Wavelength. It has a wavelength, the length of the wave. Okay. So we're going to take a different kind of wave now. we are going to, instead of doing a wave that is a sound wave, we're going to take a wave that is something called an electromagnetic wave. Okay, so in order to understand this, what we start with is a little thing called an electron. Electron is a fundamental particle. It's actually part of the particle zoo. It's a negatively charged particle. It can't, to our knowledge, be broken down into anything else. And it has a charge that is negative. And if it sits there in space, it creates an electric field because it has a charge. So this generates an electric field. The closer you are to it, the stronger the electric field is. So if I were to take that electron and move it over here, where would my electric field be? It would
Wherever it is.
That's right. Now, would there still be some electric field at where it started? Yeah.
Yes.
But would it be as strong?
No.
No.
Right? Okay, so what if I moved it now back to where it started?
The whole thing? Or
Yeah, the electron. If I moved it back to where it started,
then it would have the same.
it would go back to the way it was.
Yep.
Okay, so what if I then took that electron and I moved it back and forth and back and forth and back and forth, and I did so at a particular frequency, and I was measuring the electric field strength over here at some random point.
Oscillation?
Yeah, if I were to move it back and forth, I would measure electric field strength.
The oscillation of it.
I would measure it changing at the same frequency as I was moving it back and forth, and its value would go up and down, and its electric field would do something like this in time. The other thing is that if I have a moving electric field, a moving electron, the movement of an electron, the movement of any electrical charge has a name.
Current.
What was that?
Current.
That is current. The movement of an electron from one point to another is defined as something called a current. The amount of electricity that's contained at one point generating the field is a potential, and that's known as a voltage. That's measured in volts. So we have a static electric charge, which is just sitting there, and this creates voltage, and this measured in volts, and then the movement of this thing back and forth, movement of electrons is known as a current, and that's measured in amperes. And as it turns out, if you have a current, a moving charge is a current, and it generates a magnetic field. An electric field is essentially the ability of something to store energy as a potential to do work. A magnetic field is the ability to store energy and essentially create magnetism. So now what we have is this charge that is moving back and forth, and as we measure it somewhere in space, what we find is that if we move it back and forth, it creates, if it's moving this way, it creates an electric field. Let's see, that's going up and down in time. It also generates a magnetic field which is perpendicular to the electric field at any point in time. When the electric field peaks, the magnetic field peaks, and they're perpendicular to each other. What's interesting is, no, they're actually in phase. What's interesting about this is that the electric field, if everybody holds up their right hand, your electric field is your thumb. Now stick out your index finger. You have to use the right hand. If you use the left hand, it's wrong. It doesn't work. Notice that they make a right angle. Your middle finger, if you stick it out, is the direction of movement of the displacement of energy. So there's your motion. This actually is generated by movement of an electron. It generates an electric field, a perpendicular magnetic field in a direction of motion. Okay. So they're all at right angles to each other as defined by your right hand. That's called the right hand rule. What's interesting is that the original electron, which is here on the left-hand side and is just moving back and forth, does not ever have to relocate. It just has to go back and forth within a certain space. When it does that, it generates ripples in the electric and magnetic fields, and these propagate at the speed of light into space. What's different about sound and electromagnetic waves is that sound waves require a medium to travel. Electromagnetic waves will travel through empty space, which is a very good thing. So, okay, as our electromagnetic waves are traveling, they travel at the speed of light. So, as we now are traveling at the speed of light, we have to write that formula again. V is equal to F times lambda. V is our velocity, and that's measured in meters per second. Our frequency is cycles per second. And our wavelength is measured in meters. Except now, what is our velocity? If we're at the speed of light.
330?
300 million meters per second.
3 times 10 to the 8th meters per second. Or 300 million meters per second. Or 300,000,000. Really fast, right? Okay, this has another name. It's called c. C is the speed of light. C is equal to F lambda. Okay, so now this is actually really significant because we now have a wave that is propagating at the speed of light. And it is propagating at the speed of light, which is really, really fast. And if you have a given frequency, that will generate a wavelength. So we now can say our wavelength is equal to c divided by the frequency. So once again, our wavelength and our frequency are inversely proportional to each other. So if we get a higher frequency, what happens to our wavelength? If we get a bigger number down here, under here,
Get smaller.
it gets smaller. Higher frequency, shorter wavelength. Kind of makes shorter frequency or lower frequency, longer wavelength. Anybody guess why a tuba is so big and a piccolo so small?
Wavelength.
It's wavelength and frequency. So there you go. Okay, so now what we can do with this is we can say that if we have a frequency, let's say we were to move that electron a certain number of times per second. Let's make it, I'm a flute player too, by the way. And I've played piccolo in marching band, Damon. It's the best instrument you can play in marching band because it weighs almost nothing.
And it's the hardest instrument to play.
It's also hard to play, but everyone can hear it. You can hear all your mistakes too. Okay, so it's 300 million meters per second divided by 1,000 hertz. A hertz is a cycle per second. Well, those cancel. What's 300 million divided by 1,000? Let's see, get rid of that. 1, 2, 3. That would be 300,000 meters. Or about 300 kilometers. The wavelength would be 300 kilometers long, or about 100, what would it be? 180 miles? At the speed of light. So that would be a really long wave. I think we all agree. But now we can take this and we're going to erase this. We're going to write C again. C is equal to F lambda. And we're going to do lambda is equal to C divided by F is 300 million, or 3 times 10 to the 8th. But now we're going to say that our frequency is 100 times 10 to the 6th, which is 100 megahertz, which is 3 times 10 to the 8th, divided by 1 times 10 to the 8th, and those cancel, and our wavelength becomes 3 meters. 100 megahertz, where do we find that frequency?
3 meter.
Where do you listen? Where do you listen to it?
FM channel.
FM radio. That's our car music FM radio station. So what's the wavelength? In free space, 3 meters long, which is about 10 feet. So what that determines is how long your antenna needs to be. It turns out that we're going to get into some electronics, and that will make sense as to why that wavelength is that, and antennas are a certain length. Okay, now what we're going to do is we're going to write our equation again. C is equal to F lambda. Lambda is equal to C divided by F. And instead now we're going to do 300 million. And we're going to do a frequency of 1,000,000,000,000,000,000,000. That be known as a terahertz. Oh, wait, I drew too many zeros. There we go. It's a lot of zeros, right? And now we're just going to that's why we use scientific notation, Shay. All right, now we're just going to start canceling out zeros. The speed, Jude, is the speed the same for every frequency if it's an electromagnetic wave?
No.
What do you think?
Speed of light. No.
Speed of light. It's always the same.
Yep.
Einstein worked for a lot of years on that. Okay, so that's now 3 divided by 10,000, which is 3, 1, 2, 3, 4. That many meters. Or 300 microns. We could go even higher frequency than that. We could make it so that our wavelength was 470 nanometers. What would that be? Come on. I even gave it to you with the color that I drew it in.
It takes us some of us time to work out the equation.
Blue light.
That would be blue. Yeah. What? That would be the color blue. Okay, so what does that mean? What does that mean, everybody?
Ultraviolet light.
Well, what does it mean about electromagnetics in general?
They're a spectrum.
Yeah, and there's no difference between what and what.
Radio waves and visible light.
That's right. What's the only thing that's different about any of these waves?
The wavelength.
The wavelength and the frequency. That's the only thing that differentiates any of these things from any other. That's it. All this stuff, every color that you see, every radio wave that you are able to listen to on the air, they're all the same thing. The only thing that's different is the wavelength. That's it. That's the only difference. So, what makes ultraviolet different from visible light?
Receptors.
Yeah, the receptors. The wave itself is shorter. How about infrared? What makes
Longer.
infrared? It's a longer wave. That's right. So what makes radio waves different from infrared?
Even longer.
Even longer.
Yeah.
Well,
Even
and
longer.
actually, as it turns out, this is very important too. The longer the wavelength, the lower the energy of the photon carrying it. That's actually proportional as well. So, the shorter wavelength means higher energy. So, of all of these, which are the highest energy waves?
X-rays.
X-rays, which makes a lot of sense, right? Because what can X-rays do?
Oh yeah.
They can,
Do anything.
They can, you're right. They can, right. They can see right through your skin. They can see right through your bones.
They pass through different densities, different speeds.
Yep. And what else about X-rays? What happens when an X-ray photon crashes into one of your cells the wrong way?
Damages it.
Yeah, it can
Well,
actually
it
rip
depends.
apart the DNA.
Yeah.
And that's known as ionizing radiation. It actually tears apart the cells by ionizing the atoms inside your cell, which can damage the DNA. Ultraviolet, same thing. Ultraviolet is ionizing radiation. So why does excess sun exposure cause skin cancer?
Ionizing radiation of the
DNA.
UV light damages
Right.
cells.
Right. Ultraviolet light is ionizing. It damages the DNA in cells, causes it to sometimes mutate. When it can mutate, it can turn into skin cancer. Radio waves are at the other end of the spectrum. And as a result of that, we look at radio waves again. Radio waves are long wave or short wave?
Long wave.
Longer waves. They're much longer waves. They have much lower energy. They are non-ionizing. So they can cause heating through vibration, but they don't have enough energy to knock electrons out of their place on a cell, on an atom. So they're non-ionizing. All right, everybody. How about a 5-minute break?
That
Yes.
sounds fantastic.
Okay. Think about
I need
questions.
to go locate coffee.
Yep. Coffee good.
More coffee, better. All right. Take a break. Oh. Let me
All right. Anyone got any questions before we get going again?
Okay, I had, I guess it's kind of like a question, or not sure exactly if it's a comment or question, but you kind of answered it a little bit, but I just need to double check. So, with velocity and frequency, it takes, I'm just going to put it in my terms, it takes more energy for it to reach that high pitch versus going a longer distance because of how much energy it takes to get up that high. That's just in my the way that I can verbalize it. Is that correct?
I don't know that that's necessarily true. I mean, it comes down to.
I mean, from the diagram that you were showing, I'm not saying in every situation. What I'm saying is when you were talking about, again, because I'm not using your terms, I don't know proper terms, but you were explaining how the higher pitch doesn't go the distance.
Well,
and then you said
it's still the velocity is still the same. The velocity is the same, but the wavelength becomes shorter.
Right, that's what I meant. Well, that's what I said I'm using in my terms. Yeah. So that's what I just wanted to check because you answered it earlier. You said that for it to go the distance, it takes just like an X-ray. An X-ray can see through anything. It's going to go all the way through. But with like you said, the velocity is the same, but the frequency is shorter.
The frequency is higher. The wavelength is
higher. Shorter. Okay.
That's,
and then for the other one, it was
we got to make sure we get the terminology right because this is going to show up over and over and over and over.
That's why I said when you were explaining earlier, it takes some of it because this is new to honestly for me. This is new to some of us, so using the terminology, I'm trying to learn it.
Yep.
And that's why I'm glad you're recording, so I can go back and listen and get the terminology because I'm explaining it in my brain and not the correct terminology. So.
Yep.
Okay.
I will share this recording. Yes, velocity in different media are not always the same. That is true. Has anybody ever taken a spoon and stuck it in a glass of water and it looks like it gets bent? And you take the spoon out and it's straight?
Yes.
That is due to different indices of refraction due to different speeds of light in different materials. That's why some crystals look like they bend light. That's why water looks like it bends light. Because it does. That's why a prism does what it does. That's why a prism splits light into different colors.
Hey, Scott.
Yep.
Got a question. Off subject. My camera's not working for some reason, and I've tried everything. It's Don Starling from St. Pete, Florida. So I don't know what's going on.
We can still hear you fine, which is good.
Yeah, but I know I'm not signed up for the test yet, but once I sign up and I do it over the computer, I have to have cameras so they can watch me, correct?
You know, it's Black Friday, and I'll bet you can get a camera pretty cheap today. If that's if it's something that isn't going to work yet.
Well, I think
just use your cell phone to record yourself.
Well, you need two video devices when you go to take the test. You need you need two different devices from two different angles.
It might just need to be updated. Who knows?
Yeah. I actually went out and I haven't gone out on Black Friday morning to go anywhere in probably 15 years, and I realized that my laptop did not have an Ethernet jack because it's a new laptop and it's so thin that it doesn't even have an Ethernet jack. So I had to go out and get a $20 gigabit Ethernet adapter, USB to Ethernet, which is what I'm using today. So.
Is the reason for the two cameras so that you can see that they're not looking in a book or something to get the answers?
Yeah, exactly.
Exactly.
Gotcha.
All right, y'all ready to get going again?
I'm glad you said something about that, Scott, because I don't have one either.
Oh, yep. You need two cameras.
Wow.
You need your computer and your phone. or a phone and a tablet or something. You just need two devices that have
And
cameras.
what if you don't have a phone?
You can borrow a phone or a tablet or something. To take a remote exam, you need two cameras, and that's pretty universal.
Okay.
All right. Other questions before we get going?
Are your diagrams and DIY pictures available as well?
Which ones?
All of them.
Well, I mean, they're like all the stuff
They'll show on the video, right?
all the stuff I'm sketching out. Yeah, they'll be in the video.
Great.
Mm-hmm. All right, let's go. The next thing we're going to do is make sure that I can see myself and do a share, and there we go. Okay. So we have established that this is a wave. We've also established that this is a wave, and that this is a wave. And what is the only thing? What are the things that are different between these waves?
Wavelength.
Wavelength. Yeah.
Big
And
distance.
ooh, we got amplitude.
Amplitude.
Yeah, we got amplitude. And what else? We got frequency
The energy.
and the energy. Yep. And what else?
Wavelength.
Yeah, we got wavelength. I'll write that out. What's another interesting characteristic of waves? What's something that we can change about it? Well, height is amplitude.
Polarization.
We could change polarization, but that's a little more esoteric. We could also do this.
Phase.
That would be phase. Yeah, we can also change when it starts. That would be our delay or our advancement. And so we can change our phase. And what do you think we measure our phase in?
Degrees.
We measure it in degrees, yeah. We can also measure it in waves. We could also do that. Usually it's in degrees, though. So if a wave has a phase difference of 360 degrees, what's it going to look like?
Inverted.
No, it's going to look like this. It's 360
Sorry.
degrees. It's shifted one full wave. Yeah, it's pretty tricky, right? So you don't know when it started. You don't know where it came from. You just know that it exists. Okay, so now we're going to do a little bit of solar terrestrial physics. Okay, so what we're going to draw is this big ball in the sky. What's its name?
Sun.
That's the sun, yeah, okay. And now we're going to draw Earth. These are not to scale, obviously. And Betelgeuse, wouldn't it be more red? Anyway, so here's the Earth. And the Earth is fortunately surrounded by several layers of the atmosphere. So down here we have the troposphere, which is where we live. Above that we have the stratosphere, which is where jets fly. And then we have a couple other layers, but essentially what is most interesting is this thing called the ionosphere. And the ionosphere is the home of ions. And in order to understand what ions are, what we have to do is we have to draw an atom. So we're going to draw an atom, and the atom has a nucleus, which has protons and neutrons in it, and spinning around the atom are electrons. And we're going to take oxygen. Oxygen has 8 electrons, and those electrons are spinning around in different energy levels. But what we're going to do is talk about the fact that these oxygen atoms, and we could also draw nitrogen atoms, they're up there too. There's actually about 4 times as many nitrogen atoms as oxygen. And so we're going to put a bunch of green dots for the nitrogen atoms. Okay, so as you go higher in the atmosphere, what happens to your density of the atmosphere?
Goes down.
It goes down by a lot, yeah. So the density is really, really big down here, which is good because, we can breathe it. As you go up really high, the atmosphere thins out a lot. So atoms might be, a few 100 millimeters apart, maybe a little closer than that. But there's not nearly as many as we have down here. So what happens now is that we have this thing called the sun. What is the sun continuously shooting out at us?
Electromagnetic radiation.
Electromagnetic radiation, yep. And what wavelengths?
A lot of them.
Yeah, like such as?
Ultraviolet.
Yeah, ultraviolet. What else?
Magnetic. Not.
Oh, we have IR. That's heat. Yep. What else?
Cosmic. X-ray.
X-rays. Yeah, sun makes a lot of X-rays. What else? We have a lot of visible. We have a lot of visible light. A lot of visible light. Oh yeah, good one.
What?
We have radio waves. Sun makes a lot of radio waves.
Oh,
Sun is
heck
really
yeah.
noisy. Sun is really radio noisy. So, okay, all of these different things are getting flung at Earth all the time. The sun is continuously making lots and lots of different waves. All right? Visible light, fortunately, it can diffract, but a lot of it makes it down to the surface of the Earth, which is why it is light out during the day. Infrared, what does infrared do? Infrared heats us. Infrared heats everything up. Yeah, so we get a little bit of warmth out of it. Radio waves, well, depending on the frequency, they get down to the surface and they can make it really noisy. How about ultraviolet and X-rays?
I think the X-rays are filtered.
Fortunately, the X-rays are usually filtered by the time they get down to the surface. Because if we were at the surface continually bombarded by X-rays, the Earth would not function as a planet. The planet would be sterilized. Okay, so now, how about ultraviolet?
It gives us the suntan.
Yep, some of it makes it down to the surface, but most of it gets trapped and dissipated before it gets there. Well,
right.
So if a photon of energy, which is a packet of energy, is passing into this atmosphere, which is full of largely oxygen and nitrogen, what ends up happening is that the energy that is being carried by ultraviolet and X-rays, because they are ionizing forms of radiation, when they encounter an atom, that's nitrogen, for instance, or oxygen, what can happen is they have enough energy that they can take, for instance, that oxygen atom, which has 8 protons and 8 electrons. Protons are positive, electrons are negative. They have enough energy to transfer to an electron that they've caused an electron to fly off. What then happens is that you only have 7 electrons. Well, okay, so if you have 8 pluses and 7 minuses, what do you end up with?
A positive ion.
Yeah, you get an ion which has a positive charge. And you also end up with an electron which is floating around free. So you have a positive ion and a negative electron. So if we are down by the surface, this is happening a lot. You have electrons and you have atoms that are ionized, but you have a lot of them. So what will eventually happen, actually usually pretty quickly, what will happen to them when a plus and a minus meet?
They'll join back up.
They'll join back up. Yeah, they'll join back up.
Yep.
So they form quickly, but then they also dissipate pretty quickly.
No,
And
that
they
I
turn
wouldn't
back
like
in,
to see by itself.
they turn back into a neutral atom. But what happens if you're way up in the atmosphere and the density of stuff up there is really, really light? And
It takes
then
a little longer.
it takes longer, yeah. So between times when the electrons and ions rejoin could be a little while. So you end up with a plus and a minus floating around. And you end up with the same thing down low, but again, there's a lot of them. So you have a lot of density down here, but you have very light density up high. And they don't annihilate, they just neutralize each other. They turn back into a neutral atom. So annihilation is something way worse. We're not going there. That's if it found a positron. So what ends up happening is because the sun is what drives all of this, when do you think we will achieve peak ionization of the atmosphere? What time of day?
Midday.
Midday.
Middle of the
Yep,
day.
when the sun is directly overhead. If the sun is off at an angle or it's dark, what will end up happening is that the rate of creation of these things will slow down, and that gives those ions and those electrons more of an opportunity to rejoin, but without being recreated. So what happens is that during the day, you end up with a lot of pluses floating around and a lot of minuses floating around, which occasionally will rejoin with each other and neutralize and turn back into neutral atoms. And then at night, the rate of generation slows down and you have a lot of recombining, and then these go away. Well, so now what we have is a difference between day and night. So what we can now do is we can look at electromagnetic waves of the radio variety. And there are what kinds of waves in radio? There are very long waves. And there are very short waves. Very short waves. These, when they strike different levels of ionization, behave differently. So we're going to take a very, very short wave that is now being flung up at the sky. So here's our very short wave. So what's going to happen when that very short wave gets into the atmosphere?
Right out.
It just punches right on through. The atmosphere looks largely transparent to it. Those, unless there's a lot of ionization up there, it's just going to go straight through, which is really fortunate because what do we use those waves to do?
Talk to space
Radio.
stations or something?
Talk to the space station, control our satellites, receive satellite radio, talk to the Voyager probes, receive data from other space probes. All right, but now let's go to a much longer wavelength. We're going to do a much longer wavelength. Whoops. Didn't mean to do that. Going to draw a much longer wavelength. That will typically get through this high density at the bottom, but then when it gets up to the top, depending on the angle at which it hits, it can be absorbed and effectively refracted back to Earth. Because this layer, these are called the D layer, the E layer, and the F1 and F2 layers, this extends to about 600 miles up. If you look at the geometry of 600 miles up, that wave that you sent up does not come down in the same place, does it? How far might that be?
Depends on the angle, but it could be.
Depends on the angle. This could be 2,000 miles.
And this is also on, you're referencing this sunny days, because this would definitely be different if it was snowing.
No. Where does weather happen?
Very low at the Earth.
Yeah, weather happens like way down here.
Like the D.
So even this is interesting.
Yeah, this is way above the weather. It doesn't matter what's happening with the weather.
Because I'm saying, I only brought that up because when you're talking outside and it's snowing, the sound you can't hear if somebody's talking to you.
That's sound waves. Radio waves are not sound waves.
Okay.
Radio waves are electromagnetic waves. They don't require a medium to pass through.
Wow. Yeah. Okay.
Okay. So this is known as ionospheric propagation because the layer that we're using for this propagation is the ionosphere. It's the air. It's the part of the atmosphere that's full of ions. So that's ionospheric propagation. And propagation is the study of how how waves travel from one place to another. Now, as this wave passes up into the sky, some of it will actually pass through. Another thing is that I could send up a different length wave. We're going to draw a different length wave. Is that a higher frequency or a lower frequency?
Higher.
Higher frequency. That wave might have too high a frequency to be affected by the level of ions. There is a cutoff point which is proportional to how many ions are up there, the ion density. If it goes above that, we're not going to have anything bouncing back down. They're just going to pass straight on through. And so now what we can say is, okay, so which waves, is it possible that maroon wave that we drew at higher frequency might ever be able to be bounced?
Yeah.
Probably not.
Well, no, it's possible.
It's possible you could.
Yeah, it's possible. What would it take for it to happen?
Much more ionization.
We need a lot of ions up there for that maroon wave to bounce. So when do you think we might have conditions that would allow that to happen, considering that the sun is making that happen?
Midday.
Solar storms.
Right, midday, or the sun goes through 11-year cycles. And we are at, well, not solar storms, but solar max during times of peak solar activity, like, thank you, Nathan, right now. So we can actually visualize this. I'm actually going to pull something up so that we can all actually see this.
Wow.
Here we go. This is why this stuff is so darn cool, because I can look at this, not that. Can everybody see that map?
No.
Yes.
Okay, now you see. Okay, so I'm sharing a map.
Okay.
Let me make sure that I. Okay, so there's. Everybody see that map?
Yeah.
Okay.
Well, I'm only me. So I don't know.
Okay, so this is a map of the 10-meter band as viewed from where I live. The 10-meter band has a wavelength of 10 meters long. And, okay, what is interesting about this, to me at least, is the fact that these waves usually require a very, very high level of ionization in order to bounce from one place to another. We'll pick another frequency, which is on the 40-meter band, and what do you notice about it? What do you see, everybody?
Nothing.
Nothing. Why not?
There's nothing. Oh, okay.
So
Because
this is
it's not bouncing off of the atmosphere.
well,
Ionosphere.
yeah, but actually, what ends up happening here is that it's a lower frequency, a longer wavelength. It should be able to be bounced, right? That doesn't. I mean, it would stand to reason that if it works for a higher frequency, it would work for a lower frequency. Let's take a look at another one. Let me make sure I can still see it. And I'm going to make sure it's shared. We're going to pick another one. Where did it go? Shoot. Okay, let's make sure it's there. There we go. Okay, so we're going to pick another frequency. This is a slightly lower frequency, a longer wavelength, and what do you notice about it?
You're getting a lot farther out.
Yeah, you're getting really far out, and it's working they're bouncing into Europe. Okay, so we're going to pick another frequency that's even lower.
Wow.
Wow, that's really working, right? Now we're going to go down a little bit further. What happened?
Nothing.
Disappeared.
Everything's gone.
Dead. That's weird, isn't it? I mean, isn't that weird? That doesn't make sense, right? Okay, so now what we have to do is we have to redraw the Earth, and we have to redraw our atmosphere. And we have our DE and F1 and F2 layers.
We're still looking at your computer
Yep,
screen.
I have to unshare that. Can everybody see that?
Yep.
Okay. Okay, so now we have our D, E, F1, and F2 layers. Well, okay, so we know that, for instance, oops, I didn't want to use that color. We'll use a better color. Hot pink. So we know that at 10 meters, it was working. We know that at 15 meters, it was maybe working even a little bit better. And we know that on 20 meters, it was working pretty well. But then we checked 30 meters. And 30 meters, by this reasoning, should be working really well, right? Except that we were getting nothing. It was
It's
not
skipping
working
above
at
the
all.
Earth.
Actually, it's not even. What's happening to most of it is that this D layer is playing kind of a nasty trick on us. The D layer catches all the remaining X-rays that are headed down toward Earth, and they build up a very heavy, thick layer. But due to the way that the mechanisms of how the D layer actually works, what happens is that this D layer, all the ionization is usually transparent above 10 megahertz. And if we look at our calculations again, C equals F times lambda. And we can say then lambda equals C divided by F is equal to 300 divided by 10 is equal to 30 meters. And we saw on that chart, we saw on that map that the 30-meter band, there was nothing getting through. And on the 40-meter band, there was nothing getting through. What was happening was that those particular wavelengths, because they were longer than that point, are actually getting absorbed by the D layer, and they can't even make it through.
So how will you know when propagation is actually working to where it's actually to your benefit to get out longer on certain bands? How do you, I mean, how does that predict it, or how do you see that? Is there like a resource that says, hey, tomorrow there's going to be this mysterious sunspot and everybody needs to get out there?
You know, that's a good question, because there are there are long-term changes that happen. Well, what do you think would work better for higher frequencies, summer or winter, locally?
Summer.
Summer, yeah. Okay, but that doesn't mean that summer's going to get you more effective communication to where you want. What if you're trying to talk to South America? That'd be better in the winter.
Because it's their summer.
Because it's their summer. That's right. You just have to make it to their summer. You have to make it to that bright spot. But
So
no,
if it's too high frequencies, it won't also get refracted, right? Or
yeah, there's also a limit above which you're not going to be able to do much of anything. And on top of that, you have seasonal stuff, you have daily stuff, night versus day.
Mm-hmm.
You have fluctuations, just statistical fluctuations in what the sun is doing. If the sun happens to spit a bunch of particles at the Earth, called a CME, what can happen is that you can get into a condition where the atmosphere is so jostled that it's basically making RF noise and absorbing lots of signals, and then you can have a radio blackout. You can also have so much radiation coming from the sun due to like an X-ray flare that your D layer builds up to the point where that 10 megahertz transparency window goes up to like 25. So it blocks everything below 25 megahertz. Well, if it blocks everything below 25 megahertz, and the highest you could go, let's say, would be 22 megahertz, and everything below 25 gets blocked, what do you think works?
Nothing.
Nothing. And you get a radio blackout. There's all kinds of stuff that can happen. The predictions are kind of like a general rule of thumb, but what happens within that predicted window can change from day to day or even hour to hour.
so how high of a frequency before you wouldn't be able to reflect off the ionosphere?
Good question. You can actually get a high enough level of ionization up here to reflect or to refract the 6-meter band during really, really big sunspot peaks, which are high levels of solar radiation. You can actually have F2, as it's called, propagation on 6 meters sometimes. It's really rare. I've never experienced it. But a couple of weeks ago, because I was at work, and a lot of people who I know were not at work because they were retired, they were able to work into South America and Europe on 6 meters. And because of the distances, and Japan and Australia, because of the distances, sometimes you get E-layer propagation, but this is typically like 500 miles. You can line up additional jumps. So you could make like a short jump and another short jump and another short jump where it bounces off the ground each time, but you're not going to cover 7,000 miles that way. So that's not how it was working. So they were doing F2 layer 6-meter propagation. That's about the highest you'll see it go, and this is 50 megahertz. Okay, so I'm going to take this opportunity to make a nice circle that you're going to find very helpful. C is equal to F lambda. At least I think you'll find it helpful. So C is measured as 3 times 10 to the 8th. It's 300 million meters per second. We often measure wavelength in meters, almost always, and frequency is in hertz. But usually we measure frequency in megahertz. Well, mega would be millions. So let's say we have a frequency of 20 megahertz. That would be 20 million times lambda. Well, okay, we can factor out this million here and this million here, and they're going to cancel out anyway. So we can take this 300 and just use 300 and use this as megahertz. Because those factors of 6 zeros disappear. So this is the easy formula. 300 is equal to F in megahertz times lambda in meters. And the reason I draw this in a circle is because this allows you to very easily remember what goes where. So let's take the 6 meter band. Okay, well, we know that this is 6 meters because wavelength is 6. Frequency is the one that we don't know, so we're going to cross it out. And what are we left with? 300 divided by 6. Okay, notice there's even a divisor bar there. 300 divided by 6 is
50
megahertz. And if you look at the frequency spectrum charts, you will see that it indeed covers the 6 meter band from 50 to 54 megahertz. The wavelengths are approximate. For instance, we'll call the 15 meter band. The 15 meter band is actually 21 to 21.45 megahertz. Okay, well that's not exact. Colloquially, we call that the 15 meter band. So, but this circle right here is the easiest way to not make a mistake when converting one to the other.
I see that circle used quite a bit in the training I was doing, like, when they're talking about current and when they're talking about R equals I divided by E, and I see that same similar, or I should say the similar
There's
learning.
a reason for that.
Yeah.
Yeah. There's a reason for that. And actually, if you want this times the other one, that works that way too. So 300 is equal to 1 times the other one. And this is a really easy way to remember if you're not great with algebra and dividing things and changing around what equations look like. This keeps you from making mistakes. Okay, so now we're going to talk about what happens above a certain frequency. So what happens above a certain frequency is that things don't really bounce anymore and you start to get into special stuff. So we're going to draw the surface of the Earth again. And now we're going to say that we're going to use a wavelength that's really, really short. And we're going to say this is 2 meters. That is the 2 meter wavelength. Okay. Let's do this. 300 F lambda. Which letter? Which thing do we replace with 2 meters? Everyone. 2 meters is a.
It's a frequency, so it's
a wavelength. 2 meters is a wavelength. So we don't know our frequency again. Let's figure it out. 300 divided by 2 is 150. Which is approximate. Actually, the 2 meter band covers 144 to 148 megahertz. So now let's take a look at how a wavelength like that would actually behave. Well, we can draw the atmosphere again. Let's erase this. So here's our atmosphere. It's our 2 meter wavelength, and there's our wave shooting up toward the sky. So we've got the same things. We've got the D layer, and we've got the E layer, and the F1 and F2. And what can happen is that you can get a really, really high level of ionization in the E layer. This can bounce frequencies up to about 200, 250 megahertz, maybe even a little bit higher sometimes. And what happens is that signal then heads up into that area and it can bounce back down. And that's known as E-skip. for obvious reasons. It bounces off the E layer. This covers usually 500 miles, maybe a little more, but we'll just say 500 miles. But this takes a fairly rare phenomenon to occur, so that's usually not there. So what happens when that's not there? No E-skip. So what happens?
It keeps going up into the upper ionosphere.
Passes right on through. And this propagation we call LOS, which is line of sight, which basically means that if you can see somebody, you can send radio waves to them. It follows essentially the same pattern as light waves would. It follows the same path. So if we were to do this down here on the surface of the Earth, and we were to aim a signal this way, it would get over here, but eventually the Earth would curve away and you would be beyond the line of sight. Now, there is another feature of radio waves, which is that the longer the wavelength, they tend to hug the surface of the Earth a little bit. The Earth doesn't look quite as curved. So the radio horizon, the light horizon, are now different. This might be the radio horizon, and this might be the light horizon, because radio waves have a longer wavelength than light. So you might be able to hear a radio wave a little bit longer than you could see light waves. All right, but basically most waves like this follow line of sight, which is that they go in straight lines. Light likes to travel in straight lines. Radio waves do too, because they're really the same thing. Fiber optics, that's total internal reflection, actually. That's because that's why you can have signals that bounce around and never exit, because they have total internal reflection between the material inside and the material outside. It's completely reflected inside. Okay, so let's see. Other things that can happen, that you can end up with a signal that gets pointed up toward the sky, and you can actually find other ways to bounce this stuff back down. So what do we determine that it takes to bounce these waves, which are really short? What do you need in order for that to happen?
Ionization.
Yeah, okay. So think about some things that can cause ionization in the atmosphere.
Thunderstorms.
Thunderstorms?
Daytime.
Yeah, but thunderstorms aren't really high enough.
Daytime and summertime, like you were saying.
Yeah, but usually you don't get enough. You don't get enough ionization up here to do it.
Then just solar flares, I guess.
Solar flares also usually not enough.
Auroras.
Yes. You could get an aurora. Anything else?
Gonna change during day and nighttime also.
Yeah, but not usually at those frequencies. Oh, we saw meteor showers. Yes, that's a good one. So, here's a meteor shower. So, what happens during an aurora? You get a particle storm, you get radiation storm, and you get ionization. That's why we can see displays of colors. So, you send a signal up into the aurora. It bounces back or down depending on the angle that it's pointing. It gets all distorted because you're essentially looking at a shimmering mirror, and but you can actually copy it.
Hey, Scott, how about Northern Lights?
Well, that's the aurora. So how about that pink streak?
Is that a
You talking about at sunset?
That's a
Or
meteor.
sunrise?
That's a meteor. What happens to a meteor when it hits the atmosphere?
Burns up.
It burns
Burning
up.
and blasting electrons.
Yep, it burns up. It generates a plasma. A plasma is basically electrons and electrons that are getting ripped off of their atoms. So you have a high level of ionization along the trail. If you aim your signal at the trail where the meteor has just left a bright mark, you will get potentially a reflection back down to Earth. So this is called, the first one is called auroral E, and this is called meteor scatter. And both of these work really well on the 6-meter band. Sometimes a little bit higher, but both of them are really, really good on the 6-meter band. How long does a meteor reflect trails for? 15 seconds, maybe? Not very long. Yeah, but during a meteor shower, you might have, a few per minute in the same area, and people aim at meteor showers. They aim at the general direction in which they're coming, and yeah, basically your signal, you have to, so signals that are sent via meteor scatter are typically very, very high speed digital signals, because you don't have long before that trail doesn't work anymore. And it's very likely that if you're making a contact with another person on the ground in another place, you are not using the same meteor trail by that time. Each of you is using one flash to make that signal work.
So, just curious, Scott. I mean, does temperature play anything into this? Because I know, like, if you're looking at the sky in summer, you're looking at the sky in winter, you can see a lot more chemtrails from planes because of the temperature difference. Does temperature play a part in this at all?
Not really. Not in this stuff. But it does play a part in this. So here is an antenna. Right, there's an antenna. Yes, contrails. Yes, condensation. Okay, so let's say that we have a signal that is a very high frequency. It's typically aimed up. Here's our wave, very high frequency. It's aimed up at the sky. So here's our level of the atmosphere. This is where we live. Right? This is the troposphere. And usually these really high frequencies just shoot right through the atmosphere. Has anybody ever been driving down the road on a hot day and it looks like they can see a reflection of the sky in the road?
That's because you can.
It actually is, yes. And what's happening is, if let's say you're looking out onto the road, here's the black road, you are actually seeing the blue sky. And what's happening here is that normally this would not be an issue, but what happens is you get a hot layer of air right here above the road, above which it cools off. And this, because hot air and cold air have different refractive indices, what happens is that the light comes down and can bounce up, and it hits this barrier and it gets caught. And it can bounce around. And if you happen to be looking into it, what you can see is a reflection of the sky. This is known as ducting. Essentially, you have a duct that has now formed in this area. That works with light. But what do we know about radio waves? They're just another color of light, right? A much longer wavelength, but just another color. So, as it turns out, let's say instead of 6 inches above the roadway surface, we're now looking at 5 miles up into the air. We get a temperature inversion where we get cold, hot, cold. Your radio waves, instead of punching through, can actually get trapped and will do this. And how far will they go? What do you think?
Until they attenuate, I guess.
Or until the duct goes away.
300 miles or something like that.
So, or until the duct disappears. Yes, total internal reflection. So essentially what you have is, yeah, they probably do attenuate somewhat in there, but essentially what happens is that they will go until the duct no longer supports them. Well, are they going to go up or are they going to go down? That depends on how the duct is working. But essentially, this can actually work at 2-meter band. It can work at the 70 centimeter band. It can work at 33 centimeters. It can work at 23 centimeters. And I actually, when we used to have actual UHF television, I lived on the 9th floor of a dormitory. And I turned the TV on one Sunday morning in maybe May. And I was able to watch a TV station. I was living in Maryland at the University of Maryland, and I was watching a TV station from Connecticut, which was about 350 miles, on UHF, which is about 800 megahertz or so. Well, let's say 700.
So I have a question. So if the duct, say, has an opening, or I don't know if I'm saying it right, but it's possible that it could just dissipate if you don't have those two layers in effect.
All right, you have to have some way of getting the signal into and out of the duct. Okay. And you can't really predict them. However, there are areas where you can predict ducting. If you are, let's say, in an area that is prone to temperature inversions, you can actually sort of predict that there will be ducting. So we're going to draw this, a very common one. Notice we've got our nice blue water. And we have mountains over here and mountains over here. This is California. And this is Hawaii. People will go up to the top of a mountain in California. Somebody else goes up to the top of a mountain in Hawaii. And over the ocean, because the sun is strong, but the water is cold, you can get a temperature inversion that forms over the entire path from California to Hawaii, which is over 2,000 miles. So, why do you think people go up to the mountaintops?
You're in the high range where the inversion is.
Air center.
That's right.
Yeah.
Because from the ground, you might not be able to get it up into the inversion area, but from on a mountaintop, you can. And you can catch it before it dissipates on the other end. So this kind of ducting typically happens every year. And people will operate, if I'm not mistaken, at up to frequencies of 10 gigahertz, which is microwave. That's like, police radar frequencies, which we have access to, by the way. So that can operate all the way up to like 10 gigahertz. And people are always trying to stretch that further and further and further. And this is known as tropospheric ducting.
What's the height of the ducting? I mean, how far off the Earth is that ducting?
It's wherever the inversion occurs. So it could, and the troposphere is only about 5 miles thick. So it's somewhere in between the ground and that. Remember, this is the part of the atmosphere where we live and breathe.
So all of this is under 5 miles.
Yeah. At least on the ducting side of things. So there's also another mode where we can get that's called troposcatter, where you can have weather, for instance. And the other thing is that at certain, and this is actually important to note. Whoops, I didn't mean to do that. that. Give me a second here. Okay, so we're going to draw the Earth one more time. And now we're going to draw our atmosphere. This is where we live. Here's the troposphere. What can happen in the troposphere that doesn't happen above that?
Weather.
Weather. Yes, we get weather. Weather is typically in the troposphere. You know, some big thunderstorms can come up into the stratosphere. But most weather occurs in the troposphere. Well, so that can be precipitation, right? So precipitation can be in the form of raindrops, snow, etc., clouds, fog. So let's ask this question. Has anyone used a microwave oven in the last 24 hours? I'd be shocked if the answer was no.
Yes.
I'd be shocked if anyone didn't. Okay. So,
leftovers from yesterday.
Yes. So, what a microwave oven is a box that looks like this, right? Everyone agree with that? There's our microwave oven. Here's our door on the microwave. Here's our buttons. Here's a knob and stuff like that. And you stick your food inside and it magically heats up. Okay, so why does it magically heat up? Because what is inside a microwave oven is a 1 kilowatt RF transmitter at 2.45 gigahertz. Okay, why is this number important? Because, as it turns out, we have this really, really popular molecule that we use.
Water.
H2O. The resonant frequency of the water molecule is approximately 2.45 gigahertz. So, if we shake the heck out of a water molecule, motion equals heat. So, if we shake it really hard, what does that do? It makes it get hot. Motion and heat are the same thing. So, by injecting RF energy at 2.45 gigahertz, what we do is we heat up any water that's inside the food. Which is why sometimes you can get hot spots in your food because it has different levels of moisture, etc., etc. Okay, so now, let's say that we have our Wi-Fi. Has anyone ever noticed that their Wi-Fi sucks when they use the microwave? They get dropped. Has anyone ever heard that? Can you guess why?
Either runs at 2.4 or 5 gigahertz.
Right. 5 gigahertz doesn't get affected, but 2.4 gigs, these are awfully close to each other. And if you have any leakage at all, I mean, this could be in the range of milliwatts, then it can wipe out your Wi-Fi at 2.4 gigs. The other thing that can happen is that, let's say that you have a long-range satellite system that's up here. Here's a satellite in space, and here's you, and you have a satellite radio in your car. And it happens to be a rainy day. That never happens in Oregon. Happens to be a rainy day. Anyone notice what can happen to their satellite radio as they're driving down the road?
In and out.
It goes in and out, yes. And the reason that it can go in and out is because here's your car, here's you getting angry in the car because you're sitting and trying to listen to your satellite radio, but you can't hear anything. And the reason being that if this satellite happens to operate at a certain frequency, which is close to the resonant frequency of water, where does all that energy go before it gets down to your car?
Heating the water?
It heats the water, yeah. And if it's if it's a frequency that's close, it can still absorb some of the energy. The other thing is that this doesn't even have to necessarily be on the exact same frequency. Let's say that there is a lot of, instead of that, you're driving through a heavily wooded area with, let me make sure I can bring that out, lots of trees, vegetation.
Leaves are mostly water.
Leaves are mostly water, and they're also flat surfaces in a lot of cases. Flat surfaces can, in addition, reflect energy, and the leaves, they have a lot of water, they can absorb RF energy. So at certain frequencies, you will find that your vegetation will affect your signals. This is typically up in the gigahertz range. It can also, for instance, if you're doing something called ARDEN, which is a digital communication method at very high frequencies. If you're using ARDEN and it uses microwaves, you will find that during the winter you'll have a nice path, and during the summer you won't. It'll disappear because you have lots of leaves during the summer. Okay. So let's see, what else? So that's propagation. Okay. So propagation is how radio waves travel from one place to another. Does anybody have any questions on this so far?
Years and years ago, I guess I started out in citizen band, and we used to use a thing called, or be in contact with other people on different places, and that was called skip. So that's
Sure
what your
is.
propagation is.
Sure is. And the FCC didn't allow skip. Well, you can't tell physics whether it's going to work or not. They tried. They said you can't work anyone by skip. It's like, what are you going to do?
I got a question for you.
Yeah.
Why is it that radio waves will penetrate deciduous trees and woods easier than it penetrates conifer?
I find it's the other way around.
Well,
But
I run a WISP, okay?
Mm-hmm.
You're familiar with the term, I'm assuming, a wireless internet service provider.
Mm-hmm.
And we operate in the, well, haven't used 900 in years, but we still use a little bit of 2.4, 5 gigahertz, 6 gigahertz, and 3.65, some 60 and 80 gigahertz stuff. But we have found that we can penetrate a non-line of sight customer a lot easier going through deciduous woods than we can conifer. It just eats the signal like there's no tomorrow.
That's really weird. And I don't know if maybe pine needles could cause more diffraction.
I think
But
needles do more evapotranspiration. They don't have
I don't
like
know. I
parts
don't
that
know.
open close. So they may be off-gassing more moisture.
No one's ever asked me that before, and I don't have a good answer. I don't have a good answer. But now you mentioned multipath interference, and we're getting to multipath interference also. That's something that we do cover, and that honestly could have something to do with it.
I wonder if it's correlation, like maybe the pine trees are at a higher elevation.
Correlation versus causation.
Yeah.
Yeah, I don't know. That's something I'm gonna have to look up, because I really kind of want to know myself now. I mean, I've spent a lot of time doing antennas and propagation, and just, I mean, that was actually one of the things I did in grad school was antennas and propagation, and that I don't know the answer, and I would really like to know. Okay, so now we're going to cover one more thing, which everybody I'm sure has noticed. Has anyone here ever listened to a car radio at night?
Yes.
Okay.
Unfortunately, yes.
Yes, AM radio.
Especially AM because it travels so far. The
Yeah,
super.
okay, so the question is, why does it travel so far at night, but during the day you can only hear things 30 miles away?
Because of the atmosphere.
What part?
Changes.
What part of it? Remember that D layer is transparent to 10 megahertz?
The D layer goes away at night, right?
Yep. Okay, so where is AM radio?
What is it, 600 megahertz?
Nope, 600 kilohertz.
600 kilohertz.
Which is 0.6 megahertz. Well, that D layer absorbs everything up to 10 megahertz. So AM radio, which has a wavelength of, let's say, 300 meters long, gets up to that layer and it gets absorbed. At night, what happens? That layer disappears, and your signal now, even though your upper layers of ionization are thinning out, those are really low frequencies, they typically work, and you have skip.
I don't know if it's true or not still, but I remember the AM band used to have, or the AM radio stations used to have power settings, and they'd have daytime and nighttime settings. And if you didn't turn it down quite like you're supposed to, you could be shooting your station halfway across the U.S.
They actually also, in addition to that, they also have daytime and nighttime radiation patterns, like different antenna patterns, for that very reason. Not only do you have to change power levels, you actually have to change how your antennas are phased so that your pattern looks different. So that you cover geographic areas and don't cover other ones. Okay, so we're going to do one more thing and we're going to take a break. And this is polarization. So we're looking at a wave, and a wave, we're going to look at the electric field. The electric field can go this way. It can also go this way. It can also go this way. If it's traveling up and down, the electric field can go this way. The electric field follows the path of a sine wave, and it can go, again, into and out of the page. It can go sort of up and down. It can go literally up and down. It can go side to side. Our reference for the electric field is the surface of the Earth. The surface of the Earth is defined as horizontal. I think everyone will agree that that's the horizontal axis. If something has an electric field that is parallel to the surface of the Earth, we call this polarization horizontal. If something has an electric field that oscillates perpendicular to the surface of the Earth, we call this vertical. We can also have a polarization that is sort of random, in which case it might be a couple of different ones. We can have a polarization that over time rotates, so that at the beginning it may be vertical, and then over time it kind of like spirals and goes that way, and then that way, and then that way, and then this way, and this way, and this way, and this way, and it makes it through one full cycle. This is called circular polarization, or elliptical polarization, if it's not equal amplitude in both directions. This is often used for satellite communications because you don't necessarily know which way the satellite is going to be turned at that time. Vertical polarization, the way to make a signal is to build an antenna that is oriented in the same direction as the polarization you want. The electric field is generated by moving electrons up and down a wire, back and forth. And as that happens, it generates an electric field. If it's a vertical wire, it generates a vertical electric field. If it's a horizontal wire, it generates a horizontal electric field. The maximum direction of radiation of energy that is coming off and flying off into space is perpendicular to the wire. So which means that if we look at a horizontal wire, it's going to have a maximum direction of radiation straight up and straight down, and then out of the page and into the page. If we draw a vertical piece of wire, it's going to be that way and that way and that way and that way. This actually forms a donut shape around the wire. This also forms a donut shape around the wire. So why would you ever choose one over the other one?
Omnidirectional, or
yeah, one is omnidirectional and lower to the horizon.
Distance.
Some of them, however, are easier to build than others. So if you're omnidirectional, that means everybody in every direction can hear you. When would you want to do something like this one?
Broadcasting.
Broadcasting, or?
Yeah, simpler.
Receiving.
Or how about on the roof of a car?
Mm-hmm.
If you wanted to talk to a repeater station, which was on a mountaintop, and they had a big tower, would they want to intentionally ignore people in one direction? I don't think so. So a vertical antenna on top of a repeater would make that same donut shape on the horizontal plane. And you can point your car in any direction you want and talk to anybody else. If you had an antenna that was horizontally polarized and actually was preferential to one direction or another, first of all, you'd miss a lot of people. And secondly, as it turns out, if the electric field is oscillating up and down, an antenna that is listening for an electric field that is moving side to side, these will not hear each other. They will completely miss each other. So the polarization of the two signals, the polarization of the two antennas that are trying to talk have to be a good match. They have to match each other. So by convention, it makes a lot of sense that people who are putting an antenna on the roof of their car typically go vertical polarization, especially if it's line of sight. So what we're going to do before we take a break is I'm going to pull this up. These are terms that you're going to have to know. Okay, notice right here, each of these particular named frequency bands is in, each one is a factor of 10 times the previous one. 3 megahertz, 30 megahertz, 300 megahertz. We use our calculations. We see that 3 megahertz is 100 meters, 30 megahertz is 10 meters, 300 megahertz is 1 meter, and 3 gigahertz is 100 millimeters. You don't really have to know the wavelength so much, but you absolutely do have to know the limits for HF, VHF, and UHF. HF stands for high frequency, VHF stands for very high frequency, UHF stands for ultra high frequency. You have to know that 3 to 30 megahertz is the HF band, 30 to 300 is the VHF band, and that's where you start to get into line of sight, and 300 megahertz to 3 gigahertz is the UHF band, and up at those frequencies, oops, I need to make sure that sorry about that. You still see the graphic. Hold on, I have to Okay, there we go. Can you see that?
Yeah.
Everybody. Okay, there we go. Sorry about that. I was looking at it on my screen and it was shared, but apparently you couldn't see it. Okay, so here's the electromagnetic spectrum. 3 to 30 megahertz is the high frequency stuff. That's where most skip takes place. Ionospheric long distance skip. The interesting thing about that is that by the time a signal goes up into the sky and bounces back down, the polarization really doesn't matter. Because once it hits all the ion clouds up in the atmosphere, the polarization gets randomized, and since it's random, it doesn't really matter which one you use. So a vertical antenna can talk to a horizontal antenna just fine. But when you're into line of sight, VHF, 30 to 300 megahertz, it makes a big difference. That your VHF signals, your polarizations typically have to match. And when you're into UHF, 300 megahertz to 3 gigahertz, your skip is essentially gone with the exception of tropospheric ducting or troposcatter. Sometimes you'll get scattering off of clouds and things like that. But that's almost exclusively line of sight, which is also why we use UHF for talking to satellites, because it's line of sight. It largely goes through the atmosphere. All right, one last thing before we take a break is the fact that we can now also look at point to point. So here's point A, and here's point B. How many different ways are there to get from point A to point B?
Infinite.
There's an infinite number of ways to get there, right? Well, the easiest one is a straight line, right? But there might also be one that goes like this. There might be one that goes like this. Might be one that goes like this. And one that goes like that. How many of those could I draw?
Infinite.
I could draw an infinite number. That's right. Okay, now, if I start to look at this and say, okay, I'm going to draw at a certain frequency, how many different wavelengths does any one frequency translate to? If I have one frequency, it translates to exactly one wavelength. So as I'm drawing this signal takes that many wavelengths to get from point A to point B. Well, how about if I go this way?
It's more.
It takes more. Do we know exactly how many more? Sure, if we knew exactly how long it was. But now the question is, if I am at point B, I'm going to draw point B. Here's me at point B. I have a wave that's coming in straight, and it looks like this by the time it gets there. I have another wave that came in at a different angle, and it looks like this. Because the path was, at some point, a half wavelength longer. So this signal got shifted either that way or that way by a half wavelength. What is the sum of those two things?
0.
That is 0. In other words, this is called multipath because there are multiple paths, and this would be also known as destructive interference. Now, by moving a little bit, I could lengthen one path and shorten the other path, and I might find out that instead of that destructive interference, I now have something like this. I'm going to draw me at point B again. Except that now I have a wave that's coming in like this, and due to another path, I find that I have another wave that's coming in. It's a little smaller because it got absorbed a little bit. But what do you notice about those?
They're almost the same.
Yeah, they add together. That would be constructive interference. What is interesting about this is that in physics class, we can do something called an interferometry experiment, and we can see what interference patterns look like. But those are microscopic. I mean, the wavelength of typical light is like 650 nanometers. But we're using a different wavelength of light. We're not using 650 nanometers. We're using like 2 meters long. So what ends up happening now is that instead of these interferences where you have a strong point where they're adding together, and I'll make that in green, these are potential good points, and then you have potential bad points, which are not so good. I'll put those in red. Maybe the distance between these is a half a wavelength. If we are on the 2 meter band, how long is a half of a wavelength, everyone?
1 meter.
1 meter. How big is a meter?
About 3 feet long.
About 3 feet. So you could move 3 feet with your handheld radio and find that you went from a spot where you could hear something to a spot where you couldn't hear anything. And then if you move another 3 feet, you get to a point where you are in a good spot again. The more you are on the air, you will actually hear this and experience this. If you're driving in a car, for instance, and you're trying to have a conversation with somebody and you are moving upward, you will go from good to bad to good to bad to good to bad, and there's nothing you can do about it. And this is known as picket fencing. And that is literally when you're driving, you're rapidly passing from areas of constructive to destructive interference and back and forth. Okay. Everybody ready for a break?
That would only happen if one of the radios was moving then.
Yes. Well, yes and no. What if there's traffic on the highway next to you?
Or you're going past buildings.
Yeah. But if you're stationary, what happens if there's traffic on the highway next to you?
That could interfere. Yeah.
Yeah, because a truck might block the primary signal, or it could reflect the signal and make it follow a different path. You hear all kinds of stuff, and it's macroscopic. You know, it's there, it's real. All right, 5-minute break, everyone. I know I could use one.
It works.
Okay, I'm back. Thank you, Rob.
Scott, I just want to say thank you again. This is Chris or Harry and Connie down here in Florida.
Mhm.
And I've heard many a teacher and instructor, and you're in the top 2%.
Woohoo! Thank you.
I'm sorry that I missed the registration for the 35 for the exam on Sunday, but I'll find something out there.
No, we'll see. I'll talk to JD. Maybe he'll be available today to come and talk.
Yeah.
I'll send him.
But my wife is taking it with me. She just completed deep brain stimulation surgery where they inserted wires because she has a tremor, and she gets it turned on this week. So until then, she can't write. It's shaky, and she has a tremor, but hopefully that'll be eliminated. But she's sitting in with us and taking notes, or I'm taking the notes, and she's reading the manuals. So I thank you. I can't thank you enough.
Cool. You're welcome. And
I second that.
Go ahead. Yeah, I figure that I've spent enough years doing this that I really should teach it.
Yes. Well, like I said, it's the difference between. I mean, I studied this stuff, and I know what the numbers are. Like, say, the 3 to 30 and the 30 to 300. But you help me understand why. You know what I mean? Learning something, knowing the answer is one thing, but knowing how to get it is another, I guess.
Yeah. Well, and that's something that it took me years to come up and figure that stuff out because, I didn't have a class. I just sort of memorized all the answers, and by doing and then going through engineering school, I had many, many moments in engineering school where I said, "Oh, okay, why didn't they just explain that?"
Well, that's the difference between learning and assimilation.
Yeah.
You're teaching us assimilation as to how things work and what goes on so we can have that better understanding.
Well, and like my kids, they didn't really care. And you know what? I'm okay with that. But that's okay.
It's same as somebody, showing you how to do something and you actually doing it yourself. That experience is what's helping you teach this very well.
Well, the other thing is that when I was in engineering school, we had labs and things like that. But the labs were kind of few and far between, and they didn't teach you how to solder. They didn't teach you how to do any of that stuff. So it was more a question of, having a real life laboratory where you could build stuff and actually use it, as opposed to just going through a scripted lab and figuring out why things sometimes worked and sometimes didn't work. And very often it was the things that didn't work that were more interesting. Okay, this should work, but I don't know why it's not. And then you figure out, oh, well, okay, I built this wrong. I needed an RF choke here. I didn't follow the instructions right. Oh, I made it too long. Or worse, I made the antenna too short.
You can fix it if it's long. It's hard to fix it when it's too short.
You can always trim it. Yeah. Yeah, but then the thing is, how do you know if you're just getting numbers that don't really seem to fit either way? How do you know which way it is? Well, no, then that's why there's something called an antenna analyzer, which is essentially a sweep oscillator, either automatic or manually swept, that allows you to see which part of the resonance you're in. Oh yeah, nano VNA. There you go. Well, a VNA, a true VNA can be $10,000-$20,000. A nano VNA is like $50 or $60, maybe $100 now. All right, everybody ready to move to the next section? Okay, so we know what radio waves do, but we don't really know how to make them. So our next thing is how to make them. And in order to do that, we have to start with electronics. So let me just very quickly go through, and I'm going to pop up on the screen the fact that we have this textbook. I'm just going to show you the textbook real quick. And here's our textbook. And it looks like this. Hopefully everybody has this, and if you don't have this, I don't know why you don't have it. I sent them out, but that was part of the packet. And for this part of the class, I go rogue quite a bit. But when we get further into the class, I follow it quite closely. But notice that this actually is part of the reason. The fact that electrical principles come first. I typically do all the waves and derivation of waves first, and then go back to electrical principles. Okay, so I would like to point out that here's the electromagnetic spectrum, and I think it's very good to have this basic viewpoint. All right, so this is the electromagnetic spectrum that contains all the radio waves and all the different colors of light, and this is what there is. This is the whole thing, right? This is the electromagnetic spectrum. It is very important to look at this, though, and understand that in the high frequency band, what is 3 to 30 megahertz? How big is that? Remembering that megahertz translates to a bandwidth. It's physically a resource. So how many megahertz are available in 3 to 30 megahertz?
27.
There's 27 megahertz, exactly. Sending information requires bandwidth. I mean, that's what it is. Information requires bandwidth. Okay, so now let's take a look at the next section up, which is VHF. It's 30 to 300 megahertz, right? How much space is there in that zone?
270.
270. Or 10 times more bandwidth than was on HF. Let's take a look at the UHF. How much bandwidth you got there?
2700.
2700 megahertz. You have 100 times more bandwidth than you had in HF. They fill up the same amount of space on this chart, but they are not the same thing. Let's go up to the next one. Between 3 and 30 gigahertz. How much room is in there?
27 gigahertz.
Or 27,000 megahertz. And considering that any signal that you send, the data rate, the amount of information that you send is largely going to be proportional to how much space it fills in a particular band. Where do you think people want to put all their really high data rate stuff?
Probably a microwave.
In microwaves. It makes a lot of sense to do that, right? Because there's a lot more room. For instance, if we were to send a single analog TV signals, an analog TV signal takes 6 megahertz of bandwidth. You could put it here on HF, but it would fill, let's say, 10 to 16 megahertz, which would render it useless for anybody else. And on top of that, those are radically different frequencies, aren't they? They have different wavelengths. How do you make a single antenna to do that? And the answer is you don't. But how about up here, between 300 megahertz and 3,000 megahertz? What's 6 megahertz there? It's not much. It's pretty small, actually. And the difference between 400 and 406 megahertz, that's pretty much the same antenna. The wavelength is going to change a little bit. So it's all about proportionality, and it's all about figuring out where you're going to put a signal to be able to transmit it. Because without modulation, without putting a signal on your wave, there's absolutely no point to doing any of this. So the next thing I'm going to show you is this beautiful color chart, which I sent everybody. Did anybody in looking through their stuff actually get to look at this?
Yeah, it made my head spin.
Yes.
Okay. But why is this really important? What's so important about this?
So we know who can talk where and use what.
Yeah. And notice 3 megahertz on that one stripe up to 30. This is the high frequency band right in the middle of the screen. That's the high frequency band. We have a ham band, aeronautical mobile. That's typically going to be long distance HF communications for airplanes, ship to shore. Broadcasting, maritime, fixed. This is like land mobile. And there's a lot of people. Notice that these little green slices that we have, those are ham bands. Look how much other stuff there is that we have to share this spectrum with. So why is it that we have a special deal where all these other groups that are using all these valuable frequencies end up paying for it and we don't? It's a good question, right? Well, they want them. The reason that we got them for free was that we were there first and we were experimenting with them, and a lot of the development that came out that was used in radio was developed by us in the process of experimenting. By virtue of the fact that we still provide a valuable service, which is emergency communications, a good training ground for new people. You see this where it says broadcasting TV channels 2 to 4? Where do you think most broadcast engineers got their start?
Us?
Yeah, ham radio. Most of the broadcast engineers, especially the group that's getting old enough to retire now, it's probably 80% hams of all the broadcast engineers. This is where they learned it. You know, and broadcasting is an important thing.
What runs along the bottom of that? You've got different colors along the bottom.
I think that's whether it's government or private.
Okay.
I think. Government. Yeah, here we go. Government exclusive, non-government exclusive, or shared. So that determines who's allocated to. So, but now you look at this band from 30 to 300. That's 270 megahertz. We're getting into a lot of space. But now we look at UHF, 300 to 3,000. Look at all the satellites. Look at let's see, land mobile, aeronautical mobile, FAA is there, radio location, radio navigation satellite. That could be like GPS. This mobile satellites, radio astronomy. And as we get higher and higher in frequency, we get higher and higher bandwidths. And for instance, let's look at 5 gigahertz. Oh, look at that. We've got a ham band up here at 5.6 gigs. We've got a ham band here at 3.3 gigahertz. And we share them with other services. Notice that they're all in there. These are shared services. So if it's shared, who has first priority?
Those that pay.
Well, those that pay or those who are listed as primary users. So one reason that I will say it's important for people to consider joining ARRL is that ARRL, one of the big things that the American Radio Relay League does is that they are the face of amateur radio in front of Congress and in front of the FCC. And when somebody else looks at these frequencies and says, hey, you know, we'd like to put up a new cellular service up here at 10.4 gigahertz. Nice small antennas, and we can integrate satellite with it, and we'll pay you $20 billion to use it. How much are we paying to use it?
Nothing.
Do we like experimenting with it?
Yes.
Of course, right? But if we have no say in the matter, and somebody comes along with a $20 billion check and says, Uncle Sam, we're going to give you this $20 billion check to let us use it, what do you say? So,
No.
yeah,
they're going to try to steal it from us.
Yeah, the ARRL is our voice. So basically, they're the ones who represent us in matters such as this. So that's why I am such a strong proponent of the ARRL, because I enjoy using these frequencies. And if you enjoy using the frequencies, we need to essentially support the defense of our spectrum against much better funded organizations that have much deeper pockets. Yeah.
If you look at that band frequencies, what I notice is that the further you move from top to bottom, the more slices of the pie there were. I mean, of course, when you go from 3 to 30 and 30 to 3 gig, a lot more, out there. But I mean, there's a whole lot of slices in that pie, especially on that last row.
Yes, there are. Absolutely. And there's a lot of services that are using them. I mean, those are carved up a lot of ways, aren't they? So the other thing to bring up is that within our specific sections in that frequency chart, you'll find that, okay, each one of these little sections is a little subset of everything that we see in that big chart. And we follow these things called band plans, which are voluntary guidelines for keeping interference down amongst ourselves. So this chart is kind of like an agreement that defines what we can do where. Legally, really, for the most part, all we have to do is stay within the bounds, stay within our sidelines, and we'll be okay. But beyond that, notice that we have on 15 meters, we have Morse code and digital, and then we have these things in yellow and orange and blue. The higher the license class you go, the more privileges you get. And within that, this says to keep the peace, these are the modes that we can use within those frequencies. So it's all split apart that way. And that's known as band plans. Okay. All right, moving along. Yes.
In ham, are we limited to ERIP limits like we are in fixed wireless?
So that's effective. Well, ERP is effective radiated power.
Yes.
And for the most part, we are not limited EIRP or ERP. We are limited transmitter output power, which is another interesting thing that we're going to get to, which is another reason why. Remember, I said that one of the things that we intend to do by making you guys take a class and making you take an exam is to try to keep you from doing what? Killing yourself, or killing other people. So, if we think about EIRP, that's effective incident radiated power. I'm trying to remember. Isotropic?
Yeah, effective radiated isotropic power.
Okay, so let's say that we have an antenna and we have 5 watt. We have a couple of bands where we have a limit of radiated power. Effective isotropic or effective radiated power, that is the effective amount of power that comes out of the antenna. That means that compared to an isotropic, if we do EIRP, isotropic, which means it's the same amount of power in all directions. Essentially, if we were to pump a total of 5 watts out and we make a sphere around it to catch it all, we would be able to catch 5 watts of RF energy transmitted out of that antenna. So, and that's for any direction. The things that we can do, for instance, they instead measure a transmitter output power. So our transmitter output power could be 1,500 watts. This is actually legal, by the way. We can come up to through a feed line to a horn antenna that is at the center of a microwave dish. Perfectly legal, by the way, with 30 decibels of gain. Okay, who knows what 30 decibels is yet? Anyone?
Times.
1,000 times. Okay, so if we have 1,500 watts of RF energy, which we are legally allowed to put out over here, and we have an antenna with a gain of 30 decibels, which is 1,000 times, what is our effective radiated power in the forward direction?
1.5
megawatts. This is legal. This is why we have to go through the testing process. Because with a technician license, you can do this. That is perfectly okay. If you were to point that at somebody, what would happen?
Fried eggs.
Yeah.
Radiate them.
You could have a seriously injured person. Okay.
Make a light bulb light up.
Yeah, it is scary, isn't it? we can run a lot of power. Okay, so moving on. Someone answer. There we go. Okay. So now we're on to electronics. Does anyone have any more questions before we move on to electronics? Okay, here we go. Moving on to electronics. All right, we're going to start doing electronic stuff. Here's the first thing. This is a battery. A battery is a chemical storage device for storing electrical energy in chemical form. A battery has plates. It has the positive plate and the negative plate. And by convention, current, which is the movement of electrons, comes out of the positive plate and goes around the circuit and flows back into the battery's negative terminal. Does anybody see a problem with this?
Yeah, I thought the electrons flowed from the negative back to the positive.
The original people who designed batteries and figured out what was what got it wrong. The electrons actually come out of the minus.
They flow from the minus to the positive.
They flow from the minus to the positive because electrons are minus. But when batteries were first designed, it wasn't really understood that an electron was a negative because they hadn't discovered electrons yet. Oh, it goes way further than Ben Franklin. Everybody got it wrong. So you're not going to see this again. Electrons flow from the negative terminal to the positive terminal, but current, which is represented by the letter I, and it's measured in amperes, represented by the big letter A. This is from the positive to the negative. By convention, current flows from positive to negative, and we know better because we're 200 years down the line. All right, so by convention, current flows from the positive terminal to the negative terminal. So being that this is stored as a chemical storage, it's energy stored in chemical storage. That's what a battery is. We're literally talking a couple of different chemicals inside the battery that have an electrochemical reaction, which is either reversible or not. If it's reversible, like a lithium-ion battery or a lead-acid car battery, then it's known as rechargeable. If it's a one-time charge, like a lithium metal battery, like a battery backup thing, then it is a primary cell and you can't recharge it. So let's look at a battery. Batteries are DC. This stands for direct current. There's our current. current flows out of the positive, around, back to the negative. DC is direct current, which means that the battery's polarity doesn't change. They always flow in the same, electrons and current always flow in the same direction. They don't ever switch. Now, I could, if I really wanted to, take this battery and do this with it, right? Could I do that? If I were to do that, what would I have to do to all the arrows?
Change them.
Direction.
Change them.
Direction
That's right.
change.
This has another name.
AC.
That would be alternating current because it would change direction. So that would now be AC. And instead of a battery like this, we would typically draw something that looked like this, which is a source that has a sine wave voltage. And why do we typically use a sine wave? Well,
Because it goes positive and negative back and forth.
Yeah. Well, how do we make this voltage? If we think all the way back to the early days, where we have
coil.
Yep. Okay. We have a cliff, and flowing over that cliff, we have a river. A river, and it goes down this way, and we can put something in the path of that to catch water, like this. The water gets caught, and it spins the wheel. And if we can turn this wheel, we can take the shaft of this wheel, and we can connect this to a bunch of magnets, which are now rotating inside a bunch of other magnets, and connected to wires. And that rotary movement is a motor in reverse. This is known as a generator. And it turns out that if you design your generator, what you get out is a waveform that looks like a sine wave. Again, because it's moving around in circles. Okay. In fact, if you have a three-phase generator, you have three signals that come out. They're all 120 degrees out of phase with each other, and that's how you get three-phase power. Okay, so this goes back a lot of years, and that is why we typically have sine wave power. Now, there are also other advantages to it. Edison liked DC. Westinghouse really liked AC. Tesla loved AC. So we're going to, but for the case of this, we're going to draw our DC power source. And we're going to add something called a resistor to it. This is letter R. It's measured in ohms, named after Georg Simon Ohm. Okay, so a battery has a voltage. This is also known as E. It generates something called an EMF, which is electromotive force, or the ability of it to move electrons, electromotive force. It's measured in volts, named after Volta, like Alessandro Volta, another one of those 19th century scientists who worked a lot on electricity. So I guess if you worked a lot on electricity in that time, you get a unit named after you. Okay, so a volt, an electromotive force pushing against a resistor's job is to resist the flow of current. Well, the harder you push, which is the force, the more current you will get to flow across a given resistance. Well, again, this is named using the letter A for amperes, named after Ampere, who was another 19th century scientist who did electrical stuff. And again, this is an ohm, named after Georg Simon Ohm, another 19th century scientist who was studying electricity. These three units, we're going to use the letter E E is electromotive force. E equals I times R. This is Ohm's law. And I guess if you were really at the forefront, you got laws named in your honor. E, I, R. We can see the same thing. Sometimes this is drawn as a triangle. I like it as a circle. So let's say we have a battery that has a voltage of 10 volts and a resistor that is 1 ohm. What is our current? Our current is our current is the thing we don't know. We're left with E divided by R. So I is equal to E divided by R, which is 10 volts divided by 1 ohm. 1 volt per ohm has a name. That's called an amp. And so our total is 10 amps. That is our current flow. Current, again, is the movement of electrons. What's nice here is that we have a piece of wire. The piece of wire is made of metal. It is a conductor. What makes metal a conductor versus other things is the fact that internally,
Electrons.
we have a whole bunch of atoms that are clumped together. Each one of these atoms has electrons surrounding the nucleus, but these farthest out electrons are really loosely held. So if one pushes in, you can get another one that pushes out very easily. So, because it doesn't fight back very hard, it has a very low resistance. This makes it a good conductor. So, some examples of conductors: gold, copper, silver, tin, aluminum, really good conductor. So, a material that doesn't conduct electricity very well is known as an insulator. Typical examples of these are materials that have nuclei and electrons that are really tightly held, so that if one pushes in, it takes a lot of force, a lot of electromotive force, to get another one to push out the other side.
Glass and ceramics.
Glass, ceramics, other ones?
Plastic.
Plastic, other ones?
Wood.
Wood? How about air? Air is a really good one. Mica, like the rock. So, yeah, those are good insulators. So, we typically would use some form of insulator to make our resistors, or something that is not particularly conductive. That makes a pretty good resistor. Very often what we use for that is carbon. Not a particularly good conductor, not a particularly bad conductor either, and we can form it to the shape we want, and it we can make it thinner or fatter, and that determines how much power it can handle and how good of a conductor it really is. For wire, we typically use copper, because copper is not particularly expensive. It's very malleable. It's very forgiving. You can bend it lots of times, hopefully, without breaking it. So, for the sake of argument, looking at this circuit right here, we are going to make a statement that says that for the most part, our resistance of our wire is going to be much, much less than of the resistor. So here's our resistance. We're going to actually have a tiny little bit of resistance in the wire. Wire is not perfect, but this might be 0.001 ohms. So what is 1 plus 0.001? It's 1.001. That's pretty much equal to 1. So we're going to assume that the resistance of the wire is negligible, and for these calculations, they don't exist. When you start to get into the real world, though, they do exist, and they are actually important. Okay, so now Now that we've done a simple Ohm's law calculation, we're going to make that circle again. E-I-R, like that. There's our circle. And we're going to do another calculation. We're going to instead make this carbon resistor 10 ohms. Okay? We have resistance that's known, a voltage that's known. We don't know our current. Once again, we cross that out. I is equal to E divided by R is equal to 10 volts divided by 10 ohms, which is 1 amp. Okay, does anyone know how many electrons make up an amp per second? I believe it's 10 to the 19th electrons. Roughly 10 to the 19th electrons per second is 1 amp. Electrons are really, really tiny. And there are a lot of them. Is it 6.24? Yeah, it's on the order of 10 to the 19th electrons per second flowing across a given point. That is a lot of electrons. But, well, and it's calculated because we know what what an electron volt is, and we know how many volts an electron can carry. What is it? 1.6 times 10 to the minus 19th volts. Or coulombs. It's not a very big charge. Electrons are really, really small, but there are a lot of them. So anyway, an amp is a huge number of electrons. But that's why we use amp. It's just 1 amp. Okay, so now we can go to the next step here. Yes, you are allowed to use a dumb calculator. You can't use a smartwatch or a smartphone. You can use a dumb calculator, like the good old 4-button calculators. So we're going to do E equals I times R again.
What about I build a spreadsheet to do all these calculations in. What about something like that?
You're not allowed to use any. You're not allowed to bring any paper. You can have scratch paper, but that's all. And you can't do anything on a computer. A scientific calculator, I think if you can prove that it doesn't have anything programmed into it, you should be okay. Yep, you'll have to clear it. Okay, so here's Ohm's law again. Now we're going to say how much power is being delivered. Oh, okay. Well, we have E equals IR. We still don't know R, or we still don't know I, sorry. I is equal to E divided by R is 10 volts divided by 10 ohms, which is 1 amp. Okay, so now we are delivering with our 10 volt power supply or battery 1 ampere of current. Ohm also came up with a formula which is P equals I times E. You can draw the circle, P, I, E. And this is a relationship between volts, ohms, and watts. Power is measured in watts, named after James Watt. What's really important to note about power is that a watt is a joule per second. A joule is the fundamental unit of energy that we use, and a watt is the fundamental unit of power that we use. What's really important to note is that a watt, independent of how it is being used, is the same. What I mean by that is a joule is a unit of energy. If somebody is standing on a cliff, for instance, and here's a cliff, and they hold up a rock. That cliff, at rock, has a certain height above the ground. it has potential energy. That potential energy is measured in joules. And it is MGH. Yeah. Which is mass times gravity times height. But it's measured in joules. When it drops and it hits the ground, or it makes it to the point where it just before it hits the ground, it has no potential energy anymore. Its energy, which is now kinetic energy, is 1/2 mv squared. If there was no air resistance, the energy up here is the same as the energy down here. It just changed its form because energy can neither be created nor destroyed. The same way that if I have, for instance, a generator, and I take a crank on the generator, and I hook this up to a handle, and I can somehow support this, and here's the back shaft, and do the support, and I have a hand crank on this generator, and I turn that generator, and I get 50 joules of energy out. If I had a perfectly efficient system, I would have had to put exactly 50 joules of energy in. I have converted mechanical energy into electrical energy. I could have also reversed a chemical reaction and taken this and run it into a battery, plus and minus in my battery, in which case, if I had a perfectly efficient system, I would have put 50 joules of energy into chemical storage. Energy can neither be created, it simply changes form. Whether it's chemical, whether it's heat, whether it's motion, they're all the same. The same thing with power. Power is simply a rate of energy being made or moved or being stored or being consumed out of one thing and being delivered to another. So what's important to note here is that when we start looking at our equation, P equals I times E, we know that if we have our circuit, and here's our circuit, and this is a 10-volt battery and a 10-ohm resistor, and we know that our current is equal to 1 amp. Well, how much power is being delivered by this battery? Well, we don't know the power, P, I, E. Power is equal to I times E is equal to 1 amp times 10 volts is equal to 10 watts. That is, by definition, an amp times a volt is a watt. Because it's neither created nor destroyed, the battery is supplying 10 watts. How much energy, what is the power that is being used by the resistor? How many watts?
10 watts.
It has to be 10 watts. That's right. So, since it's 10 watts, what is the form that the resistor dissipation of that energy takes?
Heat.
It comes off as heat. Resistor gets hot. What could that be used for? We use them all the time. That would be,
toaster oven.
That would be a toaster oven or a space heater. That's a heater. That's exactly right.
Plug.
That's doing it on purpose. Now, we could also say, okay, let's say something goes wrong. Here's something that went wrong. Our circuit was designed to be consuming 10 watts at 1 amp. Well, something happened to this heater, and that used to be 10 ohms, and now it's 2 ohms. Let's go through our calculations again. E equals I times R, and our current is no longer 1 amp, is it? I equals E divided by R is 10 divided by 2 is 5 amps. Okay? So what's our power? Power is equal to I times E equals 5 times 10 is 50 watts. Okay, 50 watts. So what if that resistor, which used to be 10 ohms, but something bad happened to it, suddenly, and it was designed to be dissipating 10 watts, somehow it is suddenly dissipating 50 watts. What will happen to the resistor?
Burn up.
Burn up.
You will let the magic smoke out. It will get really hot. And what happens if that's a heater, or what happens if that's like a cord? Because remember I said that
Catch fire.
You can set your house on fire, exactly. Because it's now dissipating more heat than it was designed to. So if that's true, then you need to do something to protect yourself against the situation. So nominally, this circuit was designed to carry 1 ampere. So if we can do something right here to protect our circuit by putting a black box right there, to say that if for some reason current greater than 1 amp causes it to be destroyed, it will intentionally sacrifice itself and protect the rest of the circuit. Because now this becomes an open circuit, and there is, notice, no way for current to flow around the whole loop, is there? This device is known as a fuse. And that's exactly what fuses do. They sacrifice themselves for the good of the circuit. When you build something, you choose the value of the fuse so that it could be the resistor that fails. It could also be this wire that fails. How come we have circuit breakers in our houses?
Wires and walls don't burn up.
Yeah, exactly. So let's say that we had a load. Anything that uses power is known as a load. And instead of 10 volts, we're going to say that we're going to make it something real. 120 volts AC. And normally it would be 2 ohms, okay? And we can still do Ohm's law on it. And so we're going to do Ohm's law. Ohm's law is E equals I times R. And so that's I is equal to E divided by R is 120 divided by 2 is 60 amps. Okay, well that's a little high, but let's say that we designed our circuit for that. We picked wire that would be okay handling 60 amps, and this thing was okay handling 60 amps, and our power supply, our wall voltage, could handle 60 amps, then we have designed our circuit properly. We'd put in a fuse that would handle 60 amps, and everything would work. Let's say that in that process, because the wire is not perfect, it gets up to a temperature nominally of 100 degrees Fahrenheit, which is fine. It's not going to burn your house down. But let's say that there's a short circuit here, and now the resistance here is, instead of 2 ohms, it is 0.01 ohms. Okay, here's another important note. R total is equal to R1 plus R2. So here's R1 and here's R2. And let's say that this is actually 0.1 ohms. Which is the bigger resistor now? Is it the wire or the short circuit?
Wire.
The wire. So Now we have a big problem because this wire was only designed to handle 60 amps, and we now have a total resistance of 0.11 ohms. So now we have a big problem because by Ohm's law, we are now carrying about 1,200 amps. Do we even need to go through the power calculations on this?
No.
It's bad. This would be really bad. So
Oh,
that
but
wire,
so much fun.
it would, but yeah, I mean it's 100. It's 120 times 1,200. If your supply could do it, that'd be 144,000 watts.
Yep.
Yeah, that's a lot of heat. That's a lot of power to dissipate. So basically, this wire is going to get really hot, and if you're lucky, it will just evaporate. More than likely, in the process of doing that, it'll get really hot, turn white hot, and maybe catch something on fire. This fuse will say that's too much, and it will pop hopefully first, which is why we have fuses. So why should you never replace a fuse with something bigger, a bigger fuse?
Well, the potential to have
Keep
a
that
fire.
field gain up.
Yeah,
Then it won't pop.
yeah, exactly. So when somebody designed that circuit, the assumption is they did it right. Right? It has been working up until that point, and all of a sudden it's not working. The fuse has not changed. The problem must be somewhere else.
The wire turns into a lamp.
Yeah, you don't want that to happen. So that's basic electrical debugging and why you never want to replace a fuse with something that is unexpected, something that's a different value. Because unless you built the circuit and can prove that it is okay, you can't make that assumption. Okay, so another thing we can throw into this circuit, and by the way, the word circuit comes from circle, because essentially we are making a circle. Okay, I have added a switch to the circuit. It's just basically an open contact that when you close it, it completes the circuit. I could also do this if I really wanted to. Let's say each of these represented a light bulb. Well, now I can individually turn on and off my light bulbs. Oops. I didn't draw that quite the way I wanted. So now I can individually turn on and off my light bulbs. There we go. So this is known as the number of contacts that you have is the number of poles, and the number of different ways you can move it is known as throws. So this would be double pole because there's two separate circuits, and you can only throw it one way. You can only close it. So that's a double pole, single throw circuit. I could also do this. And now each of these switches can go to one of two different places. If I drew it right, which I didn't draw it quite right. But that would be a double pull, double throw. So depending on the type of circuit that you want, that can allow you to change the number of different ways you can do it. Okay, so now we're going to add something because resistors are what? Boring. What is the job of a resistor? It is to resist the flow of current. That is really boring because the voltage and the current are exactly proportional. The resistance is just a multiplying factor. So resistors are really boring. So in order to do something more interesting, we're going to add some devices that store energy in different formats. So first one we're going to do is this. That's called a capacitor. and its storage units are farads, named after Michael Faraday. And then there's an inductor. And no, I don't know Henry's first name. I should. This is represented by the letter C. This is represented by the letter L. So, what we have on the first one, is that a capacitor is quite literally just two parallel metal plates separated by a distance. That distance can be filled with another material, such as air or plastic or tantalum. Essentially, inside that space, it could also be, Joseph Henry, thank you. Basically, inside that gap is nothing, or a highly resistive material known as a dielectric. So if we were to hook this up to a battery, what would happen is that negative charges would flow out of this plate and positive charges would flow to it, and the negative charges would flow to this plate. But since there's really no such thing as a positive charge, this is essentially a lack of electrons on the left side and extra electrons on the right side. Well, okay, so what happens at this point? What happens if you get pluses on one side and minuses on the other? If you get a plus and a minus, what do they want to do?
Connect.
They want to connect. But since they are being restrained, what is keeping them from getting together?
The dielectric.
Whatever the dielectric material is between them. But that doesn't mean that they are not applying a force that is trying to pull those things together. They create a force, like a physical force, and the storage is known as an electric field because they're being kept apart. The electric field is generating the force that's trying to pull them together. You're not letting them be pulled together, so you are storing the energy in a capacitor. So let me ask this question. What happens if you then remove the battery and you take the capacitor out?
It stays.
It stays, yeah. Which is why if you have a capacitor and you disconnect it from the circuit that it's in, and this was the plus and this is the minus, and 10 years later, if it's a good capacitor, you go back to it, what's going to happen? You still have a plus and you still have a minus. You can measure the voltage. You could actually use it. That's a very, some capacitors. I actually did this with a capacitor once, and I learned it. You can actually use it for arc welding, even at like 9 volts. It's kind of amazing.
So what's the difference between a capacitor and an inductor?
Well, we're doing the inductor right now. Okay, so a capacitor stores energy in what kind of field?
Electric field.
Okay, so now we're doing an inductor. Okay, so this is a coil. But before we draw the coil, we're going to make this more boring. What's that? That's a piece of wire. Okay, if we have a piece of wire and current is flowing this way, that is going to make, everybody take your right hand, use your thumb as the direction of current. That's going to make a magnetic field that rolls around in the direction of your hand. So it goes into the page and out of the page. Like that. It's going to make loops around it. So that will generate a magnetic field. So what happens at this point is that if you have current, steady state current flow, you will have a steady state magnetic field that is generated. Yes, the X is the arrow tail. Thank you. That is generated and maintained around it. What happens if you suddenly stop the flow?
Magnetic field will dissipate.
It has to. Well, where's it going to go? There's energy stored in it. And unlike a capacitor, there's no such thing as permanent storage of a magnetic field. So it tries to maintain the current. And what will happen is, if you do that, you will end up with, you had, let's say, a plus and a minus that was trying to push current through. It will actually, the magnetic field will say, no, 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 no. This is my plus and this is my minus, and I'm going to try to get the current to flow that way. And until the current flows that way, the voltage will keep going up. Until what happens? Yes, you will see an arc. Very good. You will actually it will actually generate an arc. And this is actually used to our benefit in some cases. It used to be that is how you made a spark for your ignition system in your car. You would basically have a coil that was carrying current, and you would shut off the current, and it would say, oh, nope, nope, and you end up with a spark. If you can contain the spark, you can send it down to your spark plug wire.
That's how you start your grill.
That is how you start your grill. Although sometimes those are piezoelectric, aren't they? Okay, so now, in order to make this more useful, what we do is we coil up the wire like that. So when you do that, what you end up with is a magnetic field that looks like this. Instead of the loops just being around it, they are formed, they look like this, like concentric circles around it. This is actually known as a solenoid, and it's essentially a coil of wire. But it works the same way. So an inductor stores energy in a magnetic field. A capacitor stores energy in an electric field. So notice these are electro and magnetic. Very helpful, right? One of the interesting things about this is that what we're going to do now is we're going to take a different kind of voltage. That's an alternating current, which means that half the time it goes one way, and the other half the time it goes the other way. And believe it or not, it looks like this. So this is the positive direction, and this is the negative direction. So there's 0, plus, and minus. So when it's plus, the current flows this way. And when it's minus, the current flows this way. So it reverses directions. Okay. What do we call how many times it reverses its direction every second? It has a name.
Hertz.
Yeah. It's our frequency. That's right. For our typical 120 volt circuit in the United States, it has a frequency of 60 hertz. Okay. So, interestingly, this 120 volt system peaks at 170 volts and negative 170. If you were to actually measure it, you would see that it goes all the way up to 170 and all the way down to negative 170. But that has a name. That is called 120 volts. That doesn't make a lot of sense, does it?
Wow.
Okay, so the reason that we do this is because what kind of voltage is this?
DC.
That is
Constant.
DC. Okay.
Then you got volt VA
Right.
AC.
So let's say that this voltage was generating a current of 1 amp. Power is equal to I times E is equal to 1 times 120 is 120 watts. All right? So now what we want to do is figure out what kind of AC voltage would make the same average power as that. How much power would it have to be? How many watts?
120.
It'd be 120. Okay. Now, here's where it gets interesting. How much power is made when the voltage is here? When there's 0 volts?
0.
0. P equals I times E. So that's 0. Okay. How about when it's here?
Same.
How about when it's here?
Yeah.
How about when it's here? A little less, right?
Yeah.
How about when it's like right there? Just a little less, right? How about when it's down here?
More.
Nope. Well, it depends. Sorry, I have to draw the line. So let me draw that. Hold on. I'm going to here get rid of that. Okay. Here we go. This is really important. That if we have negative voltage, E equals I times R. If this is negative 120 and this is R, what's our current? It's going to be negative. And then we plug those values into our power equation and we get a negative times a negative, which is
Positive.
Positive. So it does not matter which way the current is flowing. So, and which way the voltage is. So our power is still going to be made. It doesn't matter which way it's going, but this is still not quite enough. So what we end up doing is we have to go bigger at some point to make more power to account for the deficits that we get in those areas. And it turns out that we need to get peak voltage is equal to VDC times 1.414 or square root of 2 VDC, which is about 170 volts peak. So it's about 100.
So you end up with what the average
power
voltage is. Yeah, power.
So you end up with a voltage that is needed to make the same amount of power. And that is known as RMS, or root mean square. And we do that because it turns out that, well, power is really important. I mean, we use power, right? It runs our stuff. So that's why power is chosen as as kind of like the common element there. So another thing that's important about that is that if we have a meter that is a standard cheap meter and you measure AC voltage, it assumes that it's a sine wave. But what if the voltage waveform actually looks like this? That's called a square wave. How much power is being made right there? Full power.
None.
How much power is being made down here at the bottom?
Same power.
Same power. So this waveform, which is a square wave, for the same voltage is going to make a lot more power than the sine wave. And that's why sometimes you spend a little more money and get something called a true RMS reading meter. Okay. All right, so moving back to capacitors and inductors. So now we're going to draw a sine wave generator, and we're going to have a brick wall. Connected to that brick wall are some terminals. And on this side of the wall, we're going to have a mystery device. Okay. So what we do is we take a very high frequency.
Lay down.
We have a very high frequency. And what will happen when we get to the top? We find that current flows. And then we get to the bottom, and we find that current flows that way. And it doesn't seem to have any resistance at all. So what could be back behind that mystery wall?
Diode.
Short circuit. A short circuit doesn't care which way it's going, does it? Right? Doesn't matter. Now, here's where it gets interesting. We're going to take that and we're going to replace it with a capacitor. When it goes positive, when the battery goes positive, we see positives like that. It doesn't quite get to the point of charging up before the power supply switches the other way. Before the power supply switches the other way and starts calling back all the pluses and all the minuses and replaces them again. Because now we have plus and minus like that. So the capacitor will start to charge this way and then this way. But before it can get all the way there, darn it, power supply changes again. And the plus is now here, and the minus is now here. And it calls back all the minuses and replaces them with pluses. As far as the power supply is concerned, what does it think is behind that wall? Considering that it has no response whatsoever.
A short circuit.
A short circuit. Yeah, exactly right. So what ends up happening is that a capacitor at high frequencies looks like a short circuit. Similarly, if I were to hook this up to a DC circuit, a battery, right? So now we have a plain old battery, and we have a capacitor here. The capacitor will, as we saw, charge up. When it's charging up, we get current flow, but then what happens when it's full?
Current stops.
It stops.
It opens up.
It stops. You can't stuff any more into it. Well, if you can't stuff anything else into it, you have no current. No current has a name. It's called an open circuit. So a capacitor for AC looks like a short, and for DC looks like an open. Okay, so now we're going to do the same thing with the inductor, and I'll let somebody guess what's going to happen. What do you think's going to happen?
The opposite.
Yeah, it's going to be the opposite. So here's our battery, and a conductor looking through the wall. There's our inductor, and we have current flow, and we have a magnetic field forming, and the magnetic field is happy. So what's going to happen? The current flows, and does it ever stop?
Nope.
Nope. So an inductor for DC looks like a short. Now, how about if we start flipping it back and forth? What did we say about inductors? They don't like having their magnetic field energy disturbed, do they? So we now have it switching back and forth, plus minus, minus plus, plus minus, minus plus, and this magnetic field is continually having to change direction. Well, it's not very happy about that. So it resists that from happening, and it looks like an open. Those are in the extreme. The amount that it occurs up until that point has a name. Resistance is how something behaves with DC. Impedance is how something behaves with AC. And just to be confusing, they're measured in ohms, both. Resistance is given the letter R. Impedance is given the letter X. And as it turns out on the complex plane, which is an XY plane. This is the resistance axis, and this is the impedance axis. So here we go. Since they're on this complex plane, let's say we have 3 and 4. Does anybody know how long that is by Pythagorean theorem?
5.
That's 5 ohms. But more importantly, it's 5 ohms and it's turned at an angle. This is known as Z. And actually, I should say, not really impedance. This is reactance. And this is known as impedance. Impedance is really how something reacts to AC. And part of it is reactance and the other part is resistance. And what's important to note about this is that that number, that value, changes with frequency. So for a capacitor, this is a capacitor, 1 over 2 pi fc. And for an inductor, 2 pi fl. Okay, so what's the significant thing that you see that we can actually change here?
2 pi.
We can change the f. We can actually change the frequency. If we change the frequency, what happens to the values of x?
They vary.
They vary, which means that if we change our frequency, these things behave differently. And it actually turns out that this one is negative, and this one is positive. There's actually a negative sign in front of the capacitor. And since we can actually draw a circuit that looks like this, right? I think we can draw a circuit that looks like that, right? Is everybody okay with that? It's our circuit. We can draw anything we want. We have negative XL and, negative XC and XL. Is it possible, do you think, because these add together, negative XC plus XL, could we make them so that it's 0?
Yeah, it'd be a filter.
Yeah, it'd be negative XC plus XL. Okay. Well, we have negative 1 over 2 pi FC plus 2 pi FL.
Still? Sorry.
And it turns out that that value of F for which that works is 1 over 2 pi square root of LC. This is actually a really important number. That's a really important equation. You don't have to memorize it, but you use it every day. Has anyone ever listened to a set of speakers in their car? Anyone?
A couple of times.
Yeah.
Okay. There are how many speakers or how many different size speakers are there in your car?
3.
There's 3. There's a tweeter, a mid-range, and a woofer. Some people even have a subwoofer. Well, is there any point making the tweeter, which is teeny, teeny, tiny, make booming bass sounds?
Nope.
Would not work. There's no point in making the subwoofer make teeny, tiny high sounds, really tinny sounds. There's absolutely no point to it. So what we do is we do a capacitor and an inductor. We put them in series, and for one particular combination, this resonant frequency, they cancel each other. They completely cancel, which means that if they completely cancel, what does it look like?
Nothing.
It looks like they magically disappear, and we basically have a short circuit, but only at one exact frequency, which is really profound because now this gives us something that we use all the time. This is really, really important. We have a tuned circuit. If we want to change the tuning of the circuit, we can change the frequency, or we can put those little arrows across it, which means we can alter their values. Either way we do it, that means we can actually tune our circuit to change at different frequencies, to behave differently. So another thing we can do is, let's say we have a resistor. We want to vary this value. This is called a potentiometer. And why might we use something like that? What would that be useful for?
On the radio.
Yeah. So what if we had a speaker, like a loudspeaker?
Volume control.
That would be a volume control. That's right. Because we are allowing, let's say, 0 ohms up to 10,000 ohms. If it's at 10,000 ohms, we're going to get almost no volume out of the speaker. If it's at 0 ohms, we're going to get maximum volume. So this is called a potentiometer. All right, and the last thing we're going to do before lunch, because it's almost lunchtime. Okay. We're going to draw a one-way street. This is known as a diode. Diodes are cool because they only allow current to flow in one direction. It's typically made of silicon, which is a semiconductor. Notice, remember we started with conductors and insulators? Silicon is kind of half and half. And the way that it is made, is that it uses a sandwich, actually a partial sandwich. It's really just like an open face sandwich of silicon with extra pluses on this side and extra minuses on this side, so that in order to get current to flow, you have to have about 0.7 volts over here and 0 volts over here. Once you've exceeded that voltage, the current will be allowed to flow. If you try to push it back the other way until the diode breaks, like actually blows up, it won't work. So what that means is you can only have current flowing in the forward direction. And it's even shaped like that. Notice it's an arrow, just like a one-way street sign. So that's a diode. What's significant about diodes is that this allows us to do some really, really important stuff. This is the other very significant thing that has come out of electronics. Notice that we have this, which is an AC voltage source, which looks like this, right? The voltage goes up and down and up and down and up and down. We use a diode that looks like this. Well, the voltage has to be positive in order for this to work. So, yeah, PWM is much better, but we're not doing that. So let's say that we have this one-way street. Well, this is the positive part, and this is the negative part. It only allows current to flow when the voltage goes positive. So it goes like this. And then during that time, there's nothing, and then it goes like that, and it goes like that, and it goes like that. It's ugly, but this has a name. What would that be called?
Modified sine wave.
That is direct current. We have just converted AC into
rectifier.
We have just converted AC into DC. That's magic, right? So now we can do this, and we can put a capacitor here, which slows down how it allows it to charge and doesn't completely discharge. So now we can make our voltage look like this.
More stable, yeah.
right? So now it's cleaner. And we can also add another thing, which is called a Zener diode, which is kind of like an upside down, backwards looking diode, which says if the voltage gets above, let's say, 5 volts, I'm going to allow extra current to flow to maintain that 5 volts. So this would put a little cap on it like that and take away everything on top. Well, now what do I have?
Better DC.
I have better DC. So I've taken my AC and I've plugged into the wall, and what do I get out? I get a DC current. What do I use DC for?
Charging my phone.
Pretty much everything.
Pretty much everything, because electronics don't like AC. Electronics like DC because it's stable and consistent. We use it for this. Good old phone charger, computer charger, battery charger, etc., etc., etc. All right, so after lunch is transistors. So, considering we want to be done at 3, how long does everyone need for lunch? Is 20 minutes enough?
That's plenty.
Okay, I'll see y'all in 20 minutes.
Perfect.
Sounds good.
Well, I'm sitting back here. If anyone has any questions, you can ask. If not, I'll just eat my almonds.
Hey, Scott, question for you.
Yep.
Well, like a broad kind of question. So we're doing all this radio theory, studying everything needed for the test. When it comes down to the nitty gritty of getting a radio and on the air, any recommendations for how to go about that? A course that says, "Hey, here's your ham radio. Here's how we program. Here's that kind of application of it."
Depends what you want. Depends what you want to do with it. I mean,
Sure.
That's part of the problem is that, you know, it's kind of like a generic RF toolbox. You really have to know what you want to do with it, and that's when you start to deal with, you know, your local people in your local club who've done lots of different things. And I mean, I can recommend all kinds of stuff, but without knowing what you want to do and how you want to use it, it's impossible to do a good job.
So if I'm coming at it from an emergency management, emergency communication perspective, probably a good idea to get with like the local races chapter to see.
Aries, yeah. I would. Where are you?
Vancouver, Washington.
I don't know who that is up there. I can tell you who it is in Oregon, but I can't tell you who it is in Washington.
Yeah, I found their websites and everything, so
okay,
I'll find it.
I know a lot of people up there who do it. I'm trying to think if Dave does. Let me see. WZ8T.
What are your thoughts on multi-band radios versus just getting different radios for each band?
Well, when you say multi-band, how do you mean? I mean, how many different bands are we talking?
Well, what's available, I guess, is the question. How many can I get built into one, and what are the pros and cons of doing so?
Well, I mean, so let me go to a website. Give me a second.
I mean, I see radios that go into, that do several different bands. I just wondered how that works. Separate antennas, or do you get antennas with, multi-elements, or, is there a benefit to just keeping them separate?
Well, okay, so this is here. So let's go like this, FT991. This covers everything from 160 meters up to 70 centimeters in one box.
Right.
And if I'm not mistaken, the back panel has two
antennas, I believe.
Two antenna ports?
I think so, yeah.
I mean, the really nice thing about it is that it's one box. The bad thing about it is that it's only one box.
Right, that's what I was trying to get at. I mean, I was looking at that exact radio. It was one of the ones I was looking at, but I was curious if that was a bad thing to have them blended together, or if it wasn't.
It totally depends on your use case, if you know what I mean. Like this is.
I mean, I don't need simultaneous different bands, I suppose, but
you don't know.
Well,
it depends. It depends.
I could probably use a scanner to monitor.
Yeah, but if you use, I mean, okay, so this is what I use for my home station, right? HF plus 6 meters. It doesn't do 6. It doesn't do 70 centimeters. It doesn't do 2 meters. Now, what the 991 does is it's all bands, all modes. What you give up with that is it as good as something that is a little more dedicated? The receiver's maybe not as good because it's a compromise. Any design is a compromise. It's a question of how much is compromised. So,
right.
But now you combine that with something like this, which is a dual band FM radio. The question is, do you care that it doesn't do single sideband on 2 meters?
Right.
Yeah.
Right.
It really comes down to what you want, and the fact that I have something like this along with the ICOM that's at the base of that's at the core of the core of my HF station, and I combine the two, and I can be operating on HF and also listening to a 2 meter conversation and make and talking to someone.
Right.
Right. Whereas with a radio that's a shack in a box, you can't because you can only do one thing at a time.
Right. But isn't sideband kind of isn't I mean on 2 meters is sideband not a very popular thing then?
It's popular in certain areas where people want to do it. I mean, and
mostly for distance, probably.
Yeah, well, no, I mean it's for a lot of weak signal work, good experimentation, stuff like that.
Right.
You still hear me? Okay.
Yes. I was just thinking that probably when my experience with most everything else is when you try to get an all-in-one, you usually get nothing that's the best of anything.
That's right. Yeah, nothing is superb. Everything is okay, but nothing is great. So,
right.
Again, it's a compromise. You can, what is it? You can do better, faster, or cheaper. You can do 2 of the 3.
Right.
But only 2 of the 3.
2 meters is probably one of the most popular for repeaters and things like that in a common local area, correct?
And 2 meters is going to be kind of like it's your local backbone.
Right. That's mostly what I'm interested in, I would say anyways, but.
Well, I think if that's the case, then maybe you maybe you look at the 991 and, the HF side of things is what you expand into when you figure out that that's really what you want to do. If that happens, it doesn't happen with everyone. Right. I use 2 meters because it's utilitarian. I do HF because it's a blast.
Right.
I mean, it's a blast.
Yeah, I'm not as much interested, like I said, in just making the contacts to say, hey, I talked to here, I talked to there. I mean, I'm more interested in like making a connection more local.
Yeah.
Some repeater work and stuff like that, probably.
Everyone's got their thing. And part of the problem is that a lot of people don't know what their thing is at this point. Unless you try it, you don't know what your thing is. So
right.
So let's see. Just for fun, this was last weekend. Last weekend was the CQ Worldwide CW contest, which I entered as a 5-watt station using wire antennas. And see, there's a ton of Japanese stations. There's the Cayman Islands, Chile, Virgin Islands.
So those were all the contacts you made during that contest.
Yeah.
Yeah.
Finland. Then there was a period where it was just nonstop Europeans, and this is working at 5 watts.
Right.
I mean, like, it was nuts. It was incredible. I'd never seen anything like it. Let's see. I think it was. So yeah, this is in a period of about an hour. So there's Slovakia, Italy, Hungary, Poland, Germany, Czech Republic, Russia, Slovenia, Croatia, Sweden, Corsica, England, Finland, and some Caribbean stuff, and others. Portugal.
That's pretty widely scattered, yeah.
Portugal. Well, you saw that map today. That I don't know. Did you see that map on 10 meters?
Mm-hmm. Yep.
It was amazing. It was absolutely amazing. There's Luxembourg. So, that early on, that was my thing. I had a shortwave receiver when I was 8. And I had a shortwave receiver that when I was 8, and that's what got me into it.
Yeah, I started back when I was young like that too. I had a radio that picked up all the shortwave stuff from overseas and all over the place and stuff. And then, of course, CBs was a big, huge thing in our area for a long time. And, but that's what kind of impresses me is all the like you said, 5 watts, and you talk clear to Finland. You know what I mean? It's back then people used to put the amplifiers on the CBs and stuff to try and get anywhere, and we could get some skip occasionally. That was good.
Right, but it was but it's really a case of application and knowing where to be and when. And when you've only got one band available to you, that's what you get.
Right.
You can't follow the sun and chase the propagation. You want to use the radio when that's SHTF. You're going to be terribly disappointed. Yeah.
Yeah.
But Ann, do you want to know why you're going to be terribly disappointed?
Yeah.
Why?
Why? Because you're not going to have a clue what to do.
Well, that's why I'm training.
It still won't help. You have to know how the whole system's going to work. It's not just going to be you. It's going to be, you have to know how to you're going to have to know how to interoperate with everyone in order to make yourself useful.
Well, I happen to know that my church will have a whole program set up. They're already doing it.
Okay. Well, that's good. If you have a group to work with, then, but if you don't practice, if you do practice, that's great. If you don't practice actively, everyone's gonna be lost. And that's why that's why it's important to understand how everything works together. Not just, what I mean?
That's why I'm trying. That's why I'm training.
Yeah. But I know people who will get a radio and they've done that. They say, okay, well, I know what to do, and they stick it in a drawer, and they charge it once a month, and unless you know how it's going to be used, you're gonna do more harm than good. So it's. You really actually have to be active. And yes, it's fine to, it's fine to be there and ready to operate if stuff goes sideways. That's a big part of what we do out here in Oregon, because we live on a major fault zone and a huge earthquake fault. But if you never practice, that's why we practice.
I'm getting that.
Yeah. That's why we do weekly stuff. That's why we participate in nets. That's why there are statewide emergency drills that are on the air, because the frequency spectrum is big, and different frequencies get used for different things, and if you don't know where to be, you won't know where to be. So, you know what I mean?
Well, I do now because I started training.
Yeah, that's good.
But that's something I plan to continue to do.
That's excellent. That's good.
But you're right. We have frequencies all over the spectrum, but if you don't know where to find people, when an emergency happens, you have to have some sort of a game plan ahead of time.
Yep.
I would think. If you don't, then you're, like you said, you're just gonna be lost out there.
Yeah. And you end up interfering with something else. So.
Right.
Well, I didn't have a clue, but since you started talking, I do have a clue now. So.
Oh, good. Okay, good. So it's time to
It's not gonna make me quit.
No, that's good. No, I don't want anybody to quit. I want everybody to succeed in doing this. But I need just kind of want to emphasize that it's really a whole interoperability thing. MCOM is, when I worry when I see the whole prepper discussion, and the reason I worry about it is because a prepper preps but doesn't really ever practice. You know what I mean?
That's not what I think of I'm in a group that does, actually.
Okay, that's good, because I know a lot of preppers who don't. Like that's how they ended up with a radio, and now I better go figure out how to use it.
Yeah, there's different categories.
Yeah.
My father-in-law actually has a thing that if anybody in the family gets their ham license, he will buy them a radio.
Good. That's very good.
So, one thing for me that's really stuck in is when my father-in-law had a severe allergic reaction and ended up being intubated.
Mm-hmm.
He actually used the Morse code that he learned during his ham training to communicate with his wife.
Yeah.
Because he couldn't talk.
And could she understand him? Or she could look it up?
Yeah, no, they were both extras.
Oh, cool.
So, it's just amazing to see them go back and forth. And then I recently joined the Medical Reserve Corps here in Wisconsin. And we use, obviously, a lot of radio interaction with the local fire department and police and other things. So I figured it was about time.
Cool. I like that. So, okay, so Rob, one question you had about state lines. Radios do not know state lines. Your license permits you to transmit. Radios don't care.
So it's more or less more on just FCC rules rather than state regulation.
Oh, there are no state regulations.
Gotcha.
Yeah, it's a federal service. It's regulated by the FCC. Does ham license cover GMRS, or does one have to have both? You can probably answer that one.
I got a question for you on ham, because this has been a big debate with some of my friends and I. FCC says that all local governments, state governments are supposed to allow us to put up gear, i.e. antenna towers, right?
Yep.
For our
well,
gear.
Yeah.
But the FCC doesn't give any damn regulations. The cities and states are coming back, oh, well, you don't need more than 30 feet. Well, in my terrain, 120 is what I'm looking at putting up.
If you can, are you in a place where you got to get it permitted?
Well, that's the thing. Technically, no, as long as I'm under 150, I don't need a special use permit. But they want to take and say, oh, well, it's not a normal tower, so you need to get it permitted and put it up. And I'm like, wait a minute, it's no different than putting up a TV antenna tower.
If a lot of it depends on, as I say, the AHJ, the authority having jurisdiction. Whatever your city, state, county, whatever the building codes are, that's what you got to do.
Now, I get that, but the FCC also says that they're not supposed to stop us from doing it. They just won't put a height limit on that.
No, there's a height limit of 200 feet, which is an FAA thing.
Right, but that's only if you're within 6 miles of an airport.
Right. No, 200 feet. 200 feet.
Anything over 200 has to be lighted.
Has to have lights, and that gets really expensive.
Yeah, I'm aware. I've put up cell and communication towers all over the place. But
yeah. Nobody I know has a tower more than 199 feet for that very reason.
Oh, yeah, I get it.
Yeah, because then you got to climb it and keep the lights maintained, and that gets expensive. Yeah.
Yeah. But I was looking at my home, putting up a 120, and they're like, "Well, you don't need 120." I'm like, "Yeah, I do."
Well, but again, it comes down to the authority having jurisdiction. If it depends on what the statutes say. If there's we live in Eugene and Lane County and the state of Oregon. The state doesn't care. The city, if you live in the city limits, if you put up anything, you need a permit. In the county, depending on how high it is, you need a permit or not.
I'm in the county, and they're 120 or 150. You need a special variance for anything over 150.
Well, all they can make you do is take it down.
Yeah, no kidding.
It's only 20 cubic yards of concrete.
Oh, yeah.
Yeah, that's not that expensive, right? Good quality.
I just wondered if you would ever see anything, because I know the FCC has very specific regs, and says that they are to accommodate, but then they won't set an actual height on a tower.
No, and they because they're not in that business. They're saying reasonable accommodations, whatever the local jurisdiction says. I mean,
local jurisdictions don't necessarily consider reasonable accommodation.
Well, that's when you get a volunteer council.
Yeah.
So, and by the way, ARRL has volunteer council. It's another reason to join ARRL. Yes, they do. State by state.
No kidding. I was not aware of that.
Yep. All right. Oh, go ahead. So, okay, we're talking about Baofeng radios. Okay, I have a very conflicted existence with Baofeng. Right? Everybody's probably heard of a Baofeng handheld. They're $25, and they are what I call disposable handhelds. I've had my fair share of them. I still have a few. I hand them out to people like candy. A new ham, I'll say, "Here, have a radio," because I don't care. If I'm off hiking and let's say I'm on a cliff and I drop it off the cliff and I never see it again, oh well. It led a good life, But I will say that if you put it on a spectrum analyzer, it may not be clean. They're not going to last that long. There's really the thing that you give up when you get a really cheap radio is you give up front end filtering and transmit filtering and any kind of guarantee that it meets spectral requirements. So basically, Yaesu, ICOM, Malenko, Kenwood. Those are all good. You can guarantee that anything that says Yaesu, ICOM, Malenko, or Kenwood is perfectly fine. Some of the other Chinese ones that are slightly better than Baofeng, they're slightly better than Baofeng. I mean, I know a lot of people who have these Anytone DMR radios, and they're fine. You know, it really comes down to, would you take Radio X and bet the safety of yourself and family on it? And if the answer is no, then that's probably not the radio to get. So, and if the answer is yes, then it's fine. Yaesu, ICOM, Malenko, Kenwood. You'll never go wrong with any of those four. All right, y'all ready to get started again? I try not to be too opinionated on this stuff, but, you know, at some point you are a little bit. So, all right, here we go. All right, bipolar junction transistor, BJT. This is a special device that looks like this internally. It is essentially two diodes back to back. This has the nice little benefit of, this is called the base, this is called the collector, this is called the emitter. And because if you look at this junction right here, this is a 3-terminal machine, essentially. Yes, it's called a bipolar junction transistor. And what this does, this is a diode, which means that you have to get current to flow across this, which means you have to put a plus here and a minus here. When you do that, you get a multiple of that through this larger junction. So this is hooked up to a power supply or a battery, like that. And this is hooked up to a small battery, usually. So essentially what you end up with is you end up with a big copy of something smaller. And if you have a big copy of something small, that is an amplifier. That is one of the basic uses of a transistor. And again, these are transistors. And in particular, this is a bipolar junction transistor. 3 terminals, base, base, collector, and emitter. Okay, so again, this is actually a sandwich of 3 different flavors of silicon. This particular one is an NPN because it looks like, well, there's an N piece, and then there's a P piece, and then there's an N piece. The way to tell them, you can actually build a PNP. You just turn the arrow backwards. The way to remember that this is an NPN is that it's not pointing in. NPN. Okay, the next one. Looks like this. This is a field effect transistor. Notice that bipolar junction that we drew looked like this. It actually had a physical junction. That's why it was called a BJT, bipolar junction. This one is known as a field effect transistor. What does everybody see right here? What does that look like?
Capacitor.
A capacitor, yeah. And how does a capacitor store energy? In an electric field. Okay, that's why it's called a field effect transistor. By putting a voltage instead of a current on this terminal, this is known as the gate. And this is the source. And this is the drain. By putting a voltage on the gate, that basically either opens or closes the channel. This being the channel. By putting a higher voltage there, that opens up the channel more, which means you can get a larger copy of the voltage that's going in right here. If you get a bigger copy of something, that is an amplifier. So, once again, the use of a transistor is often amplification. Another thing we can do with this is, here's another cool device. What's this called again?
Inductor.
An inductor, okay. Inductor makes a magnetic field. So here's the magnetic field. It'll have two poles, north and south. If you've made an electromagnet as a kid to pick up, using a nail to pick up paper clips, that's essentially what this is. Okay, so here's our inductor, and that generates a magnetic field, part of which comes out through the top. So up here, I'll have a contact, and then I'll have another contact, which has a magnetic component to it. This has a name. This is called a relay. It's an electrically operated switch. So what happens is you energize the coil. This is magnetic. It pulls this down and completes the circuit. That's known as a relay. Okay, another thing about our transistors is that we're going to draw our field of our bipolar junction transistor again. So our base, our collector, and emitter. So there is something called a transfer function. The transfer function is output versus input. So for a given input, we get a certain output. So here's the output, and here's the input. So the way that this works, ideally, you would have a linear function. So you would have an exact multiplication of your input giving you an exact output. That would be a perfect example of a linear amplifier. We want to make an exact but bigger copy of what went in. That would be a linear amplifier. Unfortunately, this does not usually happen. And what we end up with is something that looks like this. You have to get the input up to a certain point to get it to do anything. And then it goes like this for a while, but then when you get to its peak, it can't do anything more no matter what you do. So this device, this transistor, and all transistors really, all amplifying circuits, they really have three states of operation. One is called the cutoff, which means it's off. Another one is called saturation, which means that when the input gets up really high, you can't get anything more out of it no matter how you try. But in between, we have this thing called the linear section. If you're building an amplifier, this is where you operate, because you get a proportional increase of the output for a given increase in the input. So if we're building an amplifier, we want to operate in this linear range. If we are building a switch, such as a computer, the computer uses ones and zeros. Well, I can't think of a better way to represent a 1 or a 0 than either totally turning it off or totally slamming it on. So this is how we use a transistor in a computer. So this is completely nonlinear. That's why we use it. It's designed to either be way off or way on, because if it's something in between, that's neither here nor there. And computers are digital. They're either ones or zeros, which is exactly what you want. Okay, let's see. Another device. Was there a question before I went on? No? Okay. All right, so now another thing we can do. This is actually a really, really good one. Okay, what is that, everyone?
Inductor.
Okay, what's this?
An inductor.
Another inductor. Okay. What do inductors make? What flows around them? What kind of field?
Magnetic fields.
Okay, a magnetic field. So here's our magnetic field. Our magnetic fields look like this. Okay, but now, what if I were to take that coil that the inductor is made of and wrap it around this set of iron plates in a shape that looks like a core?
You made a transformer.
Made the beginning of a transformer, yeah. So what happens is that a core, this is usually iron or steel. These are known as ferromagnetic materials, which means they respond very favorably to magnetic fields. And what happens is that instead of these magnetic fields forming like there, the magnetic fields will actually be encouraged by the materials that we used to largely form in the core. So we're basically directing the magnetic field through the core. Well, okay, if a current makes a magnetic field, what does a magnetic field make? A current. Right, so a current makes a magnetic field, and that makes another current on the other side. If I have a voltage that's driving it, what comes out on the other side? Another voltage. Yep. Okay, so what this is used for is, notice that I drew those inductors slightly differently. This one, let's say, has 3 turns, and this side has 5 turns. If I were to put 50 volts AC on this side, I would get 30 volts AC over here. That my voltages are proportional to the number of turns that the wire is wrapped around the core. And these are remarkably efficient. These could be 98% efficient, 99% efficient. And what this allows us to do is a couple of really cool things. Number one,
his hands down by his side with his hands in front of him. We kind of really tried to throw him up in case he ran into him. I don't think he was trying to maliciously take him out to the point where it's a personal foul. So.
Okay. So here's number one. So we're going to have 100 turns over here. And we're going to have 10 turns over here. And we're going to say that we want 120 volts AC. Now, it's important to note that transformers don't work on DC. They only work on AC. So if we have 10 turns here and 100 turns here, how much voltage will we see on this other side?
1200.
1,200 volts. Okay. If we instead had 1,000 turns over here, what would we see on the other side? 12,000 volts. What on earth could we use that for? Why would anybody do that?
Transmitting electricity across long distances.
Power transmission. Yes. Okay. Why?
Less loss.
Less loss. Okay. To understand this, let's say that we are sending 1 amp over here. Power is equal to, come on, somebody tell me Ohm's law.
I times E.
I times E. Yep. I times E equals 1 times 12,000 is 12 kW, 12,000 watts. Okay, so by that same calculation, I know that if I have 12 kW over here, I have to have 12 kW over here. P equals I times E is equal to question mark times 120 is equal to 12,000. I is 100 amps. Okay. Now, what I'm going to do is hook this up to a piece of wire which has a resistance of 0.1 ohms. I have 1 amp going through it. I can figure out what my power loss is. I can figure out what my voltage loss is. But I could also say that, let's say I didn't do this and I had 100 amps going through it, if I didn't have that transformer there. E equals I times R equals 1 times 1 times 0.1 is 1/10 of a volt. All right, so I'm supposed to have 12,000 volts. I lose 1/10 of a volt, no big deal. On the other side, I have E equals I times R is equal to 100 times 0.1 is equal to 10 volts. I'm supposed to have 120 volts. Now I only have 110. And by doing that, what ends up happening is I start to lose my voltage. Well, if I'm losing voltage, that means I'm also probably losing power. And P is equal to I times E. P is equal to I times E, and that would be 100 times 10 volts, because I'm losing 10 volts, is 1,000 watts. Where's that 1,000 watts coming out? In my wire. What happens to my wire?
Getting hot.
Yeah, but what if that wire is up on a 200-foot transmission tower? What's going to happen to it?
Will it start humming?
It's going to sag and melt.
It's going to burn.
Yeah, it's going to burn up. Okay, on this side, on the 12,000 volt side, no big deal. P is equal to I times E is equal to 1 amp times 1/10 of a volt is 1/10 of a watt. I will take that. Burning up 1/10 of a watt, I will definitely take that. And that's why we transform voltages from one to another. Because resistance in combination with a lot of current makes a lot of losses. So that's why we do it that way. Not to mention the fact, how much bigger of a piece of wire does it take to carry 100 amps versus 1 amp?
About the size of your have to have a lot lower gauge wire.
A lot smaller wire. Yeah, exactly. Which is a lot cheaper. And it's a lot lighter, which means you can actually put it up on that 200-foot tower. Okay. Other things. Series. We have R1 and R2. Our current has to go through both of them in series, like watching a television series. So the R total is R1 plus R2. These two resistors, and everywhere in the circuit, experiences the same current. Well, if these resistors are different, power is equal to EI, and E equals I times R, then power is equal to I squared R. And what you're going to end up with is that if your resistors are different, then your powers are going to be different. If you have two light bulbs, what does that mean? If your powers are going to be different?
Twice the wattage.
Well, maybe. It also means they might not be the same brightness. You know, small changes in manufacturing might mean they're a little different. They're going to be different brightnesses. That's not what I want. The other thing is, what happens if you have a let's say one of these bulbs decides to blow out and you end up with an open circuit. What do you get?
No light.
You have Christmas tree lights. Your whole strand goes out. So that's why we don't typically wire things that way, at least things that matter. Instead, we wire them like this. These lines are parallel because they're parallel to each other. And R1 and R2, we have our voltage here, and we have our voltage here. Both of them experience the same voltage, which means that their currents are proportional to the resistors. But what it also means is that if we pull one out, what happens to the other one?
Still works.
It still works. This is how our houses are wired. This is why we wire our houses that way. And in this particular case, if I draw R2 back here, R total is equal to R1, R2 over R1 plus R2. And we could go through Ohm's law and calculate that, but you may or probably won't need that actually, unless you get to the general class exam. I believe it's on that. Okay. Let's see. Math for electronics. Oh, yeah. Okay, there we go. Now this is where it gets a little bit mathematical, and I'm really sorry about this, but I do have to teach it. Okay. 300. What's another way to write this? 3 times 100. That's another way to write this. 3 times 10 times 10. Well, we see there are two 10s. By convention, 10 times something, 10 times itself, a number of times, is an exponent. So this is 10 to the second power. So this would be 3 times 10 to the second power. If I were to, for instance, write 0.06, that would be 6 times 1 over 100. It's equal to 6 times 1 over 10 times 6 times 1 over 10. Each time I get a 1/10, by convention, that's 10 to the minus 1 power. So that would be that. And then I can add the exponents because the bases are the same. The exponents are both -1. That would be 6 times 10 to the minus 2. So let's say then I got that times that. Well, the easiest way to do it then would be 3 times 10 to the second times 6 times 10 to the minus second. Well, there's 10 to the something and 10 to the something. Since they're multiplied, I can add the exponents. And 2 times minus 2 and minus 2 is 0. So I get 18 times 10 to the 0. 10 to the 0 is 1. It's just 18. So this is exponential shorthand math. We use exponents all over the place. And here's why we use exponents, because they actually make our lives considerably easier. Here is why. We have something called, again, an exponent. And then we also have the opposite or inverse of that called a logarithm. Okay, so we have an exponent and a logarithm. An exponent, something that's exponential, is 10 to the second power. That means we have 10 times 10. The logarithm is the inverse of that. So we can say that the logarithm of 100 is the number to which 10 would be raised to get that value. So 10, in order to get 100, 10 would have to be raised to the second power. So the logarithm of base 10 of 100 is 2. Log base 10 of 1,000 would basically mean we have to raise 10 to the something power to get 1,000. And that would be 3. The reason that we do this is because this makes a very convenient way of showing really big and really small numbers. For instance, we have, and by the way, this is largely the same way that earthquakes are measured in strength. So let's say we have this number. And we want to know, again, just like we did this morning, that was just this morning, the interesting parts of this number are 1, 4, 3, and the number of zeros. So we're going to go to the next step and say the 1, 4, 3 is important, and we have 1, 2, 3, 4 zeros. We can take out 100 times and put it in over here. We get 1.43 times 10 to the 6th. If that is, for instance, a joules in joules, that would be 1.43 megajoules. That is, I think, a lot easier than dealing with that, especially if we have an extra 3 digits on the end, in which case this would become just 10 to the 9th, 10 to the 7th there, and that would be just become gigajoules. It just changes the letter. The next thing that we do with this is we can say, okay, so let's go with that 1.43 times 10 to the 9th. Well, I don't really feel like carrying even that. Let's take the log of that and see if we can make this useful. So, what is the log, base 10, of 10 to the 9th power? Well, that would mean we have to raise 10 to the something power to get 10 to the 9th. Obviously, that's 9. So, we still have the 1.43 out front, etc. We could, sorry, it's not out front. It would have to be in here somewhere. But at least we have an order of magnitude. So it's like maybe 9.1 or something like that. Well, if we're rating an earthquake, that is a lot more useful than that. We use the same thing to figure out gain and loss, looking at how big something is compared to something else. So, for instance, let's say that we have a black box, and this is a magic black box. We don't care what's in it. It has a big letter X on it. And we have a value of something that is 72 units big going into it. And we have on the outside coming out of it 7,200 times. We have a value of 7,200. So what can you look at that X box, X box. You look at that box labeled X, and what is that box doing? What's its function?
It's a transformer or amplifier.
Yeah, and what's it doing? It's making something 100 times bigger,
larger.
Right? It's just making something, whatever that is, 100 times bigger. Okay, so this is 100 times. So if we were to take a ratio of the output compared to the input, that would be 100 times. Whatever we put in comes out 100 times bigger. If we put in a value of 6, what would we expect to get out the other side?
600.
600, exactly. So that's a multiply by 100 box. Okay, so now we can try to characterize what that box is doing in terms of this ratio. Well, okay, it's 100 times. But let's say that that was 72 and this was okay. That's a lot of zeros, isn't it? That's a lot of zeros. Why would we do that? Those zeros don't really help us at all, right? We could say that's, let's see, 1, 2, 3, 4, 5, 6, 7, 8. We could say that's 10 to the 8th power. That's a little bit better. But let's say that we had 2 of these boxes in a row. So what we're going to do is we're going to say, okay, well, we have this 10 to the 8th, and we're going to take the log, and we're going to make this a logarithmic function and see what the rough order of magnitude is. How many powers of 10 it would have to be to get that. Log base 10 of 10 to the 8th is 8. Okay, this has a name. That would be called a gain. Is named after Alexander Graham Bell. That gain would be known as 8 bells. That means that the gain, how much bigger it got, was 10 to the 8th power because it's logarithmic. But as it turns out, people didn't really want to deal with those because then you could have decimal points, and so they created something which was 10 times bigger. So they multiplied the thing, they multiplied out front by a power by 10. 10 log base 10 of 10 to the 8th. But then they had to change the name. So that became 80 decibels. Anyone ever heard of a decibel?
Mm-hmm.
Okay. That is a measurement of how big something is compared to something else. That is what a decibel is. It's a measurement of a ratio in logarithmic terms. What's cool about decibels is that in reality, what does that actually mean? What does the number of decibels refer to? It's
gain?
No, it refers to that exponent. And that's all it does. It just refers to the exponent. And so if we have let's say 10 to the 8th times 10 to the 6th, by rules of exponents, that is 10 to the 14th. If we were to take our 80 decibels and find that the 6th one was 60 decibels, we would just add them together and get 140 decibels. Because we're really just dealing with the exponents. What that allows us to do is have a little more implicit accuracy because we have another value of 10 in there. And we have tenths in there, and it allows us to actually have a real value that we can look at and kind of make sense of. It also works the other way. For instance, let's say we have 600 going into our magic box. This one's a Y box. And we have 0.6 coming out. How many times bigger is 0.6 than 600? It's not bigger. It's not bigger. 0.6 divided by 600 is 1 over 1,000. This is a 1/1000th box. So we could actually write this as 1 times 10 to the minus 3rd power. Well, okay. So let's say that we have 10 to the minus 3rd. And now we want to take log base 10 of that. Well, that would be minus 3. But now we want to multiply out front by 10. And we get minus 30 decibels. And guess what? We have 1/1000th is minus 30 dB. And in fact, that is correct. And what's cool now is we're going to take those 2 boxes that we had. Here's our input, and then we have an 80 dB box, and then we had a minus 30 dB box. What's our output?
50.
Yeah, it's 50 dB. Whatever the input is, that whole thing makes it 50 dB bigger, which it turns out is 100,000 times. So this now can be combined into 50 dB. Because it's bigger, we call it gain. If it was smaller, we'd call it a loss. And what we can now do with this is we can build big systems. So let's say we have a radio which has a transmit power of 1 milliwatt, and we have an amplifier which is 30 dB of gain. And we have a cable which has minus 5 dB because it's cable and it's lossy. And then we have an antenna up here which has 7 dB of gain. How much signal's coming out compared to this milliwatt? So we have plus 30.
34.
Minus 5 plus 7. We get plus 32 dB.
32, yeah.
Yep. So compared to a milliwatt, we can actually have a term for this. It's plus 32 dBm. We can now take this signal, which is transmitted across the airwaves and has a loss of, let's say, minus 99 dB, being received by another antenna with 0 dB of gain, minus 10 dB in the cable, and that gets down into a receiver. How much signal gets there? So we're at plus 32 dBm, and then minus 99, minus 0, or plus 0, and minus 10 is 32, that's negative 67, negative 77 dBm compared to that milliwatt. Okay, so at this point right here, we have negative 77 dBm. If our receiver has a sensitivity of anything negative 90 dBm or better, do we hear anything, yes or no?
Yes.
Yes, because minus 77 is a bigger number than minus 90. This is how we do this is how we do radio-based systems. This is how we determine whether or not you're going to be able to hear something. If it turns out that you're not going to hear it, what can you do?
You can either raise the power or
you can raise the power. What else?
Or increase the sensitivity by going negative.
You can increase the sensitivity. Could you replace this really, really bad cable?
Yeah, I'd replace that other antenna.
You could replace that. You could replace that cable. What else can you do?
Could you amplify?
Yeah, you could increase your get a bigger antenna, put it up higher. These are all practical. These are all practical solutions that just come out of the mouth.
The signal?
Yeah, depends on where it is. Yeah, you put an amplifier here. You could put an amplifier right at the transmitter antenna. There's all kinds of things you can do. And this is where the mathematics becomes real. The mathematics describes the reality that we're seeing.
So when you hear of a preamp,
yep,
basically increases your sensitivity of your radio.
Yes, but it depends where it is. That's a very important question, and I'm going to show that because you brought it up. Make you wish you hadn't, right?
I've got a question for you on this when you get done with the answer to that.
Okay. All right, so let's say I've got a signal coming in of negative 120 dBm. Right, I have 0 dB gain in the antenna, and I have minus 10 dB in the cable. How much signal gets here?
Minus 130.
Minus 130 dBm. Okay. What if my receiver sensitivity is minus 122?
You won't hear it.
I hear nothing. Okay. So what if I put a preamplifier right here with a gain of plus 10 dB? Whoops.
You'll just barely hear it.
No. Think about it. Plus 10 dB with a sensitivity of minus 125. The signal right here is minus 130.
Yeah, you won't hear it.
I will not get any improvement by putting it there. What I'll get is louder noise. However, what if I put that same box and I stuck it up here? The sensitivity of minus 125 with a plus 10 dB. What happens if I do that? Then this preamplifier can hear the signal. It boosts it up to minus 110 right here. Down here, I lose another 10. It's minus 120, but 120 is now bigger than minus 122, and I can hear it. And that's why it's important to determine where you're going to put your preamp. It makes a difference. And this is RF system design. Isn't that cool?
I have a question for you
Uh-huh.
on that. Why is it every 3 dB of gain on an antenna doubles your effective power?
Okay. Here we go. Here's the next one. Okay. We all understand that 10 dB is 10 times. Agreed? Because 10 to the first power is 10. So that is one important thing to memorize. 10 decibels is 10 times. The other one is 3 dB is approximately equal to 2 times. Not equal to, but approximately equal to. And the reason that is because 10 log base 10 of 2 is approximately equal to 0.3 times 10 is equal to 3. Because 10 to the 0.3 power is approximately equal to 2. It comes out of the logarithm. For practical purposes, the two things that you have to memorize, and that's good that you brought that up because I was going to bring that up. For practical purposes, these are the only two things you have to remember with regard to decibels.
Thank you.
Doubling your power is the same as adding 3 dB. Cutting your power in half is negative 3 dB. Going up by a factor of 10 is 10 dB. Cutting by a factor of 10 is negative 10 dB. And then you just add the decibels. Yep. So, as Rob just pointed out, let's say that I have, we're going to figure this out. We're going to do it mathematically. We're going to have a Z box here. We've used X and Y. Now we're going to have Z. And we experimentally find that we get, for every 1 watt that we put in, we get 926 watts out. Okay. The things that we know that 2x is 3 dB. And 10 times is 10 dB. And we know that if we can convert them into decibels, all we have to do is add together. So starting at 1, how would we get up to 926? And this is not going to be exact, but it'll get us close. What's the first thing you would multiply by, a 2 or a 10? Somebody call it out.
10.
Okay, so let's go from 1 to 10. Okay, next step.
Another 10.
Okay, that'd be 100. Next step.
I'd go another, yeah. There you go.
2. Right, 2.
I'd go with 2. Okay, so 200. Next step.
Another 2.
That's 400. Next step.
1 more 2.
Yeah, that's 800. Okay, that's getting us pretty close. All right, so this is 10 times. 10 times. This is 2 times. This is 2 times. This is 2 times. So we're going to just add the decibels. So this is 10, 10, 3, 3, 3, and up to 926. Okay, maybe that's like a 0.3, like a 0.3, maybe. We're just going to sort of take a guess. Add them together, 10, 20, 23, 26, 29.3. Okay, so we're going to take a calculator, and we're just going to see how well we did. Okay, open up the calculator. I'm going to share the calculator. Okay, here we go. We're going to go to, hopefully, scientific. Okay. Going to go 926 and log. And times 10. 29.6. And what did we say? 29.3?
Close.
Close enough. And that's a big part of what it is that we do. You know, it's close enough. Another thing that we do is when we're building a system like this, is we're going to take our basic antenna, which we're doing antennas right now. Here's a dipole antenna. And in fact, this is a half-wave dipole antenna. This is the basic fundamental antenna in radio, any form of radio. Okay, so we have cut this so that it is how long? How many waves?
Half a wavelength each side.
Nope, it's a quarter wave on each side. This is a half-wave dipole.
All right.
So it's a half wavelength long. Okay, which means if we're going to draw a half wavelength, what does it look like? It starts at 0, goes up, maximizes, comes down, and ends up at 0. Does everybody agree that's a half wave?
Mm-hmm.
Okay. As it turns out, this is a thought experiment. What is the current that you would find at the end of a piece of wire?
0.
It would have to be 0. It can be nothing but 0, because once you get to the end, you can't have any more electrons flowing that way. So if we were to draw the current on this, where the current has to look like this, like the curve, it would have to look like this. Okay, so that is why a half-wave dipole is a perfect starting point for every antenna, because it's a half wavelength long. It matches the boundary conditions, which say that our current has to be 0 at the ends. So this is the beginning of virtually every antenna system. Half-wave dipoles are great for this reason. Okay, if we then take this antenna, and before we do that, let's say, what is the purpose of an antenna? What are the two purposes of an antenna?
Transmit and receive signals.
Yeah. So we move electrons, and when an antenna contains electrons that can move in a constrained fashion, that allows us to direct our electric and magnetic fields in a way that we desire. In a half-wave antenna, it looks like this donut around it. If we were to take that antenna and make it vertical, remember from this morning, that was only a few hours ago, it makes a donut horizontal. Notice that it's always perpendicular to it. So for a half-wave antenna, if it's a horizontal antenna, our electric field goes this way. If it's a vertical antenna, our electric field goes this way. That defines the polarization of the antenna. Remember we talked about that? Okay. Now, we have a half-wave dipole. That has a radiation pattern that is perpendicular to the antenna, perpendicular to the wire itself. So that would also be up and down and forward and backward. Okay, the reason that we do this is because it's easy, it's cheap, and it works. You can basically take a piece of wire, cut it in half, solder it to a piece of coaxial cable, throw it up in a tree, and it works just fine. Now, what we can say about a dipole is that a dipole with reference to a dipole has this much gain. Zero decibels compared to a dipole. In other words, compared to itself, it doesn't do a very good job. It's no better than itself. But what we can do with this dipole is we can make it, so here's our halfway of dipole right there, but we can put other stuff around it that can sort of operate in conjunction with it. We can put another one, just a straight piece of wire that is 6% longer. And we can put another one here that is 6% shorter. And we feed our dipole in the center like we did. And this has a name. This is a Yagi antenna. This is in particular a 3-element Yagi antenna. And compared to a dipole, which has a gain of 0 dB, this might have a gain of 6 dB in the forward direction. So, what is the point of doing this? The point of doing this is that if we have a box that is a 6 dB box, you can't even read that. If we have a box that is a 6 dB box and we have 1 watt going in, how much will we have coming out? Well, 6 dB is 3 dB plus 3 dB, and every time we have 3 dB, that's how many times?
Doubles.
Yep. It's 4 times. So our 1 watt looks like what?
4 watts.
4 watts.
Yep. We didn't make it out of nothing. What we did is we took some of that energy that would normally have been going backwards, and using this element, which is called a reflector, and this element, which is called a director, what we've done is we have redirected some of the reverse-facing energy back in the forward direction, so that instead of transmitting with an equivalent of 1 watt out the front and in all directions, we might have virtually nothing coming out the back or the sides, and we have the equivalent of 4 watts going out of the front. So in other words, we borrowed from other directions to emphasize the direction that we wanted. This antenna is known as a beam. It has directionality. If we were to look at its radiation pattern, we would see that here's the antenna. It would have a front lobe that looks like this and a back lobe that looks like that. And normally its pattern would look like this. So what we've done, again, is we've borrowed some of all this energy that's going up in all these different directions and redirected it forward to make it a more useful antenna.
Okay, so question.
Yep.
Because Yagi is more focused
Mm-hmm.
with a smaller beam width,
Yep.
why is it that they do not put out more dB gain than something like a 30 dB dish radome with a radome on it?
Well, because you still have power going off vertically and horizontally. It still spreads in both directions.
Okay. So you're just losing the power of your side lobes, that you're not losing so much on a dish, is what you're saying.
Oh, no, because a dish, if you think about it, if you look at how a dish is built, right, a dish, a parabolic dish, the whole idea behind a parabolic dish is that, you know, if here's your feed point and you have stuff coming out in this direction, and because it's a parabola, it takes every direction and redirects it to straight ahead. I mean,
so that's why you've got a wider beam width than a Yagi.
Oh, yeah.
And more power.
Right.
Okay.
Right. A Yagi is, if you think about it, it's kind of an open device. This is a closed device. This is a mathematical construct, which is a parabola, this is why we build telescopes with a parabolic mirror, because it takes all the energy and focuses it all in one very tightly focused beam straight ahead. All the rays are parallel then. Whereas with a Yagi, I mean, if I were to draw the antenna pattern for this, it would look, it would look like this. Here's the dish, and it would look like this, and nothing out the back. It would all be in the forward direction. It would have a very, very narrow 3 dB beam width.
Can I go back and ask a question about the omnidirectional half wave?
Sure.
How come they make 5/8 waves?
Good question. Okay, so let's talk about the quarter wave, because that's really where we start with that. So a half wave antenna is perfect because of what? Because it meets the boundary conditions of the ends. Now, what you can do with this, if you really wanted to, you could change the point where you break it and hook it up to your cable so that it's right there. You could feed it over here. You could feed it almost all the way at the end. What that does is it changes your feed point impedance. Remember what impedance is? The way that something behaves when it's exposed to AC.
Reactance in an AC signal.
That's right. So what we've basically done is we've altered our impedance, but we haven't altered how the thing behaves. What we can do is we can take this and we can split it in half. So, but there's still a half of an antenna that is now missing. Agreed?
Sure, right there. Yeah.
Yeah, it's missing. This is a quarter wave long. If we were to draw a quarter wave antenna and try to stuff energy into it, it would get like this, and it was supposed to be peaking here, except that the requirement is that it has to be 0. So we never get anywhere near peak current, and current is what launches our energy into the world. So that short antenna would really suck. That's why we don't do that. What we do instead is, if we're doing a vertical antenna, we can cheat it in a way by making an antenna that's a quarter wavelength long. What happens is the requirement is that this is actually a reflected imaginary remaining quarter wave down below. Does that make any sense?
Yeah. Yep.
Okay. And you can actually get a good example of this by taking, let's say, a mirror and shining a light along the mirror. If I were to put another mirror, oh, here we go. Let's see if I can get it to work. There we go. I'm going to unshare my screen here, if I can. Okay, here we go. Can everybody see me okay?
Yep.
Okay, how many lights do you see?
1.
Okay. How about now? If I didn't tell you there was a reflective surface down there, how many lights would you see?
2.
Okay, so if you don't know that there's a reflective surface down there, maybe it's there and maybe it's not. So when we create a quarter wave vertical antenna, essentially what we're doing is, if we can create a surface that, here's a quarter wave up above that is carrying current, and this is an electrically reflective surface, does it really matter if it's reflective, if it's really there or not, just so long as you see it that way? If you can't tell the difference, what do they say? If it walks like a duck and it quacks like a duck, then
must be a duck.
Must be a duck. So essentially what we have is a quarter wave above the ground and a fake quarter wave below the surface, which is not really there, but because it's a reflective surface, when I say reflective, it is a conductive surface that is essentially capacitively coupled through the base of the antenna so that the bottom part looks like it's there. And all these currents are induced in the bottom part, the fake part of the antenna, which is the roof of your car, to make it appear as though there's really something there. The only thing that changes is that a half-wave antenna has a radiation pattern that looks like a donut. This has essentially a half a donut because the bottom part isn't really there.
So we're just tricking it.
Yeah. The other thing that changes is that the impedance of the top antenna, if it's the dipole, if it's fed in the middle, this is approximately 72 ohms. This is 36 ohms. Because the bottom part isn't real, so it's only really half an antenna. No, you don't need a balun. I mean, you can use a balun, but you don't really need one. A balun just forces there to be equal voltages and currents on the two sides. So, anyway, that is a quarter wave vertical. The reason we use those is because it has no directionality other than, horizontal. Which is great if you're driving a car because you don't really care if the person that you're talking to is here or here. You can hear everybody, all directions equally well. So now let's talk about a 5/8 wave. A quarter wave. Actually, let's do this real quick. We're going to figure out what what an antenna is supposed to be lengthwise. So we're going to use a quarter wave at 144 megahertz. Okay, does everybody remember from way long ago this morning? You remember this formula?
Yep.
Okay, so if we plug in 144 megahertz for the frequency, we find that lambda is equal to about 2.05 meters. Well, it's a quarter wave, so we want a quarter of that. So that's 0.51 meters. And because it exists in the real world, we actually shorten it by about 5%. So it ends up being about 0.48 meters, which is about 19 inches. So this quarter wave antenna, this is how we calculate antennas. This is why higher frequencies make shorter antennas and lower frequencies make longer antennas. This is a 19-inch long antenna. This is what I have on the roof of my house, sitting above 4 radials on the roof of my house. I built it for less than $5. Okay, so now let's make this 5/8 wave antenna. How many wavelengths long is it, you think? I hope it's 5/8, yeah, okay. So we start at the end. The only requirement is that a current at the top is 0. Essentially, we now have this. Right, there's our current. But at the bottom, we have another 1/8 wave, which looks about like that. So what this basically does is it has an elevated half-wave antenna. It makes an elevated half-wave antenna, which, because it's not squished by the roof of the car, has a lower angle of radiation and a little more gain. Does that make sense?
Yeah. I've seen those, though, on, like, home antennas.
Yeah.
Not so much on a car.
No, you can do it.
Anything squishing the bottom.
Yeah. Well, no, you don't have anything squishing the bottom. What it is it's a 5/8 wave antenna.
Yeah.
So this is a half wave above it, and this is an 1/8 of a wave below this point. The feed point is still down here at the bottom.
Okay.
But in other words, it's being fed away from the 0 point. The 0 point is an 1/8 of a wave above that, and it's got an entire radiating half wave above it. This part above it, that half wave up top, is actually a really efficient antenna. That's exactly what you want.
Scott, can you say what you said again about the angle of something? I didn't really catch that or
Yeah,
understand it.
if you take this dipole, or sorry, take this quarter wave, right? Your radiation is affected by the fact that it's sitting on top of the roof. Right? It's literally on top of the roof.
Right.
If you have the 5/8 wave antenna, what you end up with is that you have a full-size dipole, a half-wave dipole, separated from the roof.
Right.
By 1/8 of a wave. So that the roof does not have as much of an impact on the pattern. It doesn't reflect stuff back up as much.
Okay.
And what it allows you to do, and in fact, this actually, because if it's connected to the roof, this would actually look like this. And there would be another reflected half wave down below, which makes it look even bigger.
Right. Okay.
So it's a more effective antenna, but because it's 5/8 of a wave long, it's like 42 inches or something. Depending on how big of a car you have and whether or not you pull into a garage frequently, that might make a difference.
Right.
Again,
okay.
Practical things, right? It's all about building stuff for real. Okay, so so now what we're going to talk about is the fact that you can do other things with antennas. Antennas are the best thing because they don't have to cost a lot, and they work really, really well, even if you don't spend a lot of money to build it. You can make okay. So let's say that I have a radio. These are my options: a radio, amplifier, and an antenna. Where do I put most of my funds and effort?
Well, you probably put most of your funds because there's most expensive in a radio.
Yep. Okay. Where do I put most of my effort?
In your antenna.
Yeah. Amplifier is the very last thing you would ever need, because an antenna, a better antenna, works better on receive and transmit. You make a huge improvement with your antenna. And how about this one? We haven't covered this one yet. We haven't done feed line yet.
So are you talking the type of coax?
Mm-hmm. Okay, so what we're doing right now is something called loading. You can make an antenna physically shorter while retaining its electrical length.
Oh, yeah, with the coil.
You can put a coil in it. Now, that adds inductance, so somewhere you might actually want to put a capacitor in there with it to balance out and cancel out the reactance, because it's only really used for one frequency. But what this does is it all comes back to drawing currents. What you'll find is that I always go back to drawing current. So let's say I have an antenna that is a quarter wave long, and it's sitting on top of my handheld radio. But it's a quarter wave long, but most of that is coiled up. What's the current up top? Everyone?
Zero.
Zero. Okay. If I start drawing my curve, I start to come down to here, and it ends up going like this. It looks pretty distorted, right? And a lot of what happens in here is that because it snakes back and forth, is that this part of the signal gets canceled out. It puts out very little actual power. So that's like nothing. So this antenna, which would normally have a current profile that looks like this, if it was long enough, looks like that. Why would I ever want to do that? And this is called a rubber duck, by the way.
Just for short distances.
Yeah, short distances. And what else? Like I have on my handheld, I have a 15.5-inch antenna, which has a very short loading coil. The one that came with it is 7 inches long, and I can go out and buy one that's all coiled up and is 3 inches long. Why would I want to do that?
Convenience.
Convenience, so I don't jab myself in the armpit. So it's easier to store, it's easier to pack. But every time I shorten the antenna, what do I do to my efficiency?
Lower it.
Yep. Now, if I go through the calculations and say, okay, well, here's my handheld, and this has this much power, 5 watts, which is about 36 dBm. And my antenna is a minus 10 dB. And here's the path to the repeater, minus 110 dB. And here's the repeater, which has a 0 dB gain antenna. And here's the cable, which is minus 3 dB. Okay, let's go through it. So I get plus 36, minus 10, minus 110, plus 0, minus 3 is, let's see, that's 123. So that would be minus 87. Minus 87?
Oh, yeah, you're right.
Okay, if the repeater sensitivity on the receiver has a sensitivity of minus 110 dBm, guess what? It doesn't matter that I have a crappy antenna on it. It works just fine. But if I go out into the field, this path loss might be minus 140 dBm because now I'm looking through trees and over treetops and stuff like that. And now I'm 30 dB worse, minus 117. And all of a sudden, I can't be heard anymore. So if I had a better antenna, then I might be able to pop up on the other side and somebody can hear me. This is why it's important to understand feed lines and antennas and decibels and stuff like that. Okay, let's see. Now we're into feed lines. There are 2 main kinds of lines. There's parallel line, and there's something that looks like this. Everybody's seen this. Coax cable. Okay, so coaxial cable is literally a center conductor and a shield, which is usually a braid on the outside. Inside a plastic or some kind of rubber jacket. Parallel line is typically 2 plastic-coated parallel wires separated by a specific distance. Because of how feed lines are laid out, they have something called a characteristic impedance. So a characteristic impedance is a measurement of how that particular cable responds to a given signal coming in. So the way that this looks is a piece of wire is an inductor, there's a capacitor, and there's a capacitor. And every long piece of cable can be broken up into sections that look like this, that just repeat ad infinitum. So this is a section. Each one of these is a section. This, because it has an inductor and a capacitor, it turns out it has frequency independent impedance. That is known as its characteristic impedance. Some cables, for instance, coaxial cable, is very often 50 ohms. Some of it is 75 ohms. You can have 92 ohms, I believe. You can have lots of other different things. What is a capacitor in reality? And what makes a capacitor?
Two plates.
That stores energy.
Yeah, two electrical things, two metal things that are spaced by a distance. Look at a piece of coaxial cable. What do you have? You have two metal things that are a distance apart. What do you have up here in top? You have two metal things that are spaced by a distance apart. What do you have along the piece of wire or along the outside of a piece of coax? It's a piece of wire that has inductance. It's a piece of wire. It may not be very much, but it has some. So this might have an impedance of 300 ohms. That's known as twin lead. There's 450 ohms. There's 600 ohms. Okay. Oops, someone's dog is going crazy. So we have characteristic impedance, which is an impedance that allows power to be transferred from one place to another. So this is where it actually starts to come into play. We have our transmitter. We have our feed line. This goes up to an antenna. The way that transmitters are built is you have a characteristic impedance that is provided to the feed line. This is typically 50 ohms for coaxial cable. Most transmitters have an output impedance of 50 ohms. Ideally, you have 50 ohm coaxial cable right here. When you have a match between those two impedances, you get maximum power transfer. So if I have 100 watts going out, I have 100 watts going into this piece of feed line. Then, if I have an antenna that is 50 ohms impedance, I have 50 ohms in my characteristic impedance for my cable, because that's how cable is measured. I have perfect power transfer, so I have 100 watts going out, and I have 100 watts going out of the antenna into the world. This is a perfect real-world situation, which never really happens. Because what is coaxial cable made from? What is it actually made out of?
Copper wire. Copper wire.
Yeah, it's made of copper. Copper has some resistance. Anytime you have resistance, what does that mean? That means you're going to burn up some power as heat. Energy that is not dissipated as RF energy comes out of the system as heat. It has no choice. So your coax is going to get a little warm, and it's going to dissipate some of its energy as heat. Which cable do you think has more resistance? A cable that's this big or a cable that's this big?
Wrong.
Yeah, the tiny one's going to have a lot more resistance. So which one is going to have it be a lossier cable?
Smaller.
The tiny one. So this big one might have a loss of minus 1 dB per 100 feet. That's how they're usually measured. And it's 50 ohms because of how it's proportioned internally. This could also be 50 ohms impedance, but could have a loss of minus 8 dB per 100 feet.
So is that like the difference between RG8 and RG58?
Yep.
Okay.
That's exactly right. And on top of that, it is frequency dependent. The higher the frequency, the higher the loss gets with any cable. So this cable up top might be fine for 1.8 megahertz. But if you start to get anything higher than that, you might start to have really bad losses. The bigger cable down at the bottom might be really good all the way up to 440 megahertz. And how do you think those losses are measured, everyone?
dB.
Decibels. You notice everything comes back to decibels? Everything comes back to decibels. So I'm going to pull, if I can find it, I have my favorite site. Anyway, while I'm busy looking for that, what's important to note here is that the other thing that can really get in your way is, let's say you have a transmitter, and what's its impedance usually? How many ohms?
50.
Okay. I hook this up to a cable which has a characteristic impedance of 100 ohms.
Ooh.
What happens?
You have a lot of loss.
I do. And what happens? I don't get maximum power transfer. I get some power transfer, but I also get some power reflected back into my transmitter. What happens at that point?
Heats up?
Yeah, it heats up the transmitter. It also can generate higher voltage in the transmitter, which can blow up your transmitter. So the reason that we do something about that at that point is that we don't want to destroy our transistors that are inside our radio. So this condition is known as standing wave ratio. It's a measure of how well matched something is to something else. If this standing wave ratio goes up, what will happen is that your transmitter will intentionally and unbeknownst to you reduce its power output so that its voltages across the transistors don't get so high that they cause all the smoke to be let out, and then you have to go buy a new power amplifier. So what we can do with this is, because we have a high standing wave ratio right there, is we can put a magic box.
Out of curiosity, are
Yes.
you using LMR, or are you actually for your cable, or are you using regular RG?
I personally have just RG8X. If I were to put in a new antenna here at the house, like for VHF, UHF, I'd use LMR 400.
I was going to say, because the loss attenuation on LMR is a lot less than RG.
It is, yeah, because it's a higher quality cable. Okay. Oh, good. I found that page that I was looking for. Okay. So now we have a magic box. We'll call it MB for magic box. This is 50 ohms. And then we have our magic box. What our magic box does is that it allows all the power to go out into the cable. How can that be? What kind of magic box is that? I mean, it's got to be magic, right? That would be an impedance matching transformer. That's a very good choice. Okay, so we're going to take a look at an impedance matching transformer. Here we go. MFJ949E internals. I'm going to try to find a nice picture. Oh, will you look at that? Oh, that's a beautiful picture. Okay. And now I'm actually going to share, so you can actually see it. Okay, here we go. Can everybody see that beautiful photo right there on my screen? On the right side?
Yes.
Okay, what does everybody see in that beautiful photo? What are the things that you see?
Oil.
Okay, a coil is what? Another name for a coil. Yep, that's a frequency sensitive device. What are the other devices that you see?
Potentiometer?
Yeah, there's a pot in there somewhere. But what are the other big ones just to the left of the coil?
Well, the other one looks like a variable capacitors.
There's two of them.
Mm-hmm.
Yeah. Okay. That is a pair of variable capacitors. Those are attached to a front knob that looks like those. Those are tuning knobs, and those are connected to those variable capacitors. And why would you use a variable capacitor?
To adjust the impedance.
Yeah, to adjust the impedance. It's a magic box. So what it does is it looks like this. Oops. Here we go. Okay, and what do those little arrows mean?
Adjustable.
Adjustable, yeah. Okay, so here's our in, and here's our out. And we have an impedance that is presented by the capacitor, which is minus J over 2 pi FC. And we have one here that's minus J over 2 pi FC. And we have an inductor, which is J 2 pi FL. And then we have our magic output impedance. So what we really have is an antenna up here.
Scott.
I need to share it, don't I?
Yeah.
Okay, here we go.
There we go.
Okay. I thought it would take over. So essentially what we have is an impedance here of the antenna, and we have an impedance for this capacitor. These are in series with each other. So here's number capacitor 2 and antenna 1. So capacitor 2 and antenna are in series. Because if you think about it, outside, if that signal never comes back, it's kind of the same as ground. Ground is our zero reference point. So the outside world is kind of like ground. So this capacitor, C2, is in series with the antenna, which is then in parallel with the inductor, which is then in series with this other capacitor. And by adjusting those, you can make this mystery impedance out here at the antenna look like 50 ohms. So if your transmitter sees 50 ohms, what's it going to do?
Be happy.
It's going to be really happy. It's going to dump full power out into it. Now, what happens beyond that? What does happen beyond that? This is a really important important thing to think about. If your power goes out beyond that, what's going to happen to it? It's going to get out into the real world, right? It leaves the antenna tuner and goes out through a piece of cable. And then it goes out into an antenna. What can you say about the cable? I don't know. What can you say about the actual antenna impedance? I don't really know. So it might be that you have, out in the real world, you have this piece of cable which has, 10 dB of loss going out to an antenna. This is 50 ohms. The antenna is 200 ohms. Is that a good match or not?
Definitely not.
Definitely not. And what you're going to have is like 75% of your power bouncing back. But it's going to get back to this tuner, and it's going to go back out because it has nowhere else to go. So it's going to get back out to here, and then 75% of that is going to get bounced back. And then it's going to go up again. So what do you really have? You have a little bit of power coming out, and you have a lot of power doing what?
Making everything hot.
Just echoing back and forth in your cable. And if your cable is lossy, you're just going to heat the cable, which is what happens. You just heat up your cable. But your transmitter is perfectly happy. At least your transmitter's happy and you didn't blow anything up. So what's the real solution here?
That's what we're waiting for.
Yeah. Well,
Match
look
your
at
antenna to your transmitter.
Yeah, that's right. Fix your antenna because your antenna is a terrible match. So figure out what's wrong with the antenna and go fix it. Right? You can make it work. And you also have some pretty bad coax here. So you could improve on both of those things. And let me just...
And how do we measure all these in the radio world?
You can do a good number of different things. You can use an antenna analyzer. That's my favorite tool, honestly. Antenna analyzers, a nano VNA You can measure reflected power, and you can measure power, going out and coming back, directional watt meter. Because you can't use a plain old voltmeter or ohm meter, because it's measuring something at RF frequencies, and RF frequencies are very different than DC. They behave totally differently. Let's see, coaxial cable. I just want to
Getting your specs on your cabling helps also. Like most
Yeah.
of your good cables will have a spec sheet.
Yep, and that is actually what I'm attempting to pull up right now. Coaxial cable. Come on. There we go. That's a good chart. Okay, so notice we start here on the left-hand side with our frequency, and notice it goes from 1 megahertz up to 1 gigahertz. They're all, for the most part, the ones at least we're looking at are 50 ohm cables with a couple of exceptions. And notice that at 1 megahertz, we start at the left-hand side of almost 2 decibels and go down to like 0.2. If we go up to 100 megahertz, our 2 decibel loss cable, RG174, is all the way up at 9 decibels. So 9 decibels per 100 feet. What is 9 decibels almost equal to, everyone?
10.
10, and 10 means what?
10x.
10 times. So if you put in 100 watts, how much power will you get out?
10.
10 watts. And what happens to the other 90 watts?
Heat.
Yep. So you've basically done nobody any favors by doing that. But notice, just by going to RG58, you've helped a lot. You're down to 5 dB. That's a lot better. But if you're putting in a repeater system, you have the money to spend. You might as well do it right. Look all the way to the right. At 100 megahertz, you're at 1.4 dB. Right? That's, if you put in 100 watts, you're probably getting 70, 80 watts out. That's a heck of a lot better. But now also notice that, let's say you're going to a 900 megahertz system, even the really good cable, you're still losing 4 dB. So for 100 watts in, you're getting about 35 watts out. Which is why, if you're building a really high frequency system like microwaves or like a TV station transmitter or something like that, your coaxial cable might be 6 inches in diameter. It might be 6 inches in diameter, and instead of being filled with plastic, it's filled with dry nitrogen to keep it watertight, airtight. So that's, it all comes down to what you have money to spend on and whether or not it's really important. So, all right, how's that for a first day, everybody?
Very good. Very good.
Enlightening.
That's awesome.
Okay, so tomorrow I think we start with a little bit of safety, and then we get into radio frequency systems and equipment, and I'll stick around to answer questions too. I still have a little bit of voice left. I hope this has been, I haven't really referenced the book all that much, but if you look at the book, I cover most of everything that's in the book.
I think this is really helpful for somebody that's getting started in this, that knows something but doesn't know the real ins and outs of ham radio.
Yeah. Well, and part of it is applicable to just any radio frequency systems and basic electronics. And that's kind of my goal. That a lot of people will use like, oh, well, here's the antenna to use, here's the cable to use, but you don't really know why. And really what it comes down to is a decent understanding, or at least a respect for the math behind it.
I really enjoyed, Scott. I really enjoyed, because I've been through the book a number of times, but to have you reteach it and use basically the vernacular, regular words, made a lot more sense. This is the first time I understood the donut of the antenna. So thank you very much. I look forward to tomorrow.
Cool. So what I don't know is what the exam session looks like yet. If you can wait a sec, I can take a look and see. And I don't know if people maybe dropped it because, I mean, like I said, I had 243 people sign up and there were 111 people here. So
still a good turnout, though.
Oh yeah, this is ridiculous. But
Right.
but you know that anybody finds me, you know, that good of a teacher that they're willing to give up 2 days of their weekend to do it with me. So, give me a second here.
Well, hi Scott. Sorry to interrupt.
Yeah.
This is Art, KK7QFT. I
Hi,
took
Art.
your first class last year, end of December, beginning of January, and I've been having kind of fun with that, beginner handheld radio. But I'd really like to try to get the general license. I got the technical one, and I joined your class today late because I didn't have the link. Thank you so much for adding me to the class.
Yep.
And I wanted to ask you, usually you send kind of a repeat or replay of your session. Will you be sending that?
Yep.
Will you email that? Okay.
Yeah, I'll be sending out a recap.
Okay. Thank you.
So where do you live again?
I live in Weston, Oregon.
You live in Weston, really?
No, not Weston. West.
Oh,
Lynn.
Weston. Okay, I know where West Lynn. Okay.
Yes.
So have you gone to any of the local clubs up there? Because I know Otvark, if you're not far from Tualatin.
I got in touch with a few guys. We talked on the radio, and I haven't. But then I've been talking to some folks in Vancouver. They have a kind of a morning session every day. And a few guys here in Lake Oswego. But I have not. For our last conversation, so I have not been a member yet of a club, but it's in my to-do list.
You got to just show up at a meeting. Cause show up at an Otvark meeting. They're such a good group of people. It's a big club, very, very diverse.
Thank you.
Really
I
good
will
club.
do that. Yeah.
Really good club. How mathy is the tech exam? That's a good question. I mean,
I've done samples and I didn't run into too much stuff that I couldn't handle.
Then that's what you'll see.
Okay.
Because here's the other thing: you'll never find an exam question that you have not seen, or you couldn't have seen if you took everything a million times.
Yeah, that's why I came today, because I've been studying on my own and I just wanted to hear someone talk about it in terms that I could understand. And man, you're awesome. You're awesome. Thank you. Thank you for that.
Well, I mean, I can talk about it in engineering terms too, if you like.
No, I'm good to go. My brain is full today.
As I was telling someone, I can get as deep, and part of it is if I have a small class and somebody wants me to go into something, I'll say, okay, do you guys want to see this?
Getting into the weeds.
And we'll really go into the weeds,
Yeah. All right. Well, I'm in Florida, Central Florida, so I'll be here tomorrow, noonish.
Yep.
And I just wanted to say thank you again. And I do wanted to talk to you possibly tomorrow or when you have a free time. I'm working a program through the VA. It's called a VR&E program, and I'm doing the independent living.
Mm-hmm.
And they've told me that, hey, they're going to give me some basic equipment, but they want to see me have my license first.
I don't blame them. That makes sense.
So I don't either. So I'd like to know, what could I ask them for as a basic base and a basic portable? And
I mean, is it going to be? Are you going to get your general license?
Eventually, I will.
Because it really comes down to that. I mean, if you don't have a general license, I wouldn't expect them to get you. I wouldn't expect them to have any incentive to go anything further than some kind of VHF UHF system.
Yeah, I'm trying to get it into the plan that says that they're going to go for the duration, so I'll have all three.
Mm-hmm.
I'm still working on that portion of it, so I'm doing baby steps until I can get that in writing, because you got to get it in writing, of course. But I plan on going
federal program, right?
Yeah, I plan on going all the way.
Yeah.
But,
well, it's I like I said, tomorrow I'm coming up on 40 years tomorrow.
Oh.
So
nice.
It's in a lot of ways it's sort of guided my career career and hobbies and friends and enjoyment and travel, and yeah, I owe a lot to ham radio, and I guess I kind of like giving back. So
Okay. Well, thank you again.
paying it forward. So
thank you for your time. I appreciate it.
Other questions? I know people have questions.
I have a question. I go to the desert a lot, and people have radios in their buggies and things like that, which talk on more channels, not necessarily. Well, obviously they're a frequency, but it's a channeled name. For example, like I think PCI and some of these other companies sell these radios for that kind of a purpose, and they talk within the ham frequencies. How would they do that? How are they allowed to do that? Or do they buy those frequencies?
No, legally they're not.
Oh, okay.
I mean, they could be, depending on what they are, they could be operating on MERS, which is multi-use radio service, which is 154 megahertz. It used to be called like Blue Dot, Green Dot business band.
Yeah.
It could be another version of GMRS. You know, they could be GMRS radios. If they're on the ham bands, they're not supposed to be there.
Yeah, I'll have to look them up, the frequencies. I don't have it right off the top of my head, but maybe I can look it up on my phone.
And I've yet to see from how often do you okay, well, as far as the online test goes, you know what? Now this is a good time to bring this up here. Don't anyone go anywhere. Okay, has anyone ever been to hamstudy.org?
Yeah, I have.
Okay.
Yes.
See this find a session remote? I want everybody to notice, here's the list of available online sessions. Here's just today. And here's tomorrow.
Oh, wow.
And Sunday. And Monday. Tuesday. Wednesday. I mean, you can sign up with anybody.
I noticed your session was the only Sunday session that you showed having scheduled.
No.
No, I scheduled one, and I think it's in LA.
Well, it's not LA per se. It's probably with Glarg.
Yes, it is.
Greater LA Amateur Radio Club.
No,
Yes.
I was saying like the Anchorage group. I didn't see any other Sundays for like the next couple of months. It was the only one that I saw, unless they're already filled.
Oh, I mean, there's Saturday, there's Sunday the 8th.
Yeah.
I mean, I know typically the Anchorage Club doesn't test on Sundays, but a lot of other clubs do. So, I mean, this is what? 1, 2, 3, 4, 5, 6, 7, 8, 9 exam sessions. This one has 6 seats. I mean, it used to be really hard to find a test. It's not hard anymore.
I don't know if I missed this or not, but if you take it and you don't pass it, are you repaying for each time you retest?
It depends on the examiners. It depends how they feel. It depends how busy they are. Typically, like if it's me, no. Depends how close you are too. You know, if you miss by 1 or something or 2.
Okay. I know my brother administers them, but he's out of the country right now, and I'd rather get it through somebody else.
Actually, he's not. He's not allowed to give you an exam anyway.
Okay.
You can't have any relatives do it.
Yeah, and that's kind of what I felt about it too. I'm like, yeah, I'm just gonna go.
Well, legally he can't.
Yeah.
So.
Yeah. Good.
Yeah, that's one
Any
of the
idea how long until successful results are communicated to FCC to go up on the database?
I mean, if you pass, you'll know immediately.
Sure.
And then, because the Anchorage group is the VEC is the one who posts them. If it's on Sunday, they'll have it on Monday morning, and you'll probably get something Tuesday morning that says time to pay.
Yeah. Okay. All right.
Okay, so when you test, the tester will submit that automatically, and
that same
then
afternoon.
the FCC will request the money then for the license. We don't have to send nothing in or do anything. Okay.
I think the hardest thing is to get that FCC number in order to put in a lot of these things. Yeah, the
FRN
number. That's just a whole web of mess that they got going on their website.
But if you have a GMRS license, it's the same FRN. At least there's that. So
I did go that far. I do have that number.
But I mean, okay, let's address the elephant in the room. That I'm kind of agnostic with regard to equipment. I like ICOM HF, I like Yaesu VHF and UHF, but somebody had asked, "Well, are you going to teach me how to use a radio?" I'm like, "No, that's up to you. I'm not going to tell you what to buy. I'm not going to tell you how to."
Too many different ones to be able to tell somebody how to work it. Yeah.
Right. I mean, I cover how they work and what they are and how in general what to do, but there's so many choices. I can't possibly do it. So, and that's again where your local clubs come into play. So,
hey Scott, back to that question about those frequencies that they use in those off-road radios and stuff. They're like anywhere from 150 to 154 megahertz.
Yeah,
that's all kinds of them in there.
That's called MURS, MURS.
Okay.
Which is multi-use radio service, and they call it licensed by rule, I believe. And that means that it's automatically licensed.
Okay, because I know some of them look like they're owned by BF Goodrich and all these racing teams.
Yeah, well, I mean, they could have specific frequencies that they actually get licensed for, but in general, the MURS frequencies are open to anyone.
Okay.
And typically, the MURS equipment is fairly high quality stuff. So,
yeah.
Other questions?
No.
Nothing? Nada?
No.
Oh, Scott, this is Art again.
Yeah.
Quick question. When it comes to the book, I'm not sure if you have already emailed the link of the book that you're using, but I haven't received. I'm not sure if you can resend that or.
I don't know if I sent it to you or not. It's the same book.
Oh, the same book you sent last year?
Yeah.
Oh, okay. Then I should have that in my old emails. Then
yeah,
I'll look for it.
Let's see. Oh, mismatch lost DB. Ooh, okay. Now I got to go there. Silicon Labs. Here we go.
Got a question for you.
Yeah.
You said I have my GRMS and I've been trying to get into the FCC site. What is the number that I have to get in order to register to take the exam that I should be looking for on that?
Actually, if you have your GMRS license, there's an FRN that you already have, which is a FCC registration number, I think.
Correct.
Yeah, you should it should be actually on your GMRS license.
Okay. Will do.
And that's the same number that you use to get into their website and access
register for the exam.
And access your existing license.
Gotcha. Okay.
So there's basically an FRN that you use to get online and administer your license and print out an official copy. It's the same one.
Thank you so much.
Yep.
So that's the site where you would see that your license had been issued.
Yep.
That makes you legal to start transmitting.
Very same one.
Okay.
Yep. It's the FCC ULS, Universal Licensing Service or System.
Could you repeat that again? I'm sorry.
The FCC ULS, Universal Licensing System.
Okay.
Here.
Awesome.
FCC
All right,
ULS.
I'm learning a lot.
Here's FCC ULS. It looks like this.
Okay. Okay.
This is also where you search for existing licenses, new licensees, available call signs.
I want to say I did that already, but I want to say they gave me a number, but I have to go take the test. But I do have that number. I need to find it.
Yeah,
You should be able to search it on that site and find it, right? By your name and
by name.
location or
Yeah.
something.
Name. Okay.
Yeah.
Now, I don't know if that'll actually allow you to find it because do you have a license already for something?
I personally don't.
No. Okay. So, yeah, I don't know if it'll do that or not.
Okay. I'll have to
Should be able to do an FRN search.
It let me do my name search and I get a common name.
Yeah.
Yeah, you can search by FRN or you can search by name and it'll give you the FRN.
Okay.
Well, I was just wondering if it. Let's see.
And we have to have that FRN,
Yeah,
right?
type
Yeah, you
type
do.
in. Yeah, I was gonna say, Scott, if you want to type mine in or something like that, it should give you the FRN.
I'm such a newbie here.
I don't know if it. See, their site is.
You have to do it under advanced search
see.
and then by
Yeah.
state, and then you have to put last name, comma, first name.
It's like I said, their site is fussy.
Yeah, it's tricky, but I had to look mine up because I couldn't remember what it was.
So government.
Yeah, it is.
David, this is Harry Whitty down here. I sent you a PM with my contact info. I'm over in the Tampa, Florida area.
Okay, I think I've been talking with you here for a minute.
I don't know. I've been on here. Thanks.
All right.
Yep.
Thank you. I appreciate you.
Yeah.
All right. All right. I'm going to head out.
Anybody else with anything else?
Thanks for everything, Scott.
I just wanted to verify. So if I have, if I already have, like if I have an FRN number, I just use that one.
Yeah.
Okay. And it won't be tied. Well, it'll be tied under cores with my current operator permit.
I would think so.
Okay.
Usually.
Right.
So.
All right.
Tomorrow's going to be
everybody.
a busy
Thank
one.
you.
Tomorrow's
See
going
you
to be a
tomorrow.
busy one.
All right. Take care.
See y'all. If anyone has any more questions, I can still stick around. I'm guessing not.
Okay, last question. Tomorrow.
Okay.
Tomorrow, what time does the class start?
9 o'clock.
9 o'clock. Okay, you're going to send another link, Scott?
It's the same link.
Same one. Okay, great.
Same one.
Awesome. Thank you.
Hey, Scott.
Yeah.
Is there much of advantage to the tri-band versus dual band?
Well, if that tri-band is 220 megahertz, if the thing that gets added is 220, it depends where you live.
Right, yeah.
Because there's not. Okay, so the story with 220 is that it used to be a 5 megahertz wide band. Then UPS made a deal with the FCC that they would take over 220 to 222 and give the hams 219 to 220, but it can only be used for some very weird esoteric things. So 220 is a 3 megahertz wide band now from 222 to 225. And the other thing about it is that it's not a ham band in Japan. And as a result, the Japanese manufacturers have been very reluctant over the years to build any 220 gear. So there's not that much of it out there. There aren't that many 220 repeaters unless you live in like LA.
Okay, probably not. Well, I had already bought a couple of those inexpensive Bofangs just to have something to tinker with and just listen. But we have a pretty active club in my area. I see it on Facebook. And I guess once I get licensed, I'll start getting involved with them and seeing what all they're using in this area.
Where do you live?
Mobile, Alabama.
Okay. I was in Opelika last month.
Oh, okay.
I travel a lot for work.
That's up up north, isn't it? I
Up,
think
yeah,
it's
northeast,
yeah,
east central,
It's-
a little
yeah.
north of Auburn.
Yeah. But I travel between Mississippi Gulf Coast to Alabama Gulf Coast. Um, yeah. Okay. I appreciate it.
Yeah.
All right. See you tomorrow.
Really, any other questions before I go? It's okay to ask. Oh, transmit deviation. You really want to know about transmit deviation? Okay. All right, Shay, are you ready? I can't hear you, though. Okay, Shay. Okay, hold on. Shay's muted. I'll wait. What, still muted or am I muted?
No, you're still fine.
I'm good. Okay.
I can't hear him now.
There it is. Hey.
Okay. Hey.
I couldn't get my microphone to connect for a second. Sorry about that.
Okay. Okay. So, here's FM. Deviation is kind of a weird thing, right? Because deviation is a measure of how much your signal varies from the center frequency. And essentially when you're talking, right? Your signal will go like this. Let's say you're putting a single tone into your receiver, into your transmitter.
Okay.
Right?
Yeah.
Okay. So the number of times that this happens. Let's say you transmit like a 500 hertz tone. What you'll see is that you will switch 500 times per second from a higher frequency to a lower frequency, back to higher, back to lower, 500 times per second. Right? That basically is how your tone is encoded. The degree to which you deviate from the center frequency is your deviation. So if your center frequency is, let's say, 146.52, and when you're using that 500 hertz tone, your frequency deviates from that. Again, 500 hertz per second, or 500 times per second, but let's say it goes down to 146.51 to 146.53, then your deviation would be 20 kilohertz, or plus or minus 10 kilohertz.
That suddenly makes a lot more sense.
Right?
Yeah, it's not how loud the signal is presented to the op amp, but it presented itself that way.
But part of it is because it's typically proportional to the amplitude. The amount of deviation is typically proportional to the amplitude.
Okay, that explains why I thought of it as a volume control, just by looking at it.
No. There's a mic. Bigger radios might have a mic gain, but typically not on handhelds. They will typically, you'll essentially be able to modulate your deviation by literally putting it closer to. If someone's telling you you're not deviating enough, that means put it closer to your mouth.
Okay.
And basically increase the audio power going into the modulator, and give it more of a chance to swing further. Now, I will say this is actually really cool. If you want to see, this is, you would never believe it if I told you, so I'm going to tell you anyway, okay?
Sure.
Okay. There is a video, FM Radio Basics. Let me see if this is what it's called. It was produced by the U.S. military in 1944. And, oh, here it is. I found it. I'm going to actually put this, blah, blah, blah. Hold on. Yeah. Okay.
I recently saw a video on the V Westlife commercial. Carson had not approved at maximum
That's
into
not
an
it.
FM station and does not change. When a guitar string is plucked, it
That's not the one I'm looking for. But I will find it and I will send it out there. It was actually the best description. Oh, here we go.
Headache.
It is.
Lightning, for instance. Hitchhike.
It's the best description of FM that I've ever seen. And it's 80 years old. Let me make sure I can get it.
I swear I've seen that somewhere before, and it's like it lives in my head rent free, like from high school at some point, maybe.
I was shocked at how good it really was. I mean, I did, all the mathematical derivations of AM and FM and stuff when I was in college. This is the best explanation I've ever seen of FM. So I put it out there in the chat. All right. Let me unshare this. All right. Anybody else with anything else?
I'm really glad I asked. Thank you for answering me.
Yep. Nothing else? All right. I'm going to go and watch some football. Maybe.
Thank you, Scott.
Thank you, everybody. That was fun for me.
Thanks, Scott.